You start the fire. I'm trying to find what you like. Oh, you and I won't close our eyes till we cross that line. There's something about you, something about you. You know I crave your touch, but we don't need to rush. There's something about you, immersed inside my mind. Maybe it's a sign, 'cause it's already over, already over, already over, already over, already over, already over, already over. Tell me what you desire. Let's get lost inside, lose track of time. Oh, and every side, we got nothing to hide. Wanna see your skin on mine. There's something about you, something about you. You know I crave your touch, but we don't need to rush. There's something about you, something about you. I know it's hard to find. Listen, it's a sign, 'cause it's already over, already over, already over, already over, already over, already over, already over. It's already over, 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 overload.
Please welcome to the stage Jelena Pieszewicz-Grobowicz from Meta.
Hello, everyone, and welcome to At Scale AI and Data 2025. We're thrilled to have you join, whether in person here in Santa Clara or online as our virtual audience. My name is Jelena Pieszewicz-Grobowicz. I'm Engineering Director of Real-Time Data at Meta. My teams fuel Meta growth by delivering high-quality, ready-to-use and fresh data wherever it's needed. I'm thrilled to be here with you today. Whether this is your first or nth time attending At Scale event, we're thrilled to have you here. At Scale is a technical conference for engineers who build, maintain, and support systems at scale. New this year, we have in-person and virtual events for all of our 4 themes. And our programs bring together complementary themes that create event communities and collaboration across the industry. For today's AI at Scale event, we have an exciting lineup of presentations, panels, posters, and Q&A sessions for you, and we can't wait to get started. Today's theme is building a world in which agents interact with billions of users. Through the speakers and panels, you will learn about the latest development in agent deployment, and product integrations. We'll also touch on many critical topics such as scaling, data for agents, agent tools and environments, and safety and privacy. But AI and data is more than just the agents. So we'll also have an exciting in-person poster session that touches many other topics in this field. We'll start today's, how we'll do today, right? Like what's the flow? We'll start strong with Meta's own Aparna Ramani, who will give us a key talk, and she will be joined by Ion Stoica, a famed researcher and a technical leader, co-founder of Databricks and Scale, and they'll have exciting fireside chat. Following that, we'll have presentations from many companies that all of you know and probably heard of, and some of exciting startups like Fiddler, Meta, NVIDIA, TowerDev, Snowflake. And we'll also have two panels. The first panel will be Gen AI panel, where we will discuss the world of reinforcement learning, post-training, and what it takes and how is it like to build up products on top of open models. We will close the day with infrastructure panel, which will explore how this infrastructure needs to evolve to support this new world well. If you're here with us in person, you will also get the opportunity to participate in the poster sessions after the main program. And you'll be able to submit your questions for the talks using that QR code. So without further ado, let's welcome Aparna Ramani from Meta.
Please welcome to the stage Aparna Ramani from Meta.
All right. Welcome, everyone, to AI and Data at Scale. I can't believe it's been a year since we all met last year. And AI has just gotten so much more interesting and so much more dynamic than ever. So let's look at what happened this last year. As an industry, the last time I was here, we talked about how we made more progress over the last 3 years with AI than we've seen over the past 75 years of history combined. This is the log curve showing the total training flops over the past 6 years. And the blue line shows the flops, growth in flops, starting from GPT-2 series around 2019, all the way to the Llama 3.1, all the way to 405B in 2024. And now, if you map this on to Moore's law, I'd like you to think about where the projections of Moore's law would fall relative to the blue line. And there it is. The incredibly fast exponential growth of Moore's law that has underpinned modern computing for decades, nothing compared to the growth that we see in AI. At Meta, closer to home, we have over 1 million GPUs in our fleet right now. And that's quite a statement for compute. The second thing that's happened this past year is that models have evolved. Turns out models can now think and reason. We saw the launch of O1 from OpenAI in September, and that unlocked the ability for models to think longer at test time. And these models, largely enabled by investments in reinforcement learning, and we'll talk a little bit about that in a second, are the foundation for the agents universe that we live in today. Reinforcement learning doesn't just help with reasoning. It helps with post-training in general. And I just want to show you this graph. And here we're looking at the performance of our 70 billion parameter model in comparison to our 405 billion parameter model. The orange line here represents the 405 billion parameter model. And the other 3 lines show the improvements we've made in our 3 series throughout Llama 3's life cycle. And in particular, 3.3 was the first model to leverage online RL. And the 3 graphs here show 3 different evaluations. And you can see that Using online RL, we were able to reach the performance, even with a 70 billion parameter model, on par to a much larger 405B model. And the only difference here was post-training. So scaling post-training through reinforcement learning just works. So we saw that the availability of compute helped this creation of the next generation of models. And so this combination you have of compute and these growing model capabilities have now led to a Cambrian explosion of AI products. We know there's dozens of coding agents out there. And I know there's many entrepreneurs in this room with products that you are building that you want to showcase later today. Really, really exciting time for AI products. So infrastructure has been a massive enabler for product evolution. And of course, we see this in our own product landscape at Meta as well. We're moving from an era of chatbots to an era of agents, where we can tell the AI to do larger tasks for us. We can ask the AI to use tools like humans do. We're also evolving from an era of image generation to video generation. And even as we increase the complexity of our products, we're also increasing the number of surfaces that are available for AI. Communication applications like WhatsApp to wearables like glasses. So it's a pretty exciting time for the rise of AI products around us. So last year was pretty big. And what's interesting here is that not all of the progress or the direction of the progress was particularly predictable. Research is, by definition, unpredictable. Sometimes our hypotheses pan out, and you land up with a very disruptive innovation. And sometimes they don't, and you have to take a reset and start again and try new things. So the question for us is, what can we do as infrastructure in a world where research continues to be so unpredictable? That's right. We build for scale. I mean, this is the at-scale conference. I cannot not talk about scale. But I really mean that we build for scale at every layer of the stack, and I'll tell you why. We know that AI progress is going to be compute-bound. We don't know how this compute is going to be used. It could be used for pre-training, because we don't know where pre-training ends with the scaling laws. We at Meta have over 3 billion users, so we know there's going to be a huge demand for inference workloads. And we also know we want to invest in post-training and reinforcement learning and all of that stuff. So we have to continue to build compute, because we know that compute's going to be the driver for AI. We at Meta are creating massive interconnected clusters, roughly equivalent to a gigawatt in power. That's like a million H100s. And the idea behind creating a massive cluster like this, it gives us flexibility. You could use this cluster for pre-training, for post-training, for inference. But in reality, if you really, really want to use such a huge cluster, there's many scaling challenges. For one, we need networking, and lots of it. Just the planning and orchestration alone can take months and years, but not only do we need to lay the pipes, we need to create new kinds of networking protocols, new kind of communication libraries, so we can communicate at extremely low latencies, so we're not starving our GPUs. 1 million GPUs. 1 million GPUs can fail a million ways. And so we need to build fault tolerance techniques that are an order of magnitude better than the state of the art today. And we've done a lot of work already at Meta. We created debugging libraries, and we have a huge slew of diagnostics all the way from the hardware to the software layers. But scale makes everything that much harder. And so I suspect we'll see a lot of just innovation in this space over the next year. We also need to be able to support multiple types of hardware. Accelerators are also accelerating at a pretty rapid pace. And we cannot afford to have static infrastructure, which means our software needs to adapt to all kinds of new accelerators within a singular cluster, sometimes even within a singular training run. And you all understand how difficult it is to have a singular training run that's dealing with multiple kinds of hardware within the same run. But that is what we're preparing for. And of course, we need to scale reinforcement learning to be able to enable this growth in agents. The concept of reinforcement learning, by the way, is not new. It is actually one of the oldest approaches to machine learning. But what is new is the scale at which we want to do it. This is one depiction of all the different components in reinforcement learning. And I won't go over everything today, but I want to emphasize that the setup and the complexity for reinforcement learning is just vastly higher than for pre-training. All of the work we've done in pre-training that I've talked about last year is within a single component in this reinforcement learning loop, which means we have so much work as infrastructure to get the rest of this working, to make it real. For example, there's a box here called generators, and that's really just having inference work within a training loop. And so we're incorporating a ton of inference optimizations all the way from flash attention kernels to speculative decoding. Everything that goes into production now is making its way back into the reinforcement loop as well. Then the model needs data to learn. It needs to be able to interact with tools, and it needs environments to operate in. And this is a much harder problem than people anticipate. We need to scale out environments and explore different strategies. So we're building coding sandboxes for the model to be able to execute code and learn code. We're creating web browser simulators. And we have to create these simulators to be as close to the real world as possible, because you don't want the model to learn one thing and then do something else in the real world. And so these are hard problems that we're tackling. But here's the thing. We talk a lot about scale, and scale is absolutely critical. But in a world of such rapid iteration in research velocity, if researchers cannot leverage scale, then what is the point? So in addition to creating and enabling scale, we need to give researchers the superpowers to be able to do experimentation rapidly. I know, Hulk was a favorite. We need the researchers to be able to find the next innovation. We need them to incorporate it into our products. And we need them to be able to do it fast. We need to supercharge them. And so how do we do this? We do this by investing in new programming paradigms to enable researchers to move fast. And of course, we have a huge advantage as a community with PyTorch. It is the language of choice for a majority of the researchers. And so now we're working on a new programming environment called Monarch. It is a distributed execution engine for PyTorch. It builds on a single controller architecture. And the idea here is that a single ML researcher should be able to develop a hypothesis, an idea, and be able to sit down, use their Jupyter notebook, and then be able to execute that idea, whether it's on a single node or a local host, or whether it's a cluster of millions of GPUs. It should not matter to the researcher. So they need to be able to operate without worrying about fault tolerance, without worrying about scale, without worrying about the underlying implementation of our infrastructure. That is the idea behind what we're trying to do next for research at Velocity. Monarch, by the way, is still early in development. It's available for people to iterate on and give us feedback, so please feel free to use it. We'd love your feedback. If you take a step back and look into the future, so much of what we will do is going to be powered by AI. Compute will be one of the largest drivers for all the progress we'll see ahead of us. So much so that I think we'll actually run out of power in this universe. So it's not that we just need, of course we need to scale. Of course we need new programming paradigms. But we also need a new mindset. Because if you think you're going to be prepared for this next phase, I'd encourage you to think again. Because we have not yet solved some of the things that I refer to as our grand challenges for infra ahead of us. AI infrastructure is rapidly becoming one of the largest consumers of power on this planet, and we are going to run out of power pretty soon. So is there a way to create hardware that is as power efficient as the human brain? Human brain operates at 20 watts and is more efficient, more intelligent than any of our large AI clusters. Can we do that on our hardware? Can we pre-train a large foundation model within a singular hour? Models like Llama takes months, years to develop. Just imagine if we could convert that into weeks, days, hours. The leap forward we would be able to get towards our progress, towards AGI, would be unparalleled. And how efficient would that be? AI is still incredibly expensive to run. And as inference optimizations are being worked on, we still are not at a point where everybody can access these capabilities. And so how can we make inference infinitely cheaper so we can have AIs everywhere, in every pocket, every notebook, every application, everybody, no matter where they live, no matter what the economic status is? What does it take to get AI to be that accessible? That's a challenge that we need to look at. And these challenges are going to require us to come together as a community of AI users, application builders, infrastructure creators. And that is a worthwhile journey for all of us to be on. With that, I want to introduce to you somebody who spent a lifetime working on grand challenges, Ion Stoica.
Please welcome to the stage Ion Stoica from Anyscale.
All right. Ion, you're incredibly prolific. You have been an academic. You continue to be an academic. You founded Databricks. Those of you who don't know, Ion's the founder of Databricks. And you continue to build really impactful projects. You're creating startups. How do you do it all?
Have great students. What can I say? I think that it's like everything I'm trying to do is starting with a problem. What problem try to solve? And you try to figure out the kind of problems which are going to have to be, to be longer term, right? It's like your solution, whatever you are doing, it's only as important as the problem you are going to solve. Because if you don't solve a particular problem, why would people use what you have done? And this is true both for systems, but theory, everything. So I think that trying to figure out, to understand what problems you are trying to solve, I think it's the first very important step. And then when you try to do that, you try to think about how do you pick the problems. It's like a lot of them are, looking at the trends out there and see where, because the trends is something which is hard to change. And you want to, in some general, to be on the right side of the trends, right? That's kind of the high level.
Okay.
And of course, the other one, you have to have, great students and, let them, solve the problems and get out of the way.
So, I mean, a lot of the advancements are being pushed right now by academia. Like, I see so much innovation coming up there. And many universities seem to be challenged by just the lack of compute in academia. Your students seem to have figured out a path forward and seem to be successful in just creating projects that the whole community now can leverage. VLLM, Chatbot Arena, LLM Arena, all of this is coming from your lab. How are you able to do that? And how are graduate programs moving into these incubator programs?
Yeah, so again, you start with a problem and then you try to make sure that people, the students, they don't learn too early what they cannot do, right? So I think this is one of the keys. Like I am old enough, so I remember during my PhD I was attending these conferences at SOSP, the premier conference in operating system, and other than panels about the operating system research is dead, because at that time this was I don't know, what is 96 or something, 95 I think. It was my first SOSP conference I attended, and operating system is dead because Microsoft is 90% of the operating system market, and it's like a few percent Apple and a few percent of this kind of Unix vendors at that time. And of course, after that, it came Linux, which it was very disruptive. Later on, actually, when I come to Berkeley, we have this kind of labs, and it was this kind of things about, well, the industry in that case was Google, are doing all this kind of great distributed system and so forth. So we are going to, have ideas, build prototypes, and at the end of these labs, we are going to put together a demo. Everything we were putting together, and we were lucky then, because of this kind of rise of the big data. So everything was new, Cloudera, Hortonworks, Hadoop, right? Yeah. And we have collaborated with all these people, who from industry. And we saw this kind of openings for doing something which mattered then, which was Spark and before Mesos. And I think that was one thing which is started to give confidence that you can actually have an impact, despite the fact that you are in academia. And since then, we are trying to, to maintain that confidence and tell people, you can do actually more than you believe you can do. And then, yeah, it's true. I mean, it's like, it's, the lack of resources is kind of massive. But, for inference, you don't need as many resources, like for pre-training. Yeah. So it's, again, it's hard, but in general, you can do more than you think you can.
Yeah, I'd love to get a sense of what are you most excited about? You've got so many projects that you're working on. Where is the most excitement for you?
Yeah, so I think a few things. So one of the excitements, it's about, obviously, I'm coming from the system side, and I think that the AI stack, and I think I'm still very excited about that, and about it's obviously like we see everything. It seems more and more vertically integrated, right? Because you want to use all these resources more efficiently. Everyone is doing that. So I think that direction is going to continue, and it's going to be interesting how this is going to play out. The other trend, obviously, is about this using the code assistance for optimizations and so forth, system optimizations, kernel optimization, and so forth. Right. So I think ideally you want to see how that also will play out and will fit in. Like we have so many accelerators. So, like in particular, one problem I think there is that because you can think about it, you have so many accelerators, right? Today, it's of NVIDIA, it's AMD, it's Trainium. You have your own chips here, yeah. And TPUs and so forth. And you want to use them. On the paper, they are very high performant and so forth. But it's still everyone what telling you is like the software stack is not there, right? Right. It's very hard to write a high performance kernel. I mean, it's hard to write high performance kernel even for NVIDIA. Yeah. So I think that's kind of a problem that, and I think that is going to be solved because it's pretty contained, right? It's like you can, once I have a kernel which is kind of run correctly, I should be able to have all the tests and so forth, so to run on a different and optimize on a different hardware. But I realized more recently that actually the problem is not that one. The problem is that these stacks are not, they have a lot of bugs. And there are bugs at all levels, hardware level, firmware level, software level, right? Yeah. The documentation is out of date. Yeah. So it's not that you are going to try to optimize something for a clean, environment. Yeah. Like, talking about RL. Yeah. It's not. It's a very, very messy environment. So actually, that's a kind of the problem, because you need to generate code which kind of avoid and goes, the bugs and so forth, avoid triggering them and things like that.
Yeah.
So I think that's one aspect, I think, which is exciting. The other one is like, at a higher level, it's how do you build reliable AI application? By reliability means predictable and so forth. I do think that one of these is one of the biggest problems that confronts today's AI, because despite all the promise, it's really going to be very successful only if it's reliable, right? And especially for the high-value use cases.
Yeah. So speaking of RL, since we talked about it, where do you think it's actually scalable to the point that it becomes absolutely useful? Do you think it's here to stay? We've looked at RL over the years.
I'm biased, right? We work on RL for, early on for almost 15 years, 14 years. So we built Ray, actually, the main library in Ray. It was RLE, it was reinforcement learning. And that was the main library for a while. I think, yes. I think that RL will have more and more impact. And there are several reasons for that. If you look in the past, one of the challenges of RL, now reflecting back, was that it was very hard to integrate in the existing workflows, processes. Like you want to do it in an enterprise and so forth. It wasn't easily being integrated.
Yeah.
And I think that one of the main challenge. I'll comment more on that. But today, it's like if you think about what an agent is, like in the simplest definition, it's an agent, it's a large language models which uses some tools, in particular, browsing the web, whatever, or calling a database. But if you think that you already have the setting for RL, right? Because that's kind of an agent also in almost in the RL sense. So you already have that, right? So you let it, this agent, collect traces and so forth. So there is no longer a problem about fitting in that workflow. It's already there. And I think that's a big deal. The other thing, obviously, why do people use RL is because with RL, you can learn new things, new solutions, right? That's how you have exploration and so forth. So now these large language models, and this is very relevant, are trained on all the data you can find.
Yeah.
If you don't have enough data, you buy other companies to get more data. But that's kind of clear, right? But then it's like, so how you add more data, and this RL, it's a source of providing you more data.
Yeah.
And you have to think about, like analogy, well, not analogy, but you have to think like AlphaGo, right? The AlphaGo, right, is like, it has different stages. In the first stage, because people say, oh, now what is RL different is that you have this kind of large language models which are already very powerful, and you don't need to do it from scratch. But it's again, if you think about the AlphaGo, there are a few things to keep in mind, because there are many papers now about which are published, basically say, oh, RL is not very useful. It's only elicit information from, like knowledge from the base model, all of these things. But if you have to think at AlphaGo, actually there are a few stages. And the first stage, it's actually building a supervised model based and we train it for all the games in the history. Right? They are played in the history. Yeah. So that's the first one, right? And this is equivalent with the LLM being trained on all the kind of human knowledge. But then you have the next stage, which is kind of the RL stage, is a self-play. So you are going to start playing these kind of models. And then when you are going to play against each other, you are going to learn new kind of moves in that particular case, right? Reinforced moves, which are not in the previous games. So that's kind of new knowledge. And that's what makes actually AlphaGo performing better than humans. And then it's a last stage MTCS, which is basically doing a little RL, but more efficiently. You basically learn a reward model. But that's kind of, you have to think about that. That's a parallel. Now, the problem is that RL is notoriously sample inefficient, right? You need to spend a lot of compute in order to get great results. And that was true back then. It was much more, you needed more compute than you have than supervised learning. right? So, and for obvious reasons. So if you think about RL, it's going to be pretty computer intensive to get great results, right?
Yeah.
Yes, if you do it a little bit, you are not going to get great results, but your conclusion will also be wrong. So I think that's kind of, and because of that, because you can accumulate new knowledge, because you can come up with eventually new solutions, and which are not in the base model. By the way, the base model, you can, for every next token, you have some probably non-zero probability, in theoretical sense, to pick any other next token, right? It's about the probability distribution. So the base model, in theory, is like it can also derive any solution. The question is, of course, the probability distribution, how likely it is. What RL is doing, it's modifying the distribution. So to learn, to make some moves which are not before, or some generate next tokens, we generate new solutions more likely than the base model. So yes, I think that, but there will be more techniques like this kind of evolutionary algorithms, like in AlphaGo and so forth.
Yeah.
But in all cases, for RL also to be successful, which was also true many years ago, it's about this kind of verification, right? It's a reward function, right? You generate a solution. How do you know it's good, right? With the games, which was very successful early on, that's a question. It's addressed pretty clearly, right? You play a game of Go or you play a game of chess. You know when you win and you lose, right? It's unambiguous. It's very clear, right? But when you try to apply RL to more kind of domains, that can become much more ambiguous, and ambiguity is going to hurt you, right? It's like the more precise you have kind of this verification generating this kind of reward, the faster and progress you're going to make.
So let's switch a little bit direction, but with the results we're seeing with RL, assuming we have all of the compute, assuming we solve some of these problems, do you anticipate using these kinds of solutions for systems problems, systems efficiency,
Absolutely.
kernel building,
Absolutely.
These kinds of things? Where do you see the applicability?
There is no reason to have more, to use RL and so forth for system problems. People use it also before. It's again, the key, it's about, there are many things you have to do, but the key is about, so first of all, what makes RL inefficient? There are a few things. It's like one, it's about if you need long trajectories, and then if you have a lot of choices at each step, right, a lot of moves, right? The games is also nice, and that was an early success because you are limited in the number of moves you can make in a game of chess or Go, right? You are limited, right? Yeah. But in other domains can be it's also continuous moves, not discrete, right? These actions, right? You can take. So the more you have to explore, and the longer the trajectory, even more, because it's exponential growth. So that kind of makes challenging. So I'm saying that because in order probably to make the most effective, you need to isolate from your system what is kind of important to limit the kind of choices you have. You can have an algorithms of scheduling and so forth. There are a few knobs you want, or a few actions, or what you want you want to limit the space, the environment, and the action space in order to be much more effective. And that will take some kind of domain knowledge to know what is important or not.
Yeah. A question for people who are in the enterprise right now. What should enterprises be doing to prepare for this world? What kind of infrastructure changes should they be making? How do they, what are some transformations that are happening in the enterprise to prepare for AI doing more?
Look, I mean, the enterprise is obviously, right now it's still, you try very hard to balance between, not missing out and investing in things which will not pan out, right? So I think as an enterprise, and everything is not only an enterprise. First one, you want to prove the value of what you are doing, right? So I would, so that's one thing. And there, you try to do that as quickly as possible, whether you are going to use homegrown systems or maybe you can leverage other systems out there, but that's kind of the first thing. This is what startups are doing, right? You have all these startups, they are starting with, oh, I'm going to use OpenAI, I'm going to use Gemini or so forth, and then, try when they are successful, then they try to reduce the cost and so forth, maybe bring more in-house, use Llama and other open source models, and in addition to that, to reduce, again, the cost and VLLM or whatever. So I think that's what you are going to see in the enterprises. Of course, they have a little bit more, there are more constraints because of the data and so forth. But that's what they try to do. It's like, and then some of these will be successful, some of them will not be as successful. And then you are going to, to double down on things which have been successful, right? Like customer support or whatever. Everyone is trying to do something like that, or some for their tools.
What is the role of evals in all of this? What is the role of evals in all of this? Like, how do you see evals sort of like permeating the enterprise?
Evaluation. Evals. Look, I think it's very important. Like I mentioned about one thing of what I think is the most important is how do you know the answers are reliable, right? And of course, we can go to LM Arena right now, and this is one of our projects. And it's difficult. So what makes things difficult here, to transition, is that the most successful AI application today, they have human in the loop, right? There are code assistants and, like we discussed, customer support and so forth. So you have humans interacting with these systems. Now, humans, they have preferences, right? And, this is this kind of the debate, like, should we trust humans in evaluating? Yeah, you should trust the humans to evaluate it, because the humans are the ones to interact ultimately with these large language models, right? And the humans, they do have preferences, besides the factuality of the context or content, right? It's like, it's not only that, right? We always like something, you have the same content. Don't you like to write that content from a well-written blog or articles, right? It's the same thing. Don't you want to hear, like the same content being delivered with, nice, beautiful slides and so forth, and by someone who maybe could be funny or whatever? Absolutely, right? So fundamentally, it's about human to AI application interaction. So you need to understand that what are the preferences? You need to quantify them. You want to factor them out. And I think a preference is like many things, like longer answers, right? Some people prefer longer answers. Some people prefer concise answers. Emoji, some of them prefer emoji, some of them, So, but the point here is that you need to understand these preferences, and you need to quantify them, how much it's going to improve, like, for instance, Arena score. And you can then factor out what happens when you factor out. And we've done all of these things. But this is the main point. It's fundamental. And it's fundamental, I don't understand why people really ask that, because even with applications, right, with the software application, we have, UI, UX, right, the designers, right? You guys, have a lot of designers about what is the most effective way for people to understand how people interact with Facebook and so forth, and your applications, right? It's true also for anything people build that other people interact with. It's like microwave ovens and cars and so forth. So that's kind of, I think that it's very important, right, to understand. And for any kind of applications in which people interact with AI, because, there are different AIs, different kind of artifacts.
Yeah. I know we're almost out of time, but I do want to ask one question for the data people in this audience, and which is, how do you see the world of traditional analytics and generative AI workloads and data for AI converging? Do you see an interplay there? Do you see a world where analytics disappears and it's all AI?
They are coming together.
They are coming together.
I mean, like, look, I heard that 2 weeks ago, Databricks, or Data Plus AI, it's called Data Plus AI Summit, right? And we called that for a few years.
Yeah.
Fundamentally, like everyone is going to tell you, the data is very important again, going back to, you believe that, obviously. So that's kind of the things, right? It's like the data, it's extremely important. You learn from the data, right? And actually, if you look, you're mentioning about the enterprises, the way they look at that, look these technologies about how is the same thing, how we are going to take advantage of the data we have, because each of them believes that the data is kind of their, what the value is, right? Because they have unique data about their products, about their customers, their own customers, and things like that. So how can I use that data, which is unique to me, to get more value, more than the competitors?
Yeah.
So everything does start with the data. But then when you talk about the analytics and so forth, you know that they are kind of, you have now for analytics, you have assistants, like you have a Databricks, you have Genie, right? And I think you are going to see much more and more fusing between
So
AI and data.
Final question, Ion. 5 years from now, 5 years from now, where do you think we are?
5 years.
5 years from now.
These are the kind of questions so you can only lose, right? Right, because you are going to be quoted maybe after 5 years. But that's basically, it's like maybe it's the best case scenario, because this means that people maybe still care about you. I think that 5 years from now, it's again, the easy one is like, we are, the transition we need to make today is about a lot, I was talking about reliability, it's about what I'm calling is like from the demo and production, right? The demos are always easy, right, as you know, because you need to find one particular kind of scenario, stories, which is really, really impressive. Now, when you go to production, that thing has to work not only in an impressive use case, it has to work in all the use cases, right? So that transition what is makes difficult, and you see that in everything you are doing. Like for instance, you write software, right? And how much time you spend in writing, a prototype for a particular feature, and how long it takes to put that feature in production, right?
Yep.
It's clearly, and with this AI, it's even much more difficult. Right?
Yep.
Because at least with the software, it's open box. You can debug it and so forth. You have tools, and you can say, oh, this is instruction, this is wrong. It should be, I don't know, a plus instead of a minus. You fix that, and it's going to work, right? But with large language model, our black box is much harder. So you should assume that the delta between the demo and the production will be much higher.
Pretty high.
So we are going to have to work for quite a bit. But as we are going to work, we are going to start using this things more and more as like, they are called assistants, right? Very powerful assistants. And it will, I think that as they are going to become more reliable, as you are going to trust more, and they are going to be far more effective, right? It's like, think about some intern, someone you are working with. It's like, let me, and why I'm saying about this reliability is so important. Let me ask you this one. Do you prefer to have a coworker or someone you depend on, right? Who is brilliant, but is not reliable? I mean, he's saying something he's doing, and it's not happening. Or someone, maybe he's not as brilliant, right? Solid, but he's absolutely reliable. Whenever she or he says he's doing something, he's done. You can forget about it. Think about that, right? Why would it be different in this case? So that's kind of journey. So I hope that in 5 years, you are going to have really kind of reliable AI systems, and it will do a lot of more work. It will do, quite a bit probably of my own research.
Excellent. Well, that's all we have the time for, Ion. Thank you so much for being here. Ion Stoica, ladies.
Please welcome to the stage Hussein Mahana from Meta.
Good morning. All right, let's just start with a quick show of hands and be honest about it. How many here spent at least 2 hours last night doom scrolling on their phone? I did. Now, While we were all watching those cute cat memes on our phones, here at Meta, we had a plethora of agents that are doing serious work, like submitting diffs, answering on-call pagers, and even answering thousands of questions. Metamate is the core of our agentic system here at Meta. And today I'll be taking you through the journey of how we evolved Metamate from a smart chatbot to a coworker that understands your work and actually helps you become productive. I'm Hussein, and I lead AI frontier systems here at Meta, and I'll be taking you through the technical challenges of this evolution. But before I do that, I first want to show you that Metamate has grown to be far more than just hype. All right. So more than 50% of Meta employees are actually daily active users of Metamate. So what does that mean? It means that tens of thousands of employees use Metamate every day. That's actually a very large number. And we think that this is probably one of the largest internally deployed chatbot systems in corporate America and perhaps in the world. There are hundreds of thousands of messages exchanged every week, and satisfaction is around 75%. Now, let me tell you this. Meta engineers do not give praise lightly, so this is a great result. In terms of what you can do with Metamate, there are a lot of workflows. One of the main ones is knowledge synthesis. So as an example, I personally suffer from document overload. I receive 10 new documents every day, and I just don't have time to read them. But with Metamate, I'm able to summarize them to very small paragraphs. And not only that, I actually ask Metamate to help me understand what are the next action steps that I need to do or my team needs to do. That's not all. In fact, Metamate is integrated into more than 50 internal tools at Meta. And those include calendaring, our pipeline definition system, our code diff system, etc. So this leads to saving millions of engineering hours every year, which has made Metamate a critical tool faster than any tool that I've seen at Meta. But with every great adoption story, there are some gnarly technical details. So time travel with me to understand the evolution of Metamate. So Metamate evolved in 5 stages. In the first stage, we used a raw LLM. And this raw LLM didn't really know much about our internal knowledge system or our code because it wasn't trained on it. So this takes us to the next stage. In the next stage, we fine-tuned the LLM on our code and our internal knowledge base. However, it suffered from hallucinations, and it often went out of date. So now, in the third stage, we augmented our LLM with a RAG system, which helped significantly ground our LLM outputs, therefore reducing hallucinations, and it also solved many of the out-of-date issues. And we started adding more integrations and tools, but we ran into more problems, which now brings us to the 4th stage. As we added more tools, we started suffering from our planner logic becoming brittle. And so we replaced it with a full LLM model-driven orchestrator. And we found that this actually made our system far more flexible, and it even made it smarter and more intelligent. And this brings us to the first important lesson of the evolution. So let's just talk a little bit about MDO. Prior to MDO, when we were adding more integrations, we were building an engineered planner/router. What that meant is we had a lot of if-else statements that we used to build this logic. Now, these if-else statements are quite soothing for engineers because it gives them more understanding of the control loop. But as we added more of these statements, it became very brittle, and it started breaking. And it became very hard to add something new. So now, when we replace this with an LLM that sits in the middle of the control loop, essentially what this LLM does is it predicts the next steps that the agent needs to take. And therefore, we no longer need to rely on those if-else statements, which we discovered are the new tech debt that you need to be wary of. Now, what are the benefits of having an LLM as your planner? Well, number one, now your planner is a generative learner, which means it can handle novel use cases that it hasn't seen before far better than a lot of these engineered planners which are static. Now, for anyone who's worked on planning, they would tell you that handling novel use cases is the Achilles heel of planners. And that's certainly my experience from working on autonomous vehicles. Now, there's additional advantages for MDO. So as an example, the MDO, or the planner, is operating in the same latent space as that is generating the answer, which means the planner and the executor are sharing weights and context, and that delivers better results. There's more and more benefits. I could talk all day, but I'm just going to go through a few more benefits quickly. As an example, reflective self-debugging. That's almost impossible to build efficiently with a static planner. Another additional benefit is emergent tool chain synthesis. Obviously, again, you have a generative planner here, so it definitely shines in that. Now, I just want to wrap this up. It turns out that we were experiencing the agentic version of the bidder lesson. Now, show of hands here. Who is familiar with the bidder lesson? Okay, just a few. So maybe I should give a quick intro to the bidder lesson. The bidder lesson is a great article that I really recommend you should read, written by Rich Sutton. In this article, he describes that many years of research were actually wasted on trying to engineer models to be smarter. Essentially, investing in making the model architecture smarter, better. But it turned out that the opposite investment, or the opposite approach, was far more effective. So LLMs have shown us that with a rather generic model architecture like transformers, but if you scale it with data and compute, you get far more improved results and higher accuracy. So on one hand, you're trying to engineer the model to be intelligent. On the other hand, you're just pumping more data and compute. The latter won. And that's essentially our experience when we replaced our engineered planner with model-driven orchestration. We found that this orchestrator will just get better with more data. And so this was our version of the agentic bidder lesson, which I suspect will occur in other forms of software. So MDO helped make our agents thinner. We had to write less code because we replaced it with a single prompt. It made them even smarter and more intelligent and more flexible, but it turns out that was still inefficient. And so now we enter stage 5. Now, before I get into stage 5, I want to describe the wall that you will hit when you use MCP, or the Model Context Protocol. It's a great protocol. We've heard about it. It acts as this universal plug-and-play that connects models to various other tools. It's fantastic. However, there are problems. Now, those who've used MCP and are familiar with building agents that call tools, you'll realize that the tool description that you provide to the model plays a big role. The model is super sensitive to that, to the extent that if you change one word, it can actually break the performance of the behavior. Now, here at Metamate, we have hundreds of tools. So this becomes unmanageable if we just change the description. Another problem you face is that, let's assume you're using a particular model, and then new releases come, even minor releases. It often breaks all the tools. So this has become a big problem for us, and we had to figure out a solution. It's not a problem in MCP itself, it's a problem in model iteration. So what is the solution? Well, 10 years ago, the problem for integration pain was to break down a monolith into microservices. We have used the equivalent, but for cognition. So instead of relying on one big agent, which is one model calling into hundreds of tools, we actually introduced this idea of sub-agent. A sub-agent is one tool, one prompt, one set of evals. We consider it the simplest form of deployed cognition. So the sub-agent effectively looks like a microservice. And we have found massive benefits to this approach. So as an example, it offered us modularity. And modularity meant speed, because now new tools or skills can be registered with the agent instead of being added. Moreover, it actually gave us the ability to A/B test skills. So let's say I have a particular sub-agent for calendaring, and either the model changed, or let's say the calendaring tool has changes. I could A/B test those changes in isolation without affecting the rest of the finance, the HR, or the other agents. And then another great benefit is fault tolerance. Just like microservices provided state fault tolerance, sub-agents provide knowledge fault tolerance. So if a sub-agent is suffering from hallucination for some reason, you don't know why, you could roll it back or you could pull it down just as you would do with API endpoints. Frankly, I used to think multi-agent systems was just hype. You know, you hear about agent societies, agent chatter, and I'm like, why are we complicating this? This just seems like people taking it to the extreme. But now, with sub-agents, we've realized they're super important for deployment. In fact, we just can't imagine how we could ship without them. All right, so enough slides. Let's just start looking at some real use cases of Metamate. Now, in a big company like Meta, we have a lot of great people doing a lot of great work, and sometimes it's hard to find who's doing what. You could easily spend half a day trying to figure out the POC for a particular project. But with Metamate, this is easy peasy. So we asked Metamate, who is the best engineering contact to help us understand sort of our relationship with Google Drive. At Meta, we use Google Drive. And in a few seconds, Metamate was able to leverage MDO to orchestrate between multiple agents, agents that access our knowledge base, agents that summarized the relevant information, agents that used our people database to do a lookup, and gave us a very succinct answer in a few seconds. Here's a different example. So Metamate can access, as I mentioned, multiple sources of information, and you can give it very specific instructions to manipulate the data that it retrieves. So in this case, we asked Metamate to access the feedback group for Metamate itself, figure out the posts that received the most engagement, because that's an indication of potentially the topmost issues, and then summarize it for us with very clear instructions, including links, etc. You can imagine that this is a task a human being could have just wasted half a day doing, reading through countless posts and summarizing information in a spreadsheet. But thanks to Metamate, this was delivered in a few seconds. Now, this example is my most favorite. This is actually a task that you ask from data scientists or even data analysts. So we asked Metamate to help us calculate the daily active user rate for one of Meta's products called Threads. And Metamate did a fantastic job. Again, this is a great example of MDO. So you need multiple agents. First, you need to understand what Threads is. Second, you need to go to a particular database and understand the schema. That's another agent. Third, you need to construct a query. That's a third agent. And then fourth, you need to run it. And Metamate did all of that in a perfectly orchestrated manner. We've never hard-coded this orchestration. And then we asked it, like, hey, go chart it in a real-time series chart. So it actually launched another agent to run the query, then another agent to gather the data, and then finally chart it. I'm not going to show you the chart here because that's confidential, but you can trust me that it produced a very beautiful chart. All right, here's my last example. I think after the pandemic, we're all living on chat systems now. I mean, half of my work is done through a chat system, and I'm pretty sure a lot of you would engage in a thread, and then you get busy or have lunch, come back, and find that thread with like 100 extra new messages. There's no time to read that. Now, with Metamate, I could tell it, go to this thread, summarize it, and just give me the next action steps. And you know what? Maybe it's time for these people to get into a face-to-face meeting. So I actually asked Metamate, go set up a meeting for all the people that are relevant. It didn't just pick up the relevant people from the participants in the chat thread. It actually figured out from the context that there's some additional participants. And again, this is a great example of MDO. Like, as you can see, this is multiple tasks that need to be orchestrated, accessing our chat system, summarizing the thread, creating a calendar invite, figuring out the participants. And all of that was done with a click of a button. All right, I need to wrap up. So Metamate, we're going to continue developing it. We're going to add more tools to it. No, that's wrong. We're going to add more sub-agents. That's what we're going to do to it. And it's going to become multimodal. But frankly, I think the biggest opportunity for Metamate in the near future is to help Meta employees build evals. This is where software engineering is going. It's no longer going to be about writing code or even vibe coding. It's going to be more about providing the system with an evaluation set for what you want to achieve. And then the system will go build the software that satisfies this evaluation. Now, for those who are involved with building evals, know it's very hard. It's not easy, it's not straightforward. And luckily today, my colleague Shishir will take you through how to build evals and some of these challenges. And I believe that Metamate's biggest opportunity is to coach employees on how to build comprehensive evals as quickly as possible. All right, so Metamate started as a chatbot. Actually, it was an idea started by Aparna. It started as a chatbot. It evolved into becoming a coworker. And in the future, it's going to coach Meta employees to build evals. And I'm so excited about building this future together with my peers at Meta. Thank you very much.
Please welcome to the stage Jeff Holland from Snowflake.
Good morning, everybody. I am so excited to be here, and I want to start with a question for everyone here, which is, what is one of the main things that is holding back enterprises from being able to take full advantage of agents? Now, as my job at Snowflake as a product manager, I have had a chance over the last few months to truthfully talk to hundreds of different enterprises and understanding of what they're doing with AI and agents. And a lot of what I want to share today, I actually love the talks that have gone ahead because they've touched on many of the same topics. The topics of the importance of data, the topics of being able to break down tasks even into sub-agents. So I want to share some of what I found and some of the technical tricks that we have found working in Snowflake to try to make this more real for agents and enterprise, for the broader community. So I'll start with something that, again, has been a theme already for the morning, which is that AI agents have a huge potential to truthfully transform the enterprise and how work is done. And I think there's a few reasons for this. One of them is the ability to just increase productivity for the amount of output that an employee is able to do. I think about, from time to time, I'll go write a little bit of code, build simple little apps. Having things like AI agents help me in software development, I'm able to build things in a fraction of the time of what it took before. I get really excited about the notion of having things autonomously done for me as well, especially more mundane tasks. We've seen that there's a lot of appetite for users to be able to say, hey, this kind of busy work stuff, I would love to be able to hand that off to an agent. A huge area that I predict we're going to see a massive growth around agents is actually going to come around systems integration. If you think of any enterprise, any large company, there are dozens and dozens, sometimes hundreds of different systems. Systems for HR, systems for sales, system for finance, system for support. And there's whole industries built on just making it so system A can talk to system B. But with something as adaptable and powerful as an agent, this notion of being able to have your systems be able to interact with each other is going to be incredibly powerful. Now, with that said, across all of this, though, is the notion that you need the right context to be able for the agent to perform its task. If I'm working in marketing and I need to go launch a new marketing campaign, there is specific context that I need to be able to perform that task as a human. I need to understand who are the customers that I'm targeting, what are some aspects about them that I need to understand. So being able to surface the right context to these agents is a critical component to making these agents real. Now that said, oftentimes in the world of LLM and agents, we focus so heavily on what I call unstructured data. Documents, messages, emails, calendars. There's so many different agentic offerings that focus on this retrieval augmented generation, or RAG, right? How do I make it so that when I ask a question that we can search across all of the documents? And that's good. It's an important piece of context. But there is a ton of context in enterprises that does not live in PDF documents in Google Drive or SharePoint, that lives in databases as structured data in tables and rows and columns. And again, if you've looked at any enterprise of any meaningful scale, this is messy as well. This data is often scattered across many different tables with complex column names. There's overlap of the data. But to make something powerful that actually understands the business, you need to be able to surface that structured data as well. Because how am I going to, again, if I use that marketing example, go successfully target my marketing campaign if I can't access all the details about who my customers are and what their behaviors are that's in that structured data? Now, this sounds, hopefully, pretty understandable. One of the things that we have learned as we've been on this journey is that building a demo or a prototype to be able to access structured data is actually pretty easy. All of us right now, you could open your phone, you could go to ChatGPT or Meta AI or whatever you want to do and say, write for me a SQL query that gives me the top customers for a table that kind of looks like this. And it will write for you really good SQL. But what we've seen through working with a few customers is that getting that to work with real enterprise data in an accurate way is very, very, very difficult. Because again, the data is massive, it's messy, it's not well organized, and accuracy is super critical. So for the next few minutes, I just want to identify 4 different problems that we've identified and what it takes to generate high valuable structured data context for an AI system, some of the solutions and strategies that we've been employing, because we're interested in working together with the community to figure out how we can bring better some of the structured data insights into the story of AI agents. So first off, and I love the previous talk where we talked about sub-agents. We found actually very similar findings that breaking this down into different sub-agents or sub-tasks is incredibly powerful. So my main agent may just have the tool, I need to go access structured data, but we behind the scenes have built this ensemble of agents to actually go break this down into smaller pieces. So something as simple as write for me the SQL to generate this query, we've broken down into many, many different steps to get to the eventual outcome. So I want to highlight, as I said, a few of these pieces here in how we've started to do this. Now, one of the things that we've observed is whether an agent is generating the question or a human is generating the question, that context may often be missing when you're going through this process. So for instance, I might ask, let's say a conversational agent, or an agent might ask another agent, how many customers did we get in the US? Now, all of us in this room probably look at that and we're able to infer, well, US probably means United States. But think about the data that might be on the other side of this, my customers table. If I have a column called like location, is it going to have a value of US? Is it going to say USA? Is it going to say region A? Like, what is that actually going to look like? So there needs to be some context or mapping between different terms and terminology and what the actual data representation would be. Similarly, there's often terminology or acronyms that are used. If any of you have worked in finance, you're probably very familiar with the term ARR, annualized run rate. But again, if I go to just a general schema generating aspect and I say, what is the current ARR? Does it understand how ARR maps to the representation of the data? So a key piece in this orchestration of sub-agents that we've used to generate SQL, we found that providing an additional semantic view or a semantic model of the data really boosts the quality of the results that you're able to surface back to the underlying agent. Now, I want to clarify here too, when I say model, I don't mean like a machine learning model. This is more like a data model. It's literally how we've started to deploy this is a text file. It's a representation. It's my map. It's how I say, this is what the data actually looks like. I have my table called customer_V2, and it has these business terminologies that might map to it, ARR, region, you name it. Can I describe some of those relationships so that when I go to generate the SQL, I'm able to map specific business context and business relationships back to the underlying data. So having that view, that semantic view, to help onboard the agent and help it understand the data is incredibly powerful. And without it, you get much less quality of results when you're trying to generate that structured data. Now, the other problem that we faced is that questions can often be ambiguous. So a user might come into a conversational experience, and they'll say something like, what is the best performing product in the last 6 months? I'll use one example. In fact, I'll probably show them a little bit later. One of the customers I've been able to work with over the last few months is a company called Whoop. Some of you might be familiar with their products. They're based out of Boston. They build health wearables. These are wearables you wear like 24/7. They monitor everything from your stress to your exercise to your sleep. And their team wanted to better understand, how can we help in our product development, in our marketing? How can we use agents to do more of these things? And this would be a common question that somebody like Whoop might ask, right? Like, what are the best products that we're doing? But again, there's a lot of ambiguity here. What do I mean when I say best? Do I mean best in that it sold the biggest number of units? Do I mean best in that it generated the most profit for the company? Do I mean best in terms of it had the least amount of defects, it had the highest quality? So there's some ambiguity there, and depending on what I might mean, it might mean that I need to access a slightly different set of data behind the scenes to answer the question. So actually, the very first step that we do in our processing before we understand how to generate the right structured data to help give context to a question is we do a quick classification to understand, is this question ambiguous? Does this require clarification? And in that case, we'll instruct the agent, you need to go clarify with the user. Go ask Jeff what he means when he says best. Here's some options of what it might mean. So by having that kind of catch at the beginning, we're able to fix what often would happen on the other side is the agent would decide some form of what it thinks it might mean by best, but that often didn't map what the user wanted, and it could mean that you're surfacing the wrong context to the agent to answer those questions. Now, this is an interesting one that surprised me a little bit as the team was coming across it, which was that we found that the accuracy of actually being able to write a really, really good SQL query, for example, could be negatively impacted just by some of the technical terminology of what data schemas look like. So I have a screenshot here of like what is a normal looking SQL query for an organization. And so it has here some column names. You can see there's like cust_f name. There's txn_ord_details_us, right? This is pretty normal looking. It's a little bit messy. It's a little bit complex. But what was interesting is if you think about this as like the physical representation of the data, this is what the actual strings, the column names, whatever else are used, that I need my LLM, I need my agent to be able to generate. It would get confused by all these weird sounding terms and underscores or whatever else. At least I think of it as confusing. I'm kind of adding personality maybe to this LLM. But we could get higher accuracy, higher quality if we, again, broke down one more step in this process. So before we ask our LLM to actually go generate the SQL, we first create a logical representation of the schema paired with that semantic view that I talked about before. So for instance, if I have here, customers and orders and products, maybe the actual data is called cust_f name, but in this logical layer, we'll just call it first name or last name or address or order amount or order date. We'll do a subset of the schema that is required, and we'll create terminology that's a little bit more natural. And we found that by creating this logical layer, we would improve the accuracy. So we have it generate the SQL query based on this logical layer, and then we map it back to the physical layer to end up with the SQL that looks a little bit more like on the left side of this slide. So again, we kind of break down. And the way I think about this whole process is, if I go ask a human being, if I go to my data science team, and I say, can you go write for me the query of how many whatever products we sold in the last 6 months? In their minds, they're probably doing a lot of things at once. They're thinking of what is the right tables that I need to look at? What are the columns that I need to use? What's the right patterns? In our process of generating high-quality SQL, we've tried to break many of these pieces into sub-steps. into individual components so that we can improve them, but also we're not asking the LLM to do everything all at once. Because when you ask it to do everything all at once, again, that quality takes a little bit of a dive. So the last problem I want to share a little bit here is, again, one more of the steps that happens is understanding the right pattern that is being asked in the context that needs to be provided. So for those of you who've worked with data, you know that there's a few common patterns when you're writing SQL queries. There's things like time series analysis. There's things like ranking analysis. There's different characteristics, and depending on what I'm looking for, I'm going to follow different patterns, right? I know if I'm doing a time series, I need to group by some time date, and I need to, probably bucket it into time windows. So again, we just broke this up into another step. We wanted to understand, okay, before we actually go ask the model to go generate the actual syntax needed for that context, let's just identify and classify what is the type of query needed here. So for instance, it will take a question, show me daily sales trends for the last quarter, and it will identify just the single step. Its only job is to say, oh, that's a time series query. To be able to ask her a sales trend over the last quarter, I'm going to do that as a time series query. And then we include that feature along with that semantic view, the logical layer, all those different pieces, and that's what we end up giving. So now when the actual thing is generating the SQL queries, it's able to not have to figure out what's the type of query. It knows generate a time series query based on this question. So again, if you think back, this was the slide I started with. Something as simple as write for me really, really good SQL, we've broken it down into all of these different little steps. And we do these steps very, very, very quickly. At least for the offerings and some of the products we bake this into at Snowflake. So we'll very quickly classify, we'll then extract what's the type of query needed, we'll enrich it with that semantic view, we'll then generate a few different SQL statements, we'll check them for errors, we'll correct the errors, we'll synthesize full results, and then finally we'll return back the SQL query. All of this work, all of this effort, and it's almost comical, how many hours and blood, sweat, and tears have been shed to try to get really, really high accurate context. But it's something that we found is incredibly important because, again, if I'm thinking about what does it take for agents to take hold in the enterprise, if you cannot accurately surface all of this structured data, all of this data that's in messy databases or scattered across data sources, your agent's going to be encumbered by only the data that's representative through that unstructured RAG-style data. So I'll show this again. I mentioned at the beginning we've been working some with Whoop. So Whoop has been working with us on building agents that can help them, as I mentioned, in some of their product development cycles. I'll just show here this quick little video of this is the agentic experience that they've now built. So they're asking a question like, how is sales in the last 2 weeks? And you'll notice it went pretty fast. I think this video will loop. Like right away, based on that question, what were sales like in the last 2 weeks? The agent's able to go and generate just the precise SQL needed using that entire ensemble of agents to go generate the pieces. Based on that, the agent can use that context. Now it has the context of the structured data in addition to the unstructured data. And then a few seconds later, if I was looking at Whoop, I would get my answer. This is demo data. This isn't actually Whoop's data. But it's doing the same flow that they're using as a company. And now I can get back a visualization based on some of that structured data. So this is how this all kind of came together so that now their agents are able to pull from highly accurate structured data, in their case running inside of Snowflake. Now, kind of in closing, as I think about what I'm starting to observe in this world of data, and I've really loved how already this morning there's been this heavy emphasis on data. It's a really important piece of the AI future. I think there's a few data adjacent things that I predict are going to be coming up here in the next few months or years. I would say years, but things are moving so fast right now, maybe it's just going to be months. The first one is if you think how employees and systems generally interact with data today, it's often indirectly through something like a dashboard or BI. I think we're starting to see this emergence of this new agentic style intelligence or generative BI, where even I personally feel when I have an answer to, or when I have a question that I want answered, do I really want to be digging through a dashboard and trying to find the right charts to answer my question? I'd rather just have the answer given to me in the same way that when I have a question and I go to ChatGPT, it just gives me the answer right away. Now, the other thing that I'm starting to see bubble up, and I think is going to be really important over the next few years, is this notion of understanding the organization and the concepts unique to the business in order to deliver agentic experiences. So beyond just the technology, the powerful models, the powerful tools, MCP, all these other things, I predict that the leading enterprise agents, the agents that you're going to see make the most adoption, are going to be the ones that are able to pull some understanding of the business relationships in addition to the actual context and technologies. The organizational structure, the unique business terminology, the processes required for a business. Think about joining any company and you go to the onboarding. How much of your onboarding is learning about your job and how much of your onboarding is learning about the company? This is the org structure. This is the process. These are those pieces, right? It's usually about half and half. I think that's an important element for agents in the enterprise is they need to understand the nuance of the business. So as agents are able to pull from that, either from existing systems or additional context that they're able to generate, those ones are going to be so much faster to be able to go into motion in the same way that if you hired an employee but they didn't understand the business context of how your team worked, they would struggle to be productive. Now, the other interesting trend that I'm seeing, kind of to wrap things up, is if you've worked in any enterprise, you're likely familiar with the term system of record, right? For any major operation, you usually have a system of record. Hey, for our revenue data, this is our systems of record. This is our source of truth. And those systems of record are incredibly important. They need to be managed incredibly carefully. Now, I think what's starting to emerge, and I can't take credit for this idea. I heard this from an analyst that I really resonate with this idea, is that if you think about these systems of record on the bottom layer, we're starting to see this emergence of these systems of intelligence that live, in my mind, as like this flowing layer on top of those systems of record. And I expect that as those systems of intelligence get established in organizations, far more will developers and other systems be not targeting to pull directly from the systems of record, but targeting those systems of intelligence because they're so much more adaptable, they're so much more easy to communicate, there's so much more specific development that needs to happen if you can go operate on that intelligence layer. But again, all of this I think is going to require that these agents and AI pieces are going to be able to blend together this combination of not just the RAG style unstructured data, but context that can be pulled from, or from unstructured data, but context from structured data as well. So hopefully this was helpful and wanted to share some of the practices that we've learned through AI research at Snowflake. If you have any questions, if you have any comments or things, feel free to reach out to me on social, on Twitter, X at Jeff Holland, or on LinkedIn. And thank you all so much for joining today. It's been a privilege to be able to spend some time with you all this morning. Thank you so much.
Please welcome to the stage Shashir Patil from Meta.
All right. Hello and good morning, everyone. My name is Shashir Patil, and I finished my PhD from Berkeley working with Ion, actually, whom you heard from this morning. And I'm now a research scientist on the Llama team at Meta. And today I'm very excited to bring you some of the research both from academia and what we have been doing at Meta on agents and agentic evaluation. So to begin, what I want to do is actually take a step and think about agents more functionally, right? What does agents mean for you and I as researchers, developers, and consumers? And the way I like to think about this is I have quite a few LLMs on the left-hand side. You might identify your favorite. I've shown you as the user at the center of it, and all the digital services on the right-hand side. So these digital services would include, for example, coding that Hussein presented with Metamate, or some of the other applications that you heard from Jeff just before me. Now, the way you interact with LLMs today is you prompt the LLM, you get a response. And I've shown this as single-shot interaction, but you can think of this as multiple back and forths with the LLM from your favorite interface. But it's then fundamentally up to you as the user to then take this information that the LLM gives you and perform an action on the digital world and observe a response. Right? This is the interface that LLMs pioneered. Now, with agents, our goal is, can we flip this around? Right? So can we have a scenario where we introduce agentic LLMs that sit in between you and the digital world to perform the task on your behalf? So here you would prompt the agent, and now the agent would perform an action on the world, observe the response, and then relay the response back to you as the user. Now, why do we want to do this? Well, this is based on these observations that humans are good at distinguishing, whereas LLMs are good at generating. Now, let me explain this with an example, right? So I was sitting in the green room listening to all the talks, and there are two types of coffees over there. Even though they had the exact beans listed on both the pots of the coffee, if you were to ask me which one would you prefer, it's very hard for me to just look at the beans and then recognize which coffee I would like better. On the other hand, if I can have a sip from each of the coffee, I can very quickly tell you which one I like better, right? So humans are good at distinguishing, and the LLMs themselves are very good at generating. So let LLMs do the generation, and agentic LLMs will help you do this, and we as humans can do the distinguishing, right? So that's the premise over here, and this is the functional view of agentic LLMs. Now, this is a little too abstract. I do recognize it. So let me ground it in one example, right? So as ML researchers, one thing that we always want is GPUs. So suppose a user came in and said, hey, can I get an 800 GPU in East US? Now, there's 3 things we want the agent to do. The first is reasoning and planning. East US is how some hyperscalers name their region, so we want the LLM to recognize which hyperscaler I may be referring to. Second, as retail consumers, oftentimes there are quotas. There are only so many instances you can launch at any given point in time. So you're reading the state of the world. You're going to your hyperscaler and requesting, all right, what's my capacity? How many GPUs can I spin up? And the third, once you have done reasoning and once you have done observing, is actually performing the action. So you want to then spin up the GPU instance and pass on the artifact back to the user, which in this case could be a terminal session from which the user can access their GPU instance. Right? So this is one example which an agentic LLM could enable from just purely thinking from a functional perspective. Now, you're, I'm sure, exposed to multiple definitions of agents. Almost every talk seems to have one, so let me give you my own. So I would like to, the way we think about this is define agents as fundamentally consisting of 3 independent components, right? The first is the LLM model, of course, the brain of the agent. The second is the framework that then orchestrates the agent with all the different tools. And you can start seeing how, with this definition, you can actually fit in a bunch of different agents. And what this also does is gives us a very handy framework to then think about evaluation. For example, I want to begin by thinking about, well, how do we evaluate LLM models for agentic tasks? And there's one research that I would like to present, which looks at how do we evaluate function calling for LLMs. Now, for agentic LLMs, function calling becomes the working horse, wherein you basically want the LLM to have the capacity to invoke well-defined, structurally accurate function calls to then interact with the rest of your services. All right? There's 2 ways you can do this. The first way is to have complete end-to-end evaluation, and we'll get to that later. But you can see the challenges of having end-to-end evaluation because it's not scalable. You tend to have a lot of confounding factors. You don't get repetitiveness. So you would want a way where you can concretely evaluate the LLM on just function calling. And one research idea that I want to present to you is borrowing this concept from programming languages literature, where we use abstract syntax trees to now evaluate an LLM on function calling in an offline scenario. Offline means you can let your engineers and model developers train multiple LLMs, evaluate all of them, without having to actually invoke the service. So how do we do this? Well, the idea is simple. On the left-hand side, I have shown an function call from an LLM. This is Pythonic. You could think of RESTful API calls, SQL, so on and so forth. The first thing that we try to do is we try and build a subtree out of the function call. Next, we look at all the function calls that a given service exposes to you. And then we ask a simple question, is the LLM generation a proper subtree of the set of all functions that you can invoke? And if the answer is yes, then you have a very robust offline way to evaluate function calls without actually calling it. Now, obviously, the devil is in the details, right? There's a lot of very intricate things here to take care of. For example, the model name. You might want to have an exact string match. Sometimes you might have arguments that are range queries that can have a value that you look for a range. And in this particular example, with the Pythonic function call, some arguments may be optional arguments, so then you may not want to check for it. Now, one question that I suspect many of you might have is, well, who's going to build the tree on the right? Unlike many other scenarios, with function calls, one thing to keep in mind is that the incentives are very well aligned, right? So when you go to PyTorch or when you go to Stripe, there's an incentive for all these providers to enable functions that your LLMs can call. So they go to great depths to make these functions and APIs available to you in very easily accessible formats like OpenAPI, spec, Swagger files, so on and so forth. Right? So this is one way how you can use abstract syntax trees as a concept to evaluate function calling. Now, there is a leaderboard called the Berkeley Function Calling Leaderboard that basically does this, right? So they look at all the different LLMs, they look at different categories like single-turn function call, multi-turn function call, so on and so forth, to then help you understand how well do different LLMs perform on function calling, where do they fall short, where else can you improve, so on and so forth. All right, so that was good. We looked at how do we evaluate LLMs for function calling. Now let's zoom out a little bit and think about, is there a way where we can evaluate agents as a whole in the different tasks that you have? Now, one very exciting example of a complete agentic system is MLGem. Published just a few months ago from Meta and our collaborators, MLGem is a framework, a unified framework that enables researchers to very easily implement and experiment with different training algorithms for LLM agents. MLGem consists of two components, the GEM environment, and the second is ML Bench, which is a benchmark for evaluating agents. All right, so let's look at the ML GEM, and you can quickly start to see how you can slot all these different components into the handy ML agent definition that we had before. So you have the prompts, the model, et cetera, that fits into the LLM category. And then you have the environment that now orchestrates the LLM model with all the different tools that's available to it. And tools here would include a shell, a terminal from which you can access your computer, and different function calls to now open coding files, edit coding files, just submit jobs to run, so on and so forth. Right? And then ML GEM Bench is a benchmark that actually tests an LLM agent on different ML capabilities. So this includes computer vision, natural language processing, reinforcement learning, game theory, so on and so forth. Now, what ML Bench does is not just tests an LLM's ability to, say, code up a small piece, but it's actually very holistic development, right? So it evaluates the LLM on its ability to solve these tasks. This includes downloading data sets, creating and processing data, implementing ML methods, training models, evaluating them, and then submitting these models when you're done training. All right, so I just spoke to you in very briefly about ML GEM and ML GEM Bench. How useful is it, or how do we use these evaluation frameworks? So let me just present one key observation, which I think is very interesting in how you can use these frameworks to now evaluate your agents. All right, so what do we have here? On the left-hand side, on the x-axis, you have different steps. So you go from the first turn, starting at 0, to the 50th turn. So these are different assistant and agent interactions. And on the y-axis, you have a simple count, right? So we are trying to plot how often are multiple tools called in each step. And you can start seeing very interesting observations, right? So for example, in this particular scenario, very early on, the model is mostly viewing, which is looking at different files, and using your shell to learn your directory structure. So it's trying to understand, well, how is your code base structured? What are the different components that's there? And as you move towards the very end, you'll see that the discovery part reduces. And now most of the time, your agent is spending in editing the files and performing tasks, right? So, if you have different tasks where you want to tune this, if you have different tasks where you feel like, well, the agent is not really performing more discovery or more actions, you could use frameworks like this to now understand, pinpoint exactly what the problem is, and then nail it. All right? So we looked at agents with this handy definition. We looked at two ways to evaluate them. One is the LLM itself, and the second is to zoom out and evaluate agents as a whole. And hopefully, both of this gives you a very handy framework to now go ahead and think about how do we build and evaluate agents. Now at Meta, obviously, we have been trying to help you along this journey, right? So almost a year ago, we launched the Llama 3 series of models, and the Llama herd has had several upgrades since then. We had the 8B model that was ultra-fast option that could be run by anyone. And then you had the flagship 405B model that really helped you with generating synthetic data, helped with distillation, so on and so forth. Then the Llama 1B and 3B small models opened up a new avenues for you to run inference. So you could run inference on your local desktops, on your smartphones, so on and so forth. And then the Llama 11B and the 90B were truly multimodal models, and the first to now help you with multimodal agentic tasks. And finally, with Llama 4, we introduced natively multimodal models, and these are a mixture of experts, Scout with 16 experts, and Maverick with 128 experts. Now, these offer strong performance on multilingual, long context, and image reasoning tasks. So on the model side, there's quite a few options for you to pick and choose that helps you with your tasks. And we're also trying to build a framework that helps you now build on these llamas. So we're trying to build the llama stack. And the goal for the team with llama stack is simple. Can we make it easy for everyone to build on top of llamas, to build agents on top of llamas? So in doing so, there's 3 different axes we want to take care of, right? The first is, can we build this so that it's compatible with all the different models that we have with varying capabilities? Second, we want to also support the breadth of different tasks that developers need when you build on top of llama models. So this could include inference, safety, fine-tuning, of course, evaluations as well. And finally, we want to enable that you can run the llama stack on all the different environments. So you can think of running it with local inference, your own self-hosted inference, or hosted inference from our third-party vendors. You heard from Jeff just a few minutes ago. Of course, we have been listening, and telemetry and state and resource management is also very critical. So we want to call this out as first-class citizens. So if you were to build with llama stack, the way you think about this is, as developers, you would expose your client SDKs, CLIs, and user interfaces to your users. And then you'd rely on package distributions for inference. And then right at the center of it would sit llama stack, which would help you maintain and build and tune all the different capabilities. So that's llama stack. Now, I want to spend a few minutes just sharing some of my own personal learnings when you work with agents and agentic evaluation. So this is not to be considered official meta recommendation of any sort, but these are just my own personal learnings. First, optimizing for agentic benchmarks is very tricky, right? So if you remember Hussein's fantastic example, you could see that the agent had to do multiple things. It had to do tool calling, it had to do RAG, and it had to do orchestration and planning, and finally, doing the actual call, and then presenting the results in a very nice fashion to the users. And what I've often found is when you start from here, it becomes very hard to then try and optimize agents for their capabilities. This may sound very trivial, but the best case continues to be to start simple, right? So an agent includes multiple capabilities, like a SWE agent includes coding, instruction following, long context, right? What I would recommend is, in most scenarios, try to freeze all the different variables. So for example, for SWE agent, I would freeze instruction following and long context in terms of just evaluation, and then try to optimize for just the coding aspect of it. Right, you start looking at just the coding evals. And once you do that, then you can try and understand, well, OK, now that I unfreeze one of it, how does it interface and interact with all the different capabilities, like instruction following and long context, and then build on top of it. Right? So just trying to break it down into individual components, wherein you understand what are the individual components that help you build your agents. Well, OK, you're trying to build something that has to interact with the rest of your services. OK, can I isolate out just tool calling, and then instruction following, and then building on top of it, is, I think, super helpful. Second, and this may come as a surprise to many of you, determining when an agent has finished is super hard, right? In the ML gym bench example that I gave you, this was one of our key challenges, is just understanding when an agent has finished. If you play with all the different LLMs, some agents tend to submit a solution super early. Some agents tend to take forever, not recognizing that they've gone off rails and knowing when to stop. And this is actually a pretty open research problem, right? You can think of very simple to innovative ideas. A simple idea would be, well, can I just prompt the LLM and let it know when it finishes? And on the more extreme end, you can think of masking your log probabilities for LLM inference to try and understand when you want the end of sequence token, so on and so forth. I'll not go into too much details, but I would encourage you to think about this as you start building and evaluating agentic LLMs. And finally, agents can be extremely effective when personalized. Right? So if you think about evaluation for the agents that you're building, also try to bake in how can you incorporate some of the personalization aspect of it, which has a significant impact on how well your agents are perceived to perform when you deploy them. All right, well, so that's a little bit of looking today. I also want to take the last couple of minutes looking a little bit into the future, right? So where are we going with this? And it should come as no surprise that the holy grail, in some sense, is autonomous agents, right? Can we build and evaluate autonomous agentic systems? Well, what does this mean? Going back to our very handy functional description, we said, well, the user sits at the center today with LLMs. The benefit of this, in some sense, is you can verify the process. When an LLM tells you, well, here's how you do something, you can actually look at it, verify before you perform the action. We said, let's flip this around, and we introduced an agent where the users are now verifying the output. Fantastic. You've made my life easy. But you can still see the problem here, right? Which is, we will end up being the bottleneck. If a user has to verify every single agentic output, then you cannot scale faster than the ability for us to scale our decision making. So a truly autonomous agentic system is one where you have multiple different agents interacting with each other, and then the users, on the other hand, have two properties. One, we have punctuated attendance. What this means is maybe once a day, once an hour, define your granularity of time. You can go in and then observe from the very top what's going on, how is the agent performing. And second, you want to ensure that your users are looking most of their time on downstream results and not the intermediate process. So the sort of high-level understanding here is, if you enable agentic systems where the agents can operate independently, whereas you give the tools to the users, this could be, what does this mean? Does this mean that all the agents have to be associative, have to have an undo feature, so on and so forth? So if you can now expose vocabulary and have strong restrictions on what an agent can do or cannot do, then you can truly enable autonomous agentic systems where the users can now step back and very routinely check in and then only look at the end output, thereby letting you scale agentic systems, scale agentic operations, so on and so forth. All right, fantastic. So what did we do? Today we looked at three things, right? The first was sort of a functional description of how you can look at agents as consisting of three different things. And then once you do this, you can now break this down into evaluations where you look at individual evaluations of each component. And then we looked at ML Gym Bench as a way to evaluate all of them together as an agent as a whole. And finally, as you start building these agents, also think about what does a future of autonomous agents look like, and how do you build systems and services that are robust and can scale well in this autonomous agentic future. Thank you, and I'm happy to take questions later on.
Please welcome to the stage Cyril Morian and Devin O'Kelly from NVIDIA.
Have you ever experienced a numeric explosion when training a model? A NaN, the infamous not a number error. Well, a lot of AI engineers have, and they're very horrible errors. They tend to kill your entire training job. Now, imagine if this happened in an AV or some mission-critical app. You may literally hit a wall, and that would be catastrophic. Most of these errors are caused actually by unstable models and corrupted training data. For example, FP8 and other small floating point formats, which are very popular these days, tend to overflow very easily, and they require special attention. We have similar issues with corrupted training data. But sometimes the cause for the explosion is elsewhere. It's actually a hardware fault. These faults are called silent data corruptions, or SDC in short. By the way, my name is Cyril, and I'm an engineer at NVIDIA. Today, my colleague David and I will talk to you about these silent hardware errors, what we've learned about them, and how they can be mitigated. Let's start with a short history lesson.
So SDCs are not a new problem, right? Data corruption in general has been around for thousands of years, going back to the first time an abacus lost a bead, right? And so that has been a persistent threat throughout the entire history of computing. But once we've had electronic computers, we've really contended with them in a lot of engineering-based ways. So your error-correcting memory or radiation-hardened components that sent us to the moon. But in recent years, with the advent of AI and larger-scale training, there are a lot more places for SDCs to show up. So nowadays, we have data centers that have 100,000 GPUs in them. We have, a B200 has 200 billion transistors in it and runs 20 petaflops of compute, so 20 million billion floating point operations every single second. So this intersection of density and scale and size all gives us a lot of opportunity to find SDCs, but the possible consequences of them are also growing a lot more diverse as we have autonomous vehicles, LLMs, and agents and sub-agents, enriching our lives in a lot of diverse different ways. But SDCs are unusually challenging to contend with because they are relatively rare and pretty hard to catch. So as the name implies, silent data corruptions are mostly silent. Most of them don't have an effect downstream. But even though this is benign, this is somewhat of a problem because this makes it challenging for us to know just how widespread the problem actually is. But some do fall through the cracks. Some might have a small perturbative effect, just tweaking the math a little bit. Others might lead to the sort of catastrophic numeric explosion that Cyril was mentioning. About 1% of SDCs, through some modeling, lead to these sort of numeric explosions, but in the current state of research, we actually understand very little about SDCs, what causes them, and their possible downstream effects. Part of this is born out of the fact that SDCs are very stochastic and complex. They're rooted in the quantum mechanics and rich architecture of a GPU. But this leads most industry studies to have to approach this from a black box perspective, the outside in. At NVIDIA, we've made a couple of GPUs in our time, and so we have a lot of insight into the sort of things that cause SDCs and have a lot of approaches for tackling this end to end to help out the rest of the industry. So we're going to walk through the journey of an SDC, starting off at the basal layers of the quantum mechanics, going up through the chip architecture, and finally landing on in the AI model itself. Cyril?
Right. Thanks, David. Let's embark on the journey. It all starts with quantum physics. So transistors are the basic building blocks of all chips. They carry and process elementary bit information. At a very basic level, actually, transistors are quantum physics devices. We're not talking about quantum computing here. However, at the scale of today's transistor, they are subject to quantum effects, and certain probabilistic behaviors become significant. What that means is that they are vulnerable to certain perturbations to their environment, such as cosmic rays and changes in voltage and temperature. When that happens, the transistor may respond more slowly or may become temporarily unstable, jumping back and forth between the open and closed state. All right. So we distinguish between two broad categories of SDCs. There are transient SDCs, which are random, isolated errors caused by strikes of high-energy particles, such as cosmic rays. And then there are permanent SDCs, which are repeating or intermittent errors caused by a variety of factors, including aging and changes in voltage. Right. All of this is highly non-deterministic. All right, so moving up to the next layer of the stack. Transistors are combined into large and complex structures to implement GPU functions. That includes register files, the ALUs, tensor cores, and so forth. The question is, how vulnerable are those functions to faulty transistors? Well, it depends on multiple complex factors, including the exact timing and site of a faulty transistor. Many faulty bits are actually not tracked by downstream logic and end up vanishing without a trace. However, some are captured and lead to a fault. For that reason, many circuits are protected today. A well-known example of this is ECC, which protects most of today's memory, typically detects up to 2-bit errors and corrects 1-bit errors. Now, these protections are expensive and they can take up valuable space on silicon, and for that reason, they're not always practical, in particular for compute logic. Okay, so when a faulty transistor does lead to an execution error, the blast radius can vary enormously. The error can be as small as a tiny math error on the 6th decimal of a calculation, or it can cause that same calculation to be off by 1 billion, or even worse, be actually incorrectly flagged as incomputable, a NaN. Right? In other cases, the fault just pushes the GPU to some invalid state, and it hangs there. All right, so at this point, the fault has jumped out of a silicon and entered the realm of software. As we just mentioned, the execution errors can take multiple forms. In the case of a hang, a watchdog is likely to detect the problem and throw an exception. At this point, it is no longer silent. Calculation errors, on the other hand, are more likely to go unnoticed. So let's focus on that. Most of the math behind AI is rooted in linear algebra, and matrix multiplication is the workhorse of that math. They're often called GEM for general matrix multiplication. Right? Those gems also happen to be one of the most expensive operations used by models, and that makes them particularly vulnerable to SDCs. Right, so these gems are implemented in low-level libraries, and they use highly optimized CUDA kernels to take advantage of tensor cores. At the elementary level, those gems are long sequences of matrix multiply add instructions. So when the original error is small, it tends to vanish in those long summations because of a limited precision of floating point arithmetic. However, when it is large, it may propagate or even explode, particularly in the case of an int for an n. All right. So what we see here is that the outcome of an SDC that goes through a gem depends on the initial error, the data set surrounds it. It makes it very difficult, if not practically impossible, to predict. All right. Reaching now the last layer of a stack, the AI model. So models are essentially a complex network of interconnected gems and activation functions. So what's going to happen to our SDC? It has survived the trip so far, made it out of a gem, and now reaching the layers of a model. Well, once again, it depends on multiple complex factors. But first, we should state that many models are intrinsically resilient to noise. A good illustration of that is quantization. Some models can be trained on as little as a single digit for precision. But it gets better. Models may even benefit from noise. Think dropout layers that actually accelerate training convergence by injecting random zeros, or LLM temperature that improves on the quality of predictions by also injecting random noise. Right? Some of that resiliency can be traced back to certain activation functions using transformers, and specifically layer norm, softmax, and causal mask, which tend to greatly reduce the impact of huge numbers that maybe have caused by an SDC outliers, that is, right? They may actually even mask entirely a numeric explosion in some cases. Right. All right. Some errors do propagate, however, and that's because some regions of a model are vulnerable. For example, the logit layer, which is the last layer of the LLM that turns the embeddings back into tokens, is not protected by an activation function. Right? Errors that happen in the backward pass may corrupt a gradient and derail training. So we've done some analysis on this, and data from simulations suggest that under 1% of SDCs translate into numeric explosions when training a model. All right, so in summary, we have followed the journey of an SDC from the initial perturbation in silicon all the way to the model. We've seen that many of these faults vanish as they move up the stack. However, some do survive and have effects ranging from tiny math errors that are extremely unnoticeable and easily recovered from, all the way to numeric explosions. All right, so we're seeing how complex and insidious SDCs are, yet they are inevitable. So how should we tackle them? Something we've learned over time at NVIDIA is that no single solution is going to fully address a problem. So we've gradually developed a multi-tiered strategy consisting of multiple lines of defense and both proactive and reactive measures, right? That covers the entire life cycle of a GPU, from its birth at the factory all the way to its end of life in a data center. Devin is going to walk us through this.
Thank you very much. So let's walk through the strategy. First of all, we don't want chips that have defects to leave the factory in the first place, right? We want to catch them before they go out into the wild and cause what we call reliability incidents. So we can do this by effectively sending the GPUs to the gym. So as soon as they're born, we take them, we put them in really hot ovens, 125°C, and we just bake them for hours and hours and running advanced stress tests on them in order to precipitate these early failures, ones that have some intrinsic defect on the silicon or ones which would otherwise fail during their high load during ordinary usage. And so this is one of our proactive measures, right? We're catching them early before they even go out into the world. But this isn't going to catch everything, right? Some factors are only visible in a data center, and some things can happen on the way to a data center. So for that, we need to catch these test escapes by doing on-site validation. So our second line of defense occurs at the data center during the initial build and validation stage. This is pretty much the same concept, just on a fully connected cluster. It's been assembled, it's been configured, everything's together and good to go. And so the idea here is that we more or less run the same sort of stress tests in order to precipitate out these failures. We want to get them before they're actually being used for productive workloads. We don't want something to just crash and burn the instant that someone's trying to start training, right? And so the way we do this is by performing some benchmarks. So your HPLs, your linpacks, other special sauce that you might have. And then we also run effectively burn-in tests, just redlining the GPUs as hard as we can for hours and days to make sure that that performance remains stable over hours and days of continuous use. And this ensures that we have the necessary stability in order to train foundation models, for example. But this is not going to be sufficient. Even if we catch 100% of these test escapes, GPUs age, as do we all. And so we have to take into account the fact that there are going to be errors that show up over time. And so we have to continually monitor the health of our data centers and the GPUs inside of them. So with a data center in production, we have a whole lot of diagnostic tools that we can use in order to eke out particular failure modes. But field diagnostics can take a tremendous amount of time, hours and hours, just to scan over every possible occasion and see what failures might be present. So that time that is spent doing these scans could be better spent doing inference or training or any number of other things that you want to do with your GPUs, right? And so we need to balance proactively finding these bad GPUs against the need to actually use them for productive work. So our approach here is very similar as before, do cluster calisthenics. So we take tens of thousands of short diagnostic tests, we throw many of these small jobs, single node, across entire data centers and run these scans on an opportunistic basis while jobs are collecting for larger training or inference or what have you. And so each of these jobs runs hundreds of smaller tests, which are meant to elicit failures. So they're exercising the memory management and the mathematical machinery that is laying at the heart of the GPU. And so by squeezing in these smaller jobs in between the much larger foundational jobs, we can effectively take advantage of idling GPUs or ones which would otherwise be waiting to enter the queue for a larger job and not affect any user experience whatsoever. We can effectively just take advantage of that downtime in order to get more information about the health of our GPUs, all for free. So we are currently running this screening tool internally for research purposes on our internal data centers, but we're hoping to share some really interesting results on that, as well as the tool itself very soon. So our next line of defense takes place the moment an SDC happens. So far, we've been trying to be proactive, get the bad GPUs out before they can fail and cause harm. But the idea here is to catch an SDC the moment it happens before it has a chance to derail the training. So one way that we can do this is detect a really strong signal, like a numeric explosion, your nans or your ints, look in the gradient, look in the loss. And when we detect this, we can take that training step and rerun it on a different GPU. If we get that same numeric explosion, that implies there was something wrong with the model. It was unstable, or you used some bad data, or something else. But it allows us to disambiguate the situation and identify that it's not a GPU problem. Conversely, if we can't reproduce that numeric explosion, then that does imply that there is something wrong with that GPU. We can isolate it, diagnose it, learn more about it, and insulate future workloads from that GPU's bad behavior. So this feature has been added to Megatron LM, which is NVIDIA's large language model training framework, and is actually currently available today for anyone to use. So hopefully this will help harden everyone's training workloads. But many SDCs, as Cyril mentioned, vanish entirely, or they have a more subtle symptom than a full numeric breakdown. To catch these more subtle symptoms, we have to have a more sensitive detection method. And the idea here is effectively the same. We have special CUDA kernels, and we're checking for variations in the multiplication's accuracy. In a perfect mathematical world, we'd expect the checksum of the input and output matrices to exactly equal each other. But floating point error has some intrinsic round off, and so we have to set a threshold. If we detect that a threshold has been exceeded, we can say, okay, I need to rerun that gem on a different GPU. Again, if we have that same threshold exceeding, that just means, again, something wrong with the model, something wrong with the data, or the threshold was set too sensitive. But if we don't reproduce it, then we know that that particular gem, that particular tensor core, has a specific problem. And again, we can raise an exception, isolate that GPU, and insulate the workload from its consequences. This is in development in NVIDIA, but we're hoping to share these hardened CUDA kernels with the rest of the world very soon to help protect the critical computations that Cyril had mentioned earlier. And the performance impact of these is very mild. It's only on the order of a couple of %. So it really can be used whenever we need to. We've had multiple proactive defenses and multiple reactive defenses, but we have a last opportunity to find bad GPUs, learn from them, and cull them to reduce their blast radius. So when we have these test escapes from all of our previous lines of defenses, we have job failures. And these can manifest themselves in a wide variety of ambiguous ways. You might have incorrect math, as we mentioned before, specific types of XIDs that are cast, or just strange hardware exceptions. And each of these in isolation doesn't tell us a whole lot. If you go to the hospital with a cough or just a sneezing, it's not going to tell you a whole lot about the underlying syndrome. But if we look at the whole constellation of symptoms across the entire history of a node or a single GPU, then we can pull back that fog and disambiguate the situation and identify exactly what caused that GPU to fail. And we can remove it, correct it, and take it back to better learn from it. So this failure tracking service that we are currently running in NVIDIA gives us this power of perspective to look at the entire patient chart of a given GPU and understand it at a much more rich level so that we can better harden our future designs and software against the consequences of SDCs. So each of these lines of defense, from the factory testing to the functional validation to the failure diagnostics, offers us a great opportunity to protect researchers and users and customers from the inevitability of SDCs. But we've had a whole line of defenses, and I'm going to hand it back to Cyril to bring it full circle for us.
All right. Thanks, Devin. So all the solutions we just walked through really aim at identifying and weeding out defective GPUs and therefore improve the health of our data centers. However, there is another indirect benefit to this, which is by deploying diagnostics and detection tools at scale in data centers, we collect a lot of valuable insights about the failures we observe, the types, frequencies, and so forth. By incorporating those precious learnings into the design of future GPU generations, we really sort of give back to the community. So in essence here, what we have is a virtuous cycle from foundry to industry and back, and each iteration of that cycle really improving on the last one. All right, so to recap, right, we've seen that SDCs are increasingly inevitable at the growing scale of today's data centers and as we continue to push the boundaries of physics. We've seen how complex and yet poorly understood this area is. This is an issue that NVIDIA is taking very seriously, and we believe we're uniquely positioned to tackle it thanks to our deep expertise in GPUs. We've put together a multi-tiered solutions for this. Some pieces of it are already available to the ecosystem. Others are in active development and will be gradually released. All right. We want to thank you for listening, and we're looking forward to the next iteration of our virtuous cycle. Bye.
Thank you very much.
Please welcome to the stage Yelena Pieszewicz-Grobovich, Hussein Mahana, Jeff Holland, Shishir Patil, and Cyril Morian.
Hello, everyone. We're going to have now a Q&A session. Thank you, everyone, for very inspirational and interesting presentations. We have some of the questions that were submitted from the audience. We also have a mics here, so if you want to ask a question in person, just stand up and come to the mic. I'm going to start off with asking with a question for Hussein. Metamate touches everything from source code to HR data. How do you keep the LLM helpful without violating privacy or compliance?
Yeah, it's a great question. There's a lot of techniques that we use, but I'll just mention two important ones. So at training time, you really want to scrub your data for any PII information, and you want to do a very good job in that. And then at inference time, you also want to make sure that your RAG agents are operating under the same authorization of the user so that the agent could only see what the user could see and could not pull out any data. There's a lot of other techniques. You could always have filters, filtering the answers, watching out for things that look suspicious, and then you could block the answer, etc. But it's becoming more and more of a solved problem. I guess my point here is don't let that make you afraid of using agents.
Oh, thank you. Jeff, a question for you. You mentioned a lot about need for context for agents and AI to help make decisions. What about hallucinations?
Yeah, this is a great questions from the get-go, the kind of access, permission, and then hallucination. I guess the short answer is it's definitely not a solved problem. Anytime you're thinking about an agent, especially agent for a business, I don't know of any solution where it's like it won't hallucinate at all. I'll say a little bit of kind of where we've started to tune and optimize for. The first one is if I think about, kind of defining the flow of an agent and the orchestration, especially for enterprise tasks, we heavily prompt and tune the agent to retrieve context whenever possible. So like anecdotally, if I open like ChatGPT right now and I ask it a question, I don't know, 40% of the time it will go and like look up the web or actually go look at other content. And a bunch of time it just starts generating right away. It's just pulling and it just starts generating an answer. And in the latter half is where hallucinations become much more problematic. And so in the case of some of our enterprise agents, like 95 to 99% of the time, the first thing the agent will do is go retrieve the relevant context and then generate the answer based on that context. So if you can help ground it a lot more, it really lessens the impact. The only other thing that we're trying to spend a lot of time and effort in, and we've seen some success with, is just trying to surface and identify where are the context pieces that you're going. You even showed this in some of your demos, but like showing this is where the answer came from, this is how the answer got derived. I even think about me as a human. I guess I don't hallucinate, but like I'm not right all of the time. Sometimes I give the wrong answer. Agents are going to be the same way, but just make sure that I can at least follow the breadcrumbs. So those are two strategies that we've tried to employ to help at least make it so people are more willing. I like where your head was at too. Like, don't be scared of agents. Yes, there's a possibility things might hallucinate, but you can prevent against it and at least be able to verify.
Thank you. Shashir, you talked about developing a Llama stack, right? What do you see as the most open challenges in that space?
Yeah, with Llama Stack, I think there's two parts to this, right? One is the technical parts of it. How do you make it robust, et cetera, which I think there's an excellent team. So that's not really a concern. But I guess there's a more philosophical question is how do you think of building the right vocabulary, right? Because in a lot of agentic scenarios, it's not like classical systems where you can say, oh, well, there's throughput, there's latency, let's just measure that, right? So this is, OK, well, people are going to have different applications. People are going to have different interfaces, different languages. And then how do you now build the right vocabulary so then people can come in and then either plug their evals or lift their evals in a very small, significant lines of code contributions into Llama Stack, or adapt Llama Stack in such a fashion that it's immediately readily applicable to them. So just making it extremely flexible, making it very agile, and just thinking about that is, I think, pretty challenging.
Thank you. And Cyril, one question for you. What is the weirdest cause of silent data corruptions you have seen?
Well, I think the ones I probably find the most intriguing are the ones stemming from cosmic rays, right? The thought that a particle has traveled millions, if not billions of miles, may actually even come from a different galaxy, lands on your GPU and messes up your math is, is rather intriguing. Now, obviously, we don't have particle detectors in data centers, not yet, at least. So we can only speculate, but we do observe single failures. Or in the case of a permanent issue, they will find some kind of intermittence or pattern. But those are truly random, and we do have a few isolated events that, at this point, we can only put on particles. Now, in a lab, so lab environment, it has actually been, caught and actually created. I mean, we have physicists that take GPUs and they bombard them with particles and see what happens. So it's been observed in a control environment.
Thank you. I see we have some questions like in person. Let's go to the first.
Hey guys, thank you all for the wonderful talks by all of you. My question was for Hussein. Like, what were the key business metrics that the Metamate team has been using? And I'm sure there were some internal tough debates of what's the right metric, at least at the early stage, and how those metrics have kind of changed or evolved over the course of time.
It's a great question. Like, those business metrics are never a straightforward answer, but we do have some what I would call proxies of satisfaction, like either users just clicking in and saying they're satisfied or not. Feedback is also very useful. But we do want to evolve the metrics to start understanding how much time are we saving actually, and that's not a very easy question because monitoring and observing all workflows is just very hard. But you do come up with various proxies and you find a proxy that the team is comfortable with. My advice is don't trust it forever. It eventually breaks and you'll have to figure out a different one.
Thank you. It's kind of hard to see, but I do have one question that came in from before. Like Hussein, and please jump in, everyone. You had an analogy with microservices. And historically, one of the challenges, well, there were many challenges with microservices as well. Problems like complexity management, data consistency, fault tolerance. How do you see that type of problems playing out in a world of MDO and sub-agents?
Yeah, perhaps I could chip in, and Jeff also would love to hear your perspective, and Shishir and Cyril. So I think I'll just simplify the answer. Number one, you need sort of to manage complexity via some sort of catalog where people could register skills and you understand what it's supposed to do. But most importantly, they also need to register the schema and the evals associated with it. It's just, look, at the end of the day, test-driven development is the way to manage complexity of software. In this case, for sub-agents, if each sub-agent has a clear set of evals and you have a system that is running through them and highlighting failures and you have people who are maintaining that, you'll be able to manage complexity. That would be my short answer. Jeff, I wonder.
I love that. I think the only additional spin, at least that to me makes this interesting, even prior to some of the time I've spent now working on some of the AI things, I spent a bit of my career working on like microservices and Kubernetes and whatever else. I think one of the things that we've started to observe as we're starting to implement some of these sub-agent things is some of the really, really hard problems when it comes to microservices. You mentioned a few, fault tolerance, you name it. Like they could be very finicky. And it wouldn't be uncommon at all to go to an organization, they're like, oh man, we have such a hard time knowing what microservices to do. What happens if there's a ripple effect where we now have this web of all these different dependencies? How do we make sure things go? Many of those same principles hold true, but I think the part to me that gets exciting is with an LLM kind of at the core, orchestrating and reasoning around some of these things, it actually does a really good job of like taking care of some of the marginal work automatically for you. Meaning that like there can be a blip in the system, or there might be some, whatever, common woe in microservice land is what happens when my upstream microservice or downstream microservice makes a change, and how do you make sure that doesn't break everything else? That can still be a concern when you have a sub-agent, but some of the agents will actually find it on their own. Like they'll be like, oh, it looks like something here changed. I'm actually going to adjust how I'm going to interact with this other system or do whatever else. So many of the same things hold true. I think where I get optimistic, though, is the ability for us to scale these things and scale them really quickly becomes easier in some ways because you have this regioning agent that can deal with more ambiguity than the previous world of if-else statements that are very, very finicky to any change of variable.
Yeah, absolutely. Self-healing, self-reflective debugging, absolutely.
Yeah, I think on the modeling side, it's already becoming pretty clear, right? And historically it has been as well. You had the narrow ways for TCP/IP with microservices, like you mentioned. You had RPC calls or RESTful API calls. And now the equivalent of that on the LLM side is, do you have very clear function definitions or tools definitions? So you're going to have very clear interfaces where the LLM itself is allowed to do multiple things, use multimodal information, do test time compute as much as you need. But then as long as you guarantee that here's this narrow waist and a promise of how you interact with different microagents, interact with each other or interact with one orchestrator, I think as long as we control this narrow waist, and right now function seems to be the way to get there, then you have a good control.
Okay, thank you. Should we go? Would you like to say something?
Well, I think, on the fault tolerance angle, yeah, I believe that models are increasingly resilient, and teaching those sort of systems of models to kind of learn to operate when something doesn't go right, is probably.
Okay, so next question in person.
Thank you, everybody. It's a great engineering conference. My name is Alexei Kraber from AI Community Architect at Neo4j, and I also run Open Source Science Initiative at NumFocus, which connects scientists with open source developers. And for scientists, as you know, and for engineers, reproducibility is top of mind, right? So we used to have reproducibility. You write tests, your data sets are fixed, right? You usually get the same result. And with models, the key difference is they're constantly evolving, right? And so you can put evals on them, but evals can say the things are different, right? And you can suddenly it will stop answering, suddenly out-of-the-blue will hallucinate. So how do we institute reproducibility? For instance, at metascale, how do you snapshot your data? How can you snapshot metadata, right? Not metadata, metadata at scale. How do you do you do timestamps? Do you timestamp agents? Is everything becoming timestamped? How do you guys approach this? And for Hossein, how do you approach this for Metamate? Because what if agents give you different results, right? And I just wonder, what is your approach to reproducibility as an engineering discipline?
I invite Shishir to start. I'm happy to add to that.
Yeah, so it's a very good question, right? And the way we think about this is you can choose to have reproducibility at the very core model level, which could be at the tokens level, but understanding that it's not, well, you can go pretty far with it, honestly, as long as you have very good control of your underlying system infra by setting the right, temp, topy, and so on and so forth. But the other way to also think about this is, can you expect and run your evals and then expect reproducibility at a specification level, right? If you can have very clear specifications that, okay, well, rather than this is the document that I want the LLM to take and this is the exact sentence I want to come out with, to say, well, here is my namespace that I expect the LLM to touch for a given query. And then this is, I expect these substrings to perhaps exist. I'm going into the detail here, but just to illustrate the point. So if you can have specifications, then you get really good reproducibility. And then you can swap in and out the underlying LLM. You don't have to worry too much as people try to optimize it using different techniques. So there is ways where you can do that, right? It's pretty open, but I think as a community, we are now trying to understand what's the right level to operate at.
That's a great answer. Thank you. I think the concept of reproducibility in the era of intelligence needs to adjust a little bit. It's not going to be reproducible byte for byte, just as you mentioned, Shishir. So I think, your judges or your evaluation agent needs to be probabilistic or non-deterministic. It needs to understand that the essence of the answer is the same despite of using different words, etc. And that's why evaluation is really hard. I've witnessed this in autonomous vehicles. There's so many different paths the vehicle can take that are correct. And just reproducing it sort of turn for turn or location by location doesn't make sense. So it is just part of the challenge. I think, just to throw in, I think LLMs as judges are a very interesting concept, and we're investing in that at Meta. We're trying to automate judges and leverage LLMs. I mean, ideally, you could have human beings look at all these things and say whether they're the same or not, but even that is not accurate and it's slow. And so potentially automating some of this via LLMs themselves, while making sure you're not getting into a vicious cycle where the LLMs introduce bias and so your evals are biased, etc. But I think that's the direction forward. You're going to have to automate. Like the equal sign is going to mean something very different for intelligence.
Yeah. Thank you for the question. Next.
Hi, thank you for speaking today. My question is about defining the responsibilities of subagents. And Jeff had a really good example of a query comes in. You want to make sure it's unambiguous enough. And if it is it a time series? Is it ... When we think about how much work should be done in that one inference, how do you think about, let's go ahead and bundle it versus split it out? Is it just kind of see what feels right and try it? Or is there more science than art behind it?
I'll speak from our experience and happy for others to chime in. I think it's actually fairly related to even the conversation we were having before with eval, where The higher up you go in the more complex things, the harder it really becomes to reason about, like, where do we make changes to get improvement here? And so we just consistently, like, anytime we see an eval score that is suboptimal or some quality that's doing, we just start by breaking it into smaller tasks, and then we specialize each one of those smaller tasks. And so honestly, all the ways that we figured out how to break this down, it started as one big box. Like the first version was one big box, and then we broke it into 2 boxes, and then 2 boxes broke into 2 more, and 2 more, and 2 more. And we just consistently did that because, again, with this non-determinism, and like as awesome as it is for the self-healing and the reasoning, if you try to optimize it at too high of a layer, you'll drive yourself a little bit crazy. So rather than just continue to optimize, we realized, like, let's break this down. We would optimize one little piece of it, and then the whole, the aggregate would come. So it was fairly, at least for us, like an organic journey that really was the side effect of how do we find the right ways to make this thing better. And then it helps because now we have these individual, again, sub-agents that now we can just focus on making sure the sub-agent is really good at its eval, and the whole generally follows suit.
Yeah, I could not agree more. This is not an addition, it's just out of my experience. You'd be surprised how many people treat their evals very superficially. They just think it's the word of God, and they don't really understand what's inside of it. You really need to understand your evals inside out. You need to understand what they stand for. And then finally, don't trust them, indefinitely, because they get saturated and they often become, they lack representation with customer use cases. So the more you understand your evals, the more your team is looking at debugging these evals, the more they realize that evals themselves have issues, the better the outcome you get.
Cool. Can you have a next in-person question?
Good afternoon, and thank you for a very inspiring and insightful morning of talks. This is Lamia Youssef from Stanford University. And my question today is about eval and reliability. We talked this morning about how agents need to be reliable in order to be able to integrate with the workforce. And obviously, this is for the technology native companies. My question about the non-native technology companies, what needs to be true in order to be able to integrate agents into the workforce? And some of the ideas that comes to mind is compliance, maybe privacy, but I'm thinking about healthcare, I'm thinking about banking, I'm thinking about oil and gas even. The question is, what needs to be true for agents to be able to be integrated into this kind of workforce? Thank you.
I'll start with a quick one, but I'd love to know others. I mean, the first thing that truthfully comes to mind for me on that is it's less of a technical one. That's the one that initially springs up. There's a ton of things, and you mentioned some great ones. To me, it's much more of like behavioral and psychological. Like I think back to, I spent a few hours about a month or 2 ago with an ER physician at a medical facility in Canada. And he was talking about, all of the things in his day-to-day. He walks into a lobby overflowing with patients. He's overwhelmed with like just trying to stay on top of things. If anyone's watched like the new TV series, The Pit, it was like literally, it was like watching an episode of The Pit, hearing him talk about his day-to-day life. And his sentiment was, he was like, I see the potential in different areas where agents and AI has even started to help him some. Like he's using an agent that helps automatically transcribe the conversations he's having with patients. But the biggest obstacle he sees is there's just a lack of both awareness of what's possible with agents, but more importantly, like trust. This kind of fear of the unknown. Anytime this new technology comes in, it's there. So to me, the biggest thing that needs to happen is that people need to start to understand. And again, to be clear, I'm not advocating for recklessness, but having a little bit of the willingness to accept a new tool system into it and the variables that come with it. The fact that like this thing is not going to be perfect. It's going to have its quirk. It's going to be non-deterministic. But to me, it's much more psychological. Like I think as people start to, and it's inevitable, just like any technological innovation. But to me, that's the biggest one. It's not even technological. It's human psychology of like, am I willing to do work differently than I have done over the last decade?
So there is maybe like 2 things that you can do, right? And we already see some of these things. The first is, can we build these services, keeping this in mind? Concrete example is Kubernetes. If you go to Kubernetes, there's something called a dry run option. So you can like try to fake run the option, see what the potential end result is, and then you can choose to either run it or not. So giving this more for agentic systems where you can try to dry run things is one way to do it. The second is to have very unique session identifiers, right? So you basically tell the agent, hey, do something. Otherwise, give me an undo button, right? Just give me a clean slate, erase everything that you tried, and do not leave it in a more messier state. So in terms of transactions, this is the commit versus abort, right? So can people who are building all these different services or applications that they then want to interface with agents, can they now start enabling the scenario where the agent itself has an ability to either completely accept or completely reject and go to a clean slate. So I think, yeah, there's some ways in which, obviously, early adopters, hyperscalers are super early at adopting this, and then, of course, healthcare and banking, they aren't there yet, but there's been a steady stream of techniques to enable this, yeah.
Very nice. I fully agree that the psychological component is really fundamental here. But I think the trust really starts building on technology, and people need to trust the technology. I'm thinking of the aerospace industry, where you have a very strict compliance, redundancy, and so forth. Understanding that some of it may be more psychological than practical in the context of AI. But look at the AV space, where today I don't think there's any sort of enforced certification on the reliability of the calculators used behind it, but there's companies are sort of volunteering sort of safety standards, making sure that you don't get the NAN more often than you can, and if you do, you can recover. So totally agreed with the fact that at the end of the day, it's trust, right? It's psychology. But I think providing assurances that the technology works or works well enough can help.
Yeah, if I may add just one small thing.
Of course.
These are definitely great answers. I think what enterprise users definitely want to build trust is signals and signs that the answer is accurate and also explainable. And I've met with various startup founders who are working in this field, particularly with financial services, and they mentioned that citing resources is an extremely important aspect of the answer. So I think there's a big experience aspect of how you present an answer to those users that would actually either accelerate or de-accelerate adoption.
Okay. I feel like we...
Insightful. Thank you very much.
I see we still have people, but we're also very close to the time, so I'm going to ask one final question, and this one is for all of you. And the question is, what gets you most excited about the next year of AI?
Robotics, particularly. Can't wait for something to fold my laundry, iron it, and
I
take
could
out
get
the
that
trash.
one, yeah.
So I love agents, but I'd love them more when they have physical impact.
Yeah. For me, it's if I think back even to the last week of how I do my work, whether it's having LLMs help me in writing blog posts, to I have little agents that help me in creating little artifacts. I'm just excited for a world where it's I feel like I have this mini team of experts that just follows me around as I work and just makes me so much more productive. Even already, I feel like I can do 1 extra day's worth of work a week than what I was able to do a year ago. And I'm hopeful that in 2 or 3 years, it's going to be that I can do a week's worth of work in a day. So just the productivity aspect of that gets me really personally excited, and it feels very attainable, directionally, of how fast things are moving.
I think what I find particularly interesting is just how accessible agents has become, right? So there's no one winner in agents, and it's become very accessible. Open source is so far ahead, and people are doing so many interesting things. They're just seeing so many new things show up. I think it's pretty exciting.
1 year, that's an easier question than 5 years. So what I probably most excited about is autonomous vehicle. I think it's real. After years and years of promises, I think we're seeing it happening now. And I find that extremely exciting because it really is changing lives in very concrete ways. So yeah, I'm excited to see that happening before my eyes.
Excellent, thank you. Well, let's thank our speakers for this session. With that, we're closing this part of the program. We have a lunch, and then we come back for a startup panel on Gen AI to discuss RL, agentic integrations, and see you in a minute.
At Scale, AI and data will resume after this
I find peace of mind in quiet places, quiet places, quiet places. This is why. Nobody say it, but I can read between the lines. Yeah. Nobody say it, but I can read between the lines. I can read between the lines. Energy is fire, conversation is right. If you stay tonight, baby, I might let you say all of me. Want you here, need your mind in these sheets. Come You start the fire. I'm trying to find what you like. Oh, you and I won't close our eyes till we cross that line. There's something about you, something about you. You know I crave your touch, but we don't need to rush. There's something about you, something about you, immersed inside my mind. Maybe it's a sign, 'cause it's already over, already over, already over, already over, already over, already over, already over. Tell me what you desire. Let's get lost inside, lose track of time. Oh, and every side, we got nothing to hide. Wanna see your skin on mine. There's something about you, something about you. You know I crave your touch, but we don't need to rush. There's something about you, something about you. I know it's hard to find. Listen, it's a sign, 'cause it's already over, already over, already over, already over, already over, already over, already
Please welcome to the stage Joe Spisak from Meta.
Welcome, everyone. I see everyone's still getting back from lunch to the panel on Gen AI startups. So I'm Joe Spisak. I'll be the moderator for the panel. I lead product at Meta for our PyTorch efforts and have in the past worked on our large language models called Llama. And this is kind of a conference after my own heart. So, and I was actually luckily able to pick some of the best panelists, probably at some of the most impactful startups in the world. And you're going to get to learn from them and kind of get to know them, and we're going to have a little bit of fun. So let's welcome the other panelists.
Please welcome to the stage Horace He, Dhruv Batra, Sal Candido, Eugen Hote, and Karina Hong.
All right, so this is where we do jumping jacks, right? Is it? No? OK, all right. Cool. All right. Well, let's start with some intros, so get kind of acquainted with who's up here on the panel. So starting with Horace, my old colleague, PyTorch. So three things about Horace. One, he's a core contributor still of PyTorch, although it says at Meta here. That's strange. But actually now at Thinking Machines. He's also an ML systems researcher with papers at OOPSLA, Eichler, and kind of like the who's who of conferences, including NeurIPS. He's also a competitive coder and open source contributor. And yeah, kind of, I guess you reached the ICPC World Finals. Yeah. That's pretty cool. Awesome. Welcome, Horace.
Thank you.
All right, and then I have Dhruv. So Dhruv, also a former researcher in FAIR, so kind of embodied AI pioneer and tech leader, formerly led FAIR's embodied AI work including Habitat. He's also an award-winning educator and academic out of Georgia Tech, actually where your wife is also a professor there, so power couple for sure. Well-cited. And then obviously a huge advocate of multimodal AI over the years. And that makes sense given your work in embodied AI. Awesome, welcome. And then to his left is Sal Candido, so another ex-colleague of mine, co-founder and CTO of Evolutionary Scale AI, focused on AI and biology, one of my favorite areas that I think AI can have a really positive impact in. Let's see, he was formerly at Google X, working on the Loon project as CTO of that. Has researched multi-scale geospatial and sustainable AI with lots of papers, including a seminal paper on scale, masked autoencoder at ICCV 2023, and actually also works on AI for biological sequence modeling, as I mentioned. So welcome, Sal. Awesome. And then to his left is Eugen Hote, member of technical staff at Perplexity, worked on Llama post-training. And so he's an ML engineer, formerly Google also, at Perplexity, worked on open source, including, wow, you worked on GPT too? That's cool.
Not that GPT-2.
Okay. You worked on style transfer and a bunch of other stuff. And you also worked on adaptive neural architecture search in the past. Awesome, welcome again. And last but certainly not least, Karina Hong, founder and CEO of Axiom, former Stanford PhD, a Rhodes Scholar, let's see, award-winning mathematical researcher. And man, what else could you do? I know, right? I got a crazy panel here. If I can get my paper here. Let's see, and a community builder and student leader. Wow, so you actually led MIT's undergrad math association, recipient of Mathematics Community Building Awards, NSF Awards. Wow, okay, so crazy. So from MIT to Stanford PhD, founder, raised money, building a team and a company. Amazing, thank you, welcome. Awesome. Actually, so fun fact, all those bios were actually generated by ChatGPT. So I'm kind of curious, actually, like, did ChatGPT hallucinate at all? Was it accurate? Was there anything, actually, Eugen, I know it said that you're still at Meta, which is like maybe wishful thinking for me, but like, I don't know.
Yeah, big news. I'm at Perplexity now.
Yeah.
But yeah, besides that, everything else sounded pretty reasonable.
Okay.
I think also, like it said, I was at DeepMind, which I was at like Google Research, but I guess small mix-up.
Okay, cool.
Yeah.
Any other hallucinations? Everything accurate?
It said is for a few of us, right? Like,
yeah.
Which is wrong. But
right.
I'm mostly curious, did you feed it our bios, or is this from parameters?
This is, so it's probably got some knowledge cut off, and I'm sure it did some like, indexing and that, but I fed it, I literally asked it your name and like, give me 3 lines about you all, and it fed pretty good information. I did play with the Utori API, by the way, and it's actually even better. So shameless plug for Drew's startup.
I feel like I got it right, but it was like an interesting choice on like what it like picked out, like the 3 things. Like
yeah.
It was probably like this guy gets a mention for a vision transformer. Like,
yeah.
but I mean, I did do. I was part of that. So
yeah.
Yeah,
okay.
I do really like the factual statements were right, but like the emphasis were like a little bit strange. Like I'm kind of surprised that went back to like my undergrad.
Yeah.
A little bit surprised it didn't bring up like high school clubs
wow.
and stuff like this.
Okay. Interesting. Okay.
Yeah.
I mean, AI is it's still a work in progress. We're not there yet. So amazing. Okay. All right. So let's kick off some actual questions here. I guess the first one's for Horace, and then I want others obviously to jump in. So, I mean, you and I have been building open source tools for a long time. We worked on PyTorch together. I was like literally surfing through like GitHub the other day, looking at awesome lists on agentic frameworks. I saw one of them had 93 frameworks. Like a bunch of them were like vertically centric, like build an AI agent for like legal or I don't know, whatever it was. But like 93, like what the hell's happening here? Like, we've seen, you and I have seen like the framework wars happen with PyTorch and TensorFlow and all of that. Like, is there, like, what is the best one you've tried, and what do you think that the winner is? Or do you think like we're in for this like crazy entropy for a couple of years and then stuff settles out, or where do you see this going?
Yeah, for sure. I think definitely like when you kind of see these like framework fights happen, definitely at the beginning there's always like a Cambrian explosion, especially when like the barrier to entry is so low, like it is here, like where like fundamentally an agent framework is just like a string templating library of some kind, and like anybody can write a string templating library. And so like yeah, I definitely think you're going to see like a huge explosion like soon, like right now, and then eventually it'll start consolidating. But I think to me, like the more interesting question about like the agent frameworks is kind of not even about like which one will win. It's kind of more about like how, like what is even the place for agent frameworks in the long run? Because I think one of the things you kind of see, right, with the labs and stuff like this is like things like deep research. They're kind of very much focused on like end-to-end RL trained like agentic tasks. And it's kind of not super clear like how these like plug into like the existing agentic frameworks. Like as in like our agentic framework kind of like going down the wrong path, and they should be focused instead on like building RL environments. Like definitely like even if you're doing RL, there's like a lot of nuances in like prompting and like this kind of stuff. But I think it's not super clear to me like where the boundary ends for like post-training and where it should start for agentic frameworks. And I think my personal suspicion is kind of that we're gonna start seeing like more and more stuff get like swallowed up a little bit by like post-training, as opposed to like purely being done in the agentic. That's kind of my.
Yeah, I mean, if you go to like local llama, you'll just see like so many like 4-letter word like descriptions of LangChain, and just like this. I mean, basically like it's a DAG control flow, like give me components and orchestrate them in Python and all that. And people are like definitely like looking for something better, but
yeah.
And my feeling is definitely that the models, once they start reasoning much better, like you'll less need an actual framework at that point. You'll need stuff, but the model itself, in theory, should like be able to reason about which tools to use, like which files to touch if it's doing a coding task or whatever. So
yeah.
Anyone else like have a feeling on that, or a framework they love or hate? Preferably hate.
I don't know. I feel like one of the big problems is that the best thing kind of to do, like not even like a framework, but like the best thing that you want to do if you're just doing like an agent-based system is different than what you want to do if you're generating data for post-training and then trying to change the model through that. And ideally, we would want to be in a situation where you can start from an agentic flow and then you can improve the model doing that. But I just don't see like there's a really good solution yet to doing that whole piece. So hopefully soon it will save us all a lot of code, I think.
Right. So all these kind of like have hopefully like planned obsolescence. Like they're all just going to die in like 2 years, and like RL will take over.
I think we do have to sympathize a bit with the framework makers.
Yeah.
The reason why so many frameworks aren't useful is because the ground is shifting underneath them. Like,
that's fair.
When you make a framework, you kind of are playing this balance of having some opinions, otherwise you're not providing any value, but providing enough modularity that people can build what they want to build. And you folks with PyTorch have had to get those decisions right. The history of PyTorch is that it came from a pull, right? Like researchers were already hacking away on Torch, and you wanted to improve that process while not limiting anybody's scope. Today you build an agentic framework, and if you misjudge where the capabilities are going to be, you end up putting walls that are just getting in the way of developers trying to get things done, and it's much easier for them to just go directly to the model, and your framework doesn't provide anything additional. So.
I had this chat with Ion Stoica earlier today. We did like this podcast, and we were talking about abstractions, and I think like that's like you just nailed it. I mean, I think like if you pick the wrong abstraction, then it's a dead end, right? You can't either hit like the right target user, or like people want to click down to a lower level, or and so like I think like we are kind of building hopefully at like a level where we understand the patterns, or things start to emerge, and then you kind of build from there. But like I feel like there's plenty of frameworks that have kind of started all the way at the top, and they're losing, right? They're just like, because all of a sudden I want to have more flexibility and I don't have that, and that's like the framework, that's the gaming frameworks, right? So.
Yeah, I'll give another argument, which is like I think One way to think about it is like, what is the point of like agentic framework in the first place? It's like the reason for agentic framework to exist is that the base model cannot immediately like do it by itself, or like it's like not capable of like doing all the actions or like like doing its memory or like handling all the things by itself. And so in some sense, like what you're asking from an agentic framework is you're trying to like get the model to do something that it does not like immediately like naturally do by itself. And if you want to do this, I think in many cases, like I'd say, like RL seems like a more principled way to like elicit like a different behavior, as opposed to kind of purely something that's like agentic on top.
Okay, so I keep hearing RL. Everyone is, of course, talking about RL these days. Like I remember I was sitting in a room with Gary Marcus, like probably 11 years ago, and he was pitching us, like he had geometric intelligence. I think Uber ended up buying them. And he had this crazy cast. He had Zubin, right? He had like Jeff Kloon. He had this like amazing set of researchers. And they had literally just formed the company, and all of a sudden they wanted to sell, right? And half the people were like half-time at the company. And they showed us a demo, and it was like, I think it was like Pong or something, right? And it showed like the really smooth actions, like, and then they compared it to like DQN. And we're like, okay, that's kind of cool. But that was like what was exciting at that time about RL. We kind of walked away like laughing, like this great researchers, but what did they just pitch us? And they wanted, by the way, like 8 figures per employee to buy them, right? Something crazy at the time. But like
that seems low now.
I know it is. I know. I need one of those 9-figure offers. Yeah, let's put that aside for a second. But like Drew, tell me, like, is RL for real this time? I know we had RLHF, and RLHF is largely kind of a fake RL. But is this really the future, or is there going to be like something beyond RL, or?
So, predicting the future aside, which is hard, but I think maybe a short history lesson is in order, because people think RL got invented with RLHF, and that certainly is not the case. Like, there's a wonderful talk called, in the beginning, all learning was reinforcement learning. The idea, the genesis of AI was with intelligent agents that can go interact with an environment and, have sensory action loops and exhibit intelligent behavior. And when you start from that abstraction, you kind of very quickly get forced to deal with the dynamic nature of the data that's coming to you, stochasticity of the feedback, long horizon problems, and RL tackled that head on. We actually did see successes of RL 90s with game playing agents, and 2015 is the phase right after the Go results, which were shocking the world. So what did they get right? They got right that whenever you have evaluative feedback, meaning I don't know how to do this, but if you do it, I know when it works well. So I can judge better. There's a verifier generator gap. There are problems where there's a massive verifier generator gap. Board games are a perfect example of it, but those are not the only games, turns out. Unit tests with code is also an example of it, and there are other cases that are also examples of it. Theorem proving with math, and I'm sure Corina will talk about it. Anytime you have that verifier generator gap, and you have a way of getting verifiable rewards, and crucially, what people forget is the reason why games were first is you have a perfect environment. And you have a simulator of that environment. You can run it, and you can do massive amounts of rollout. Those were the perfect settings for making that work. What did they get wrong? What did that community get wrong? Not enough emphasis on broad understanding of the world and pre-training. And those are the two things that we're seeing in the combination of multimodal LLMs and LLMs in general, combined with RL. Just sort of, I'm not trying to nitpick, but the most recent RL results, like DeepSeek for theorem proving and code proving, they're technically not RL, they're bandit problems, because you're not dealing with an external environment. You're generating a token by yourself. It's internal monologue. At some point, you're done, and you either get a reward or not. Which means this has implications on both the algorithms, but also the systems that you guys create. You folks understand very well that if there's no external environment, then there's a certain kind of optimization. You are going to try to get max throughput through that one GPU. You're not bottlenecked by an external world. If I bring in a bash terminal or a text writer or a web browser as an environment that you have to go interact with, wait for a response from that environment to perceive, then take the next step, suddenly your infra challenges become very different. You're now having to deal with the kinds of problems that gameplay agents did, where you have to run multiple environments in parallel and deal with variable length batching of the rollouts that you're having to do. So that's the world we find ourselves in now, where a bunch of companies and frontier labs are realizing that I just need extremely interesting environments that are high throughput, that I can parallelize, that give me rewards in the end, and I can construct infra around it to elicit capabilities. And where I start from is not from scratch, which is the mistake that the last batch of RL made.
Yeah.
But with those aside, like, it is a compelling framework. Coming back to the example that you started with, you give ChatGPT our names. I give, Scouts by Yutori a link to this event, and I said, go find me who the panelists are and tell me everything that you can about them. So the first, there's not enough information in there to execute the task. So the first, it has to go read that link to find who the panelists are, then conduct another search to learn about them, then maybe look them up on LinkedIn or other personal websites, then comprise this information. This is an environment loop that you have to take on, because anytime you deal with a world that is changing, maybe this link had not listed all the participants. You'd have to go monitor it again. You just have to take that head on, and RL lets you do that.
I'm kind of curious to get Karina's take here, because formal mathematics feels like an area where you can have a verifiable reward, right? There's a ground truth to how you actually solve or formally solve a theorem, for example, or back when we were building theorem, we had theorem proving team, which is now the Mistral team, largely out of Meta. We had environments like Lean, for example, and you had we were doing MCTS, and it was kind of a brute force approach, right? It's like an LLM plus MCTS, or Monte Carlo tree search. But how do you see mathematics? Is it playing here?
Yeah, 100%. I think I'm very excited about the future of applying RL in areas where there's really good grounding and verifier, just like math and code. I think it's very intriguing to think of, because math, when we kind of think about it and we see the math data that's being fed into the large language model, it's doing formal reasoning in natural language. But if you use programming language like Lean 4, then you can suddenly attempt to turn the entire mathematical literature into GitHub actionable code and to apply all the amazing techniques and progress in the coding space to mathematics. If we think about kind of math and how it's different from, say, chess and Go, it is a very big action space. At each step, you can take many possible moves. And if you just apply the sort of techniques that we have seen that made amazing gains in coding to math, but you have a data scarcity problem. So if you scrape all the Lean code on the internet, there's only about I think a couple million lines of code, which is not enough. And how to kind of convert these natural language math data into Lean code, I think that remains a stubborn technical challenge that we are super excited to try to solve that axiom.
Oh, very cool. Where do you see, so if you're able to, we still haven't solved Riemann hypothesis through AI. That was if you recall, when we were putting our North Star goals together, back when we were in FAIR together. Yep. That was an aspirational goal. I don't think we've solved that yet. No one solved it, AI. I guess how would you see, what would a breakthrough look like, I guess, in your space? 100%.
I think there are really 4 stages as we see it. One is kind of problem solving. We have seen a lot of mathematical benchmarks that are numerical answer graded. So if I get the answer right, then I score. If I don't, then it's a 0. But the next stage will be theorem proving, where I want to make sure that the intermediate steps leading to the final solutions are correct and rigorous mathematical reasoning. We're not there yet. Large language models currently are generating a lot of proofs based on sort of pattern matching on what's fed into the training data. We kind of have not seen it being able to reason we haven't been able to see it do grounded reasoning without hallucination on the intermediate steps. And then that's the second stage, which I call the rigorous stage. And there's a big leap to the third stage, which I would call conjecturing, which is having large language models propose interesting mathematical problems to try to solve. And these conjectures are it's so different from what it has seen before. And the fourth stage is kind of intuitions and theory building, connecting these dots, these new conjectures, problems, and the solutions into theory, into mathematical theories and frameworks, and put them into context. Like Grothendieck has this idea of if you put mathematical concepts in the right framework, then the solution might emerge like a landmass being swallowed by the rising sea. And that's a very beautiful mathematical idea and a very powerful one, but we have not seen the AI mathematician being able to do that, and that's what we're really excited to build toward.
Oh, very cool. I guess tangential to math in the biology space, because I have a biologist, a nouveau biologist.
A very new biologist.
Very new biologist.
I play biologist on panels, I guess.
You play? You play? So as you know, Sal is a former CTO of the Loon project, which was what, balloons flying in the atmosphere, providing internet access?
Correct.
Right. Okay. So he works on crazy stuff.
Using reinforcement learning.
Using. Of course.
Interact with the
It's back.
It's how you get funding, right? It's RL. I guess, how has your role changed? I mean, when we were back in FAIR and we were training large language models, or they were quote large language models, they were actually pretty small at the time. How has this kind of agentic world changed biology, changed how you guys approach? Like, has it changed, or are you still just kind of like is your roadmap at all changed? Has it allowed you to raise more money, calling it an agentic biology startup?
Well, I mean, so the world has definitely changed, but I think it's just it's a big progression for like AI for math and science, right? Like from where it was. So I think we've seen very large sums of money go into some of the big pre-training labs, right? Yep. Like in other companies. And I think that like for AI for science, it's just a little bit behind on that same curve, but it feels like it's very much on the same trajectory. So, you think about maybe like 5 years ago or something like that, we all of a sudden like large language models happened, and we said we should train these things to write code, and then like people started working on that, and now they're pretty good at writing code, right? Like, and there's a huge amount of value coming out of that, yep. Right? Like, both in terms of like economic value, but also just like our time, right? Like you go and you are able to build things so much faster. And I think we're seeing the same thing, at evolutionary scale with the kind of the biology that we're working on. So I am not a biologist, I work with biologists, but I have no idea what was going on with some of these things, especially when I started. But I was able to do some actually the reason I got into evolutionary scale was I started working on protein design just because I was interested, and I was working with some colleagues on that. And I was playing around with the models, and I was doing things which I thought, oh, this is cool, this is interesting, this is a nice little weekend project. And then I talked to people who I knew who were experts in the field, and they were like, you did what? And like, I'm kind of an unremarkable person, so you kind of know it's like the models which are getting a lot better. And we just see that happening, right? Like, so how do I end up working on, going from something which is pre-training large language models on biological data to now working on like making drugs, right? Like, it's because like that curve of capabilities, like all the models are climbing up it. And so I do think that like, it's a little bit behind, but we're going to start seeing people have we are seeing people have great world results with these things, and it's going to come more and more to the focus of people's attention. And then I think, more investment will come in. I should say that like our investors put a lot of money into our company, so I think there's like I think there's a lot of people who are thinking this way, but it's the smart money that's doing it right now.
Yeah.
I'm curious because like I feel like it's so cool that you guys are doing. I would say that it's scientific superintelligence. How do you think about like working toward pretty kind of like general capabilities versus specialized like problem, because in math we have trade-off between like good general performance on benchmarks that are getting harder and harder. I mean, they are currently at graduate or research level, but also it's a totally different question to like work toward a specialized problem, like for example you say the Millennium Prize problems.
Yep.
So is that the same sort of trade-off you see in AI for science? Like is a model being able to do many things?
So I hear Donald Trump somewhere in the audience.
Yeah.
I really don't want to hear that voice right now. Go, Sal.
Yeah, I'm just gonna go. So yeah, I think that's a great question. So the way we kind of see it is I think there's two critical importance. Like, there's two critical things to building like a virtual scientist, right? Or even going beyond like what a scientist can be. So there are simulators, and like a lot of the models that we built, like our traditional models, like ESM models, are essentially simulators of biology. They're not like molecular dynamics or something like that, but it's a simulator built to an information bottleneck, right? Like, and it simulates like a protein or a genome. The other thing that's happening, right, like, and many in the field are building it, is reasoning models, right? Like, and when you fuse these two things together, you allow the reasoning model to reason not only in the space of words or whatever space it's choosing to reason in, but also in the latent space of something that sees the world through like amino acids or something like that. And I think that's a really interesting fusion. So we work at it from those angles to bring those two pieces together.
Cool.
It does feel, I mean, generally like the world is kind of going in a certain direction. I mean, the sciences will kind of like fast/slow follow depending on who you ask. I'm kind of curious though for you again though, like on this, you've worked at like a lot of different layers of the stack. And like we talked about agentic frameworks, there's obviously that we go all the way down to the metal where we're generating kernels, for models. Like where do you see the bottleneck in things, and where's the most innovation needed, I guess, in the stack?
Yeah, I would say still it's like trying to take these models and training them on like hundreds to thousands of GPUs. We've kind of seen over the past few years this trend, even in open source, towards like bigger models as we like try to close the gap with API models. Like Llama, for example, Llama 3 was like 70B for the medium model. Now Llama 4 is like 400B. Same trend is happening for Qwen. Same trend is happening for DeepSeek. And there are like libraries out there that kind of try to let you do this, like try to let you scale models, but sort of the kind of use cases they solve are very disparate. Like there's some libraries that are nice to use, but maybe don't support all parallelisms, so then you can't scale past a certain limit. There's other ones that maybe support everything, but don't support the architecture and like the sort of attention mechanisms you care about. There's other ones that are like way too complicated to use. You can't really iterate, like it's hard to understand. And now with RL, kind of like as Drew was talking about, like we see that in our kind of workflows as well. Like we're moving towards this world where we don't just have single chat models, we have these like agentic models that use tools. This adds like a new layer of complexity. Like how do you do generations well? Like how do you transfer like your huge model weights from your training GPUs to your inference GPUs efficiently and so on? And in that area especially, there's like nothing sort of, well, I shouldn't say nothing, but there are like very few sort of tools to use in open source. And at least for us, like because of all these issues, we've kind of had to build everything from scratch. And it's not a place that we necessarily want to be in. Like we're a pretty small post-training team. We'd love to just run experiments. But yeah, there just isn't anything like too great out there. And I think there's potentially an opportunity to kind of improve things.
That is a perfect segue to my last question for all of you. Lightning round. If you could have anything from PyTorch, or I guess if you want Llama, that's fine too. But if you could have anything from PyTorch, what would you want? Like your deepest, wish, whatever you could have. Maybe I'll start with Horace over here.
I think my requests are like pretty different from what most other people's requests are.
It's okay.
I think my requests are mostly at like the lowest level. So like things like kernel authoring, things like detensor, things like symmetric memory. Like Yeah, like I think when you're kind of at like a more like frontier type lab, it is kind of like you end up building like a lot of things yourself, or at the very least you're capable of building a lot of things yourself. And so a lot of the times the things that are useful are like the fundamental building blocks that are like reusable and are like solid that you can like reuse. And so those are kind of the things that.
Okay. Well, we'll keep working with you guys on that for sure. Groove?
Here's what I want, and then I'll backtrack into what PyTorch can give. Every digital surface that a human interacts with, their phone, their app, their browser in their laptop, their email, their calendar, everything is a tool call for an AI system. It's just an external memory mechanism. It's a way of communicating. It's a way of dealing with the world. And I want every digital surface to just be
I got a roadmap now.
A tool call away in, high throughput, high bandwidth.
So essentially a library of incredibly high performance environments. I mean, believe it or not, actually, I'm already building something like that. So okay, so we'll talk later. Okay, awesome. Sal, what can I do for you, sir?
We also want to scale models. So actually, I knew you were going to ask this question, so I asked my engineering team on Slack.
Yeah.
And their answer was the same as mine, and similar to Horace's. Like we want better sharded checkpointing, detensor, all the level stuff. I mean, when we train out models, we kind of have the PyTorch layer, and then you have a layer of other libraries, and then we write our own stuff either on the top or on the bottom or whatever. And the more of that stuff we can kind of get rid of and just have like PyTorch and what we want to customize, the better for us.
Okay. You good?
Yeah, for us, pretty similar, honestly. Like we want to be able to scale models, and I know PyTorch has been doing a lot of like awesome work here around different scalability methods, and like we're pretty excited about that. I guess more on the model side, like we would love a better tool calling model. At least like on the chat side, there are open source models out there that kind of close the gap with API models, but for tool calling, like the Quen, DeepSeek, like they're okay, but they're not like as good, and like having something better there would be amazing for us.
Cool.
Yeah, we would love to see just like plug and play, like to do RL at scale, like TorchTune. I know that like there are some like really amazing recent updates. It's getting kind of more and more keeping up with the state of the art like algorithms that's rolling out. It's quite interesting now we think about GRPO. It actually came from DeepSeek math. It's like like these algorithms we would like to kind of be able to have them available in TorchTune. That's a good
awesome. Yeah, I don't know if you caught, it was very subtle in Aparno's keynote this morning, but the little butterflies in there. So if you kind of like look for Monarch and PyTorch, you might see, Horace knows, maybe not everyone else knows, but yeah, you can imagine kind of like a God mode being able to scale. I think Yugen would be right up his alley. Because like I think we're just like fundamentally running out of ways to like aggregate enough power and GPUs in one place. And so if you can do this like across data centers and actually like literally scale up to like that level, which I think is like insane. It could be inference, could be post-training, could be obviously pre-training, but make it feel like you're kind of writing code locally and feel like natural, like you're sitting here on your Mac, like developing PyTorch locally. Like that's kind of like our objective. So yeah, it's really cool. Anyways, awesome. I think we're out of time. How about a round of applause for our panel? Thank you. Awesome. Thank you so much. This was a wonderful conversation. Yeah, I appreciate all the answers. Really diverse panel and so many different perspectives. Thank you again. I appreciate it. Cheers.
Thank you.
I think it's that way. OK. I'm supposed to like fill in the gaps while they take a bunch of chairs behind me away. OK, so I think we have a couple more talks right after this. So we have Tower Dev and we have Meta speaking. After that, we're going to have a short break. And then we're going to have Fiddler and Meta speak after that. And then we have another panel on the future of infra to close out the day. And then, of course, there's a happy hour, poster sessions, and some networking. So I want to introduce Serhi from Tower Dev as our next speaker. Thank you.
Please welcome to the stage Serhi Saukolenko from Tower.dev.
Hello and welcome to the iceberg age. I promise it's going to be better this time. Last time when we had the ice age, it didn't work out really well to the inhabitants of Earth, but it's going to be much better. Who of you, raise your hand, remember this case from a couple of years ago when 2 New York lawyers submitted a ChatGPT-generated court brief? I see a few of you raising the hand. What happened then? Well, our favorite chatbot generated an entire legal brief. It actually created case citations of non-existing legal cases. The court accepted this legal brief. The opposing counsel, of course, did the reference checks and discovered it was entirely fabricated. The lawyers were fined $5,000. The plaintiff lost the case. We ended up in a mess. Why did we end up in a mess? Well, this is a very simple diagram. You probably know how chatbots work or used to work 2 years ago. They used a large language model that was trained on a corpus of training data. And it took us months and months to train this model. So by the time the model was created, it was already dated. And secondly, the chatbots didn't really have the ability to check anything. They would accept your user input, and they would use a probabilistic technique to generate the output. And that was the answer to the user. Interestingly, the lawyers in our case did ask ChatGPT, are you sure these cases were real? And the chatbot didn't do what a human would do, which is going to a legal database like LexisNexis and actually type in the case numbers and check if they existed. Chatbot just replied, yes, they exist, and the lawyers relied on this information. Now, since then, the industry realized we need to complement the knowledge in LLMs with factual and recent info. So the new technique, and this is a little bit of a refresher of what you've all have heard in the first set of sessions here today, we still have our LLMs, and they receive user input, the questions that people want to ask. But instead of producing output immediately, they start a reasoning loop. And this reasoning loop begins calling out various tools. Some of them call external APIs, such as LexisNexis. Some of them will call enterprise analytical and operational databases. And the loop will continue until the LLM decides this is the final answer. I have enough information to create a final answer, at which point the output will be generated and stored together with a prompt in a thing called memory. So this is generally how these agents now work using tools. Who am I to be speaking to you so passionately about this topic? I've built data and AI systems previously at Databricks, Snowflake, and Google Cloud. I now run a company called Tower.dev, and we build Python platforms, portable Python platforms, to build pipelines, agents, and tools. So in this talk, we already motivated why it was a problem not having a reference database to check. Let's talk about solutions. So let's talk about enabling agents with enterprise data that they can cross-check. We'll talk about trends in the world of analytics. There's a big trend, and it's also the namesake of the stock. Apache Iceberg is this big new trend for analytical storage. We'll look at an architecture of an agentic platform that provides easy access to analytical data to agents, and we'll look into the future as well. So how do we complement LLMs with recent and factual info? Tim Scarl, the host of ML Street Talk, has recently said something that really resonated with me. And effectively, he said, LLMs are databases. Now, I'm a database geek, and if you show me a brick, I will call it a database. I'll find a way to explain why it's a database. But it's actually making sense. Think about the training process of a LLM. You get a corpus of data, and let's say in Llama's 4's case, it was 30 trillion words, which is approximately 150 terabytes of data. We've got enough meta folks here to confirm or disprove whether it was 150 terabytes or maybe 200. But it took us 9 months to train this model. And so by the end of this training process, we ended up with a set of files that were less than a terabyte in size. So it was a 200x compression of our training set into this binary output. And everyone who knows information theory, or at least have read a little bit about information theory, a 200x compression of data immediately leads, it's lossy. You cannot recover the information that went into this process one-to-one. We are still OK accepting LLMs as databases because they trick us into believing they're smart and they can create creative responses. So we're OK with this lossy compression. Now, on the other hand, if you look at the world of analytical data lakes or operational databases, we are dealing with a much larger sets of data. Some customers have tens, 50, 100. I know customers, large banks, who have 1,000 petabytes of data. Some of it's still sitting on tapes. And the recency of data is measured in an hour to a day in the analytical case, or maybe a couple of milliseconds in the operational database case. So it's very recent data. And the compression, there's pretty much no data compression per se. But what you get into your database, you can get out by querying it. So there's compression, but it's not lossy. That's what I meant to say. And because of that, query results are deterministic and they're factual. So it's kind of makes sense to be able to try to use both LLMs with your operational analytical data stores. So some of us have been asking the question, can't we store everything in one place? Wouldn't it be much more convenient to store everything in one place? Well, disregarding the fact that LLMs at inference time require an entire different set of infrastructure, mostly in memory, versus operational analytical stores, have you ever tried to replace a database, a popular database, anywhere? You're looking right now at a chart from DB Engine's rankings. That's a site where database geeks usually go to brag about popularity of their favorite databases. And so what you notice there is that the top 3 database technologies for the last 10 years have been Oracle, MySQL, and SQL Server. This is something that our parents were using. And it's remained, sorry, I used to work for Microsoft. It's OK, it's all right. And this top 3 rankings remained pretty much intact over the last 10 years. And the hot new technology, hot in quotation marks, Postgres, that just recently received a bunch of investments from both Databricks and Snowflake, it took them almost 10 years just to get to position 4. And the newest kids on the block, the Snowflakes and Databrickses, they've been growing faster, but this is logarithmic scale. So actually, the popularity between Snowflake and an Oracle is still 10x. It will take you ages to even consider the idea of replacing a database with something else. So I think this means we have to deal with the fact that LLMs as a database will have to coexist with analytical and operational databases. And we need to figure out a way to make it work all together for agents. So let's look at what's going on in the analytical world, because this is important. There are trends in the analytical data space that will influence how agents will get access to that data. And the big trend in the analytical world is Apache Iceberg. Maybe another raise of hand who has heard about Apache Iceberg as an open table format. Some of you, maybe not everyone. So Iceberg is a standard. It defines a way to store relational tables. And it's actually a pretty simple standard that says there shall be a tree of files, and there are 3 types of files. And these files kind of cross-link to each other. There's a root of this hierarchy. Every table has a root file, and then it points to a bunch of metadata files until it reaches the data layer. Now, Apache Iceberg is not a database engine that you can buy. You cannot buy Iceberg. You can buy a technology that supports this standard. But it describes or specifies a very important concept of a metadata catalog. And this will be your single point of failure in Apache Iceberg-oriented storage. This is the critical piece that binds everything together, because it serves only one purpose, which is pointing to the root of a metadata file that initiates the tree for each table. So its responsibilities are small, but it's super critical. Now, why are customers, small and large, migrating to Iceberg? And to understand this, let's look at what was happening, let's say, 5 years ago. 5 years ago, customers would use a combination of different database technologies. They would use maybe a Databricks, a Snowflake, and a Fabric, and some other database engines. And these database engines were, of course, all cloud-based, all distributed processing, all separation of data and compute, shuffle everywhere, awesome stuff. But they were storing tables in their proprietary table format. Now, underneath, they might have used open file formats, such as Parquet and Avro, but this middle layer that defined which data files corresponded to which tables, they were all proprietary. So I used to work for Snowflake, and part of my job was to creating storage optimization technologies to make search really fast on that metadata layer. It was very sophisticated, very smartly written, but it was proprietary. And if you wanted to move data between silos, and let's admit, we used to use these database engines for different tasks. We use Snowflake for analytical processing, and we use Databricks for ML and data engineering, and we used Fabric if you were a Microsoft shop. So to move data around, we had to employ ETL processes, which were super expensive. There are some estimates that 40% of data processing costs in companies was actually spent on ETL. Well, customers are not entirely naive and dumb, so they rebelled. And one of these large customers, Netflix, open sourced a technology that later became known as Apache Iceberg. And since then, this stack actually received a very significant adoption across both enterprises and startups and mid-sized companies. You'll see in this graph, the Iceberg is represented by the red chart. It is experiencing a hockey stick growth pattern. Now, what's important for agents when they access analytical data stores? So hopefully I was able to motivate agents need to access analytical data stores. It's important. It makes them grounded in truth. But what do we need to do to make it work for agents? And I would say there are two important considerations. And I had to really, I started with a long list of considerations. I ended up with these two most important ones. I think throughput will be one critical consideration. And to understand this, think about you typing in a question or tasking an agent to do some research and find some anomalies in your sales data. So what will this agent do? They will run a bunch of analytical queries, slicing your data by different dimensions. Now, a human analyst, if you gave this task to a human analyst, they would actually stop after a while because they need to go home and have dinner. They don't have the mental capacity to run 1,000 queries. Agents have unlimited time and hopefully resources, so they can continue slicing and dicing your data, looking for these patterns. Therefore, they will execute 100 times more queries. And also, an important reason, agents don't have yet that knowledge, that institutional knowledge of interesting insights in your enterprise data, as human analysts do. So they don't really know how to stop and when to stop until they find an interesting anomaly. Because of these factors, I think throughput is a huge consideration for analytical workloads when they're used by agents, and we need to find a technology that enables high scalability. The other important consideration is data security. Because if you also think about this, if you were a human user of an agentic system, you gave the agent a task, you don't want the agent to be using PII information if they didn't necessarily need it to accomplish this task. You don't want them to access data sets that are not necessary for accomplishing the goal. So things like column masking and row filters will become important in an agentic world when they start using analytical data stores. How does Iceberg measure up for these requirements? Read throughput is amazing. In Iceberg, it relies on the huge scalability of underlying storage systems, such as S3 and Azure Blob and GCP or GCS. The write throughput is not great. The community is working on it, but your agents will probably also not be writing transactional data directly into your analytical data store. So that's not very important, the write throughput. In terms of data security, it's also work in progress. There are some catalogs that allow you to manage better your column masking policies and your row filter policies. I will call out maybe a few catalogs here, Lake Keeper and Unity Catalog. And there are some emerging standards in the world of open, fine-grained access controls, OpenFGA, and role-based security are back. Now, let's look at a platform that allows agents to easily access analytical data. I'm working on Tower, and Tower is a serverless platform for building pipelines, agents, and tools used by these agents. We provide a couple of building blocks, tables, models, catalogs. We also have horizontal services. We call them beams, team collaboration, orchestration, observability. And in Tower, everything revolves around applications or apps. And you can build 3 types of apps. You can build a traditional transformation pipeline, or you can build tools and agents that use these tools. We rely on partnerships with open source technology to libraries such as DLT Hub and DuckDB and Polars to implement these functionalities. So when you want to build a platform or an agent with Tower, I would recommend using a great agentic framework. I personally like LangChain. And when you use LangChain with building an agent on Tower, you would typically go through the steps of declaring tools. And the textual descriptions will become super important of these tools, because this is how the LLM will know whether to call your tool or not. You define things like memory. You choose a model that you want to use for in your agent. You pick a prompt. The prompt is also super important. There are some standard prompts that you can use, such as React. Then you create the agent, and then you collect the input from the user, and you invoke the agent on this input. I have a demo that will show you how all of this works together. In this demo, I will actually build a data engineering system agent. It's not something that will interface with users directly. You give this agent the task of maintaining a lakehouse table. So this table is stored in Iceberg in a lakehouse, and its purpose is to store data about stock tickers. We'll see it in the demo. And so this agent has 2 tools available to it. It has a tool that is able to check if data is already available in the table. And it has a tool that is calling an external API and downloads the data and stores it into the table. So using these 2 tools, the agent can reason whether they need to retrieve data or if they can skip a particular stock ticker. What's critical, and I wanted to show you how all of this works, how agents actually are able to reason, here's an example of a system prompt. It follows the React architecture. You'll see the placeholder in this system prompt, tools and tool names. This is how you pass the descriptions of your tools to the LLM to start the reasoning process. There's a template to which the agent will run the reasoning through. And here are some descriptions of the 2 tools I mentioned before, the one that checks availability of the data and the one that pulls the data from an external API. Now let's look at the demo of an agent developed with LangChain and running in Tower. And so we'll start by importing Tower and some additional libraries, such as Polars and LangChain. We'll define the function that the tool will use to, this one will actually pull the data, and it starts another Tower application to perform its task. We'll define our data getter, our data downloader, give it a good description. We'll then define a new function that checks the availability of data, and it uses the Tower's Iceberg Tables API to do this quickly. And we'll again define the purpose of this tool so that we can pass it to our agent. And then we'll reach the stage where we'll create the tools, the LLM, the system prompt, create the agent, pass all of the parameters to it, and then we'll collect a user prompt, the description of the goal of the agent, and we'll initiate the invocation. Now, there's a concept in Tower of a Tower file. This is basically your metadata about the application. You have to specify or tell us 5 things. What is the name? What is the description of this app? What are the parameters? And here I will add another stock ticker for the agent to process. So we'll now deal with Amazon, both with Amazon and Microsoft. I'll deploy this tool to Tower. I will start the run of the agent. And so now we are in the web UI. The agent is running. Let's quickly look at the logs of this particular agent run. After the installation of libraries, we'll start getting the reasoning flow of the agents of the first line entering the chain. So it will call the first tool, check the data availability for one ticker, and it will figure out, oh, I already have data for Amazon, so let's not pull it again. Now let's call the availability checker for Microsoft. Oh, I actually do need to pull data for Microsoft because I don't have it in my lakehouse table. So I will get my downloader tool and execute it. And this will run as a separate application in Tower. And at the end, the final answer will arrive, and the agent is happy. It synchronized the data in my lakehouse table with the task that I gave it. So with this, I wanted to maybe talk about a few additional things you can build on Tower. We have a customer, for example, Cogni. They're building a knowledge graph system that implements AI memory, and they use Tower for ETL tasks, onboarding documents into a lakehouse table, as well as for serving search requests, again, the knowledge graph. Let's maybe summarize what we learned today. Hopefully, I was able to show you how by doing three things, by complementing LLMs with up-to-date and factual data in LLMs, and by paying attention to the trends in the analytical world and finding ways to integrate with Iceberg, and by using agentic frameworks, we can address the fails, chatbot fails of the past. What do we think will happen in the future? We think the future is bright for agents. We think agents will eventually run everywhere, in public clouds, in your cloud account, on your laptop. And the adoption blockers that were used to be true in the past, they're also being addressed. OSS models are becoming as accurate, or if not better, than proprietary models. Model sizes are being addressed. You can get now, through various techniques such as quantization and distillation, you can get model sizes down to a size that runs on your local hardware. And local hardware itself is improving. Apple and NVIDIA are releasing desktop-based machines that you can basically run a full-scale DeepSeek R1 on them. The one remaining adoption blocker, and this is something that we are working on, are the differences in GPU stacks. There are still differences locally, on premises, and in the cloud. Folks have tried different techniques to address these differences. They try to package things into Docker containers. There are reasons why it doesn't really work on, let's say, Mac GPUs and Docker and PyTorch. That combination just doesn't work. They try to put consumer hardware in the clouds and build inference servers out of them, also not super scalable. Tower is working on a different solution. I think it's a little bit more scalable. We are working on portable Python runtimes that give you virtual Python environments and actually works pretty well. If you would like to get in touch with me after this talk, would love to chat with you with any questions. We do actually have a couple of minutes for questions, if you would like to ask me. I'm the first talk who is doing a live Q&A after the talk. So if you would like to ask me a question, go ahead.
Hi there, Sergey. Thank you all for submitting questions through the QR code. Unfortunately, we only have time for one question because of time constraints today. And somebody wanted to ask this question. Can agents learn from previous queries and optimize their reasoning across time?
They definitely can. Remember one of the first slides I had where there was a memory system where you store both the prompt and the output. This is how agents can learn from previous interactions. If you want to learn more about this, happy to answer after the talk. All right, I think we'll call it a day. Thank you.
Please welcome to the stage Kan Lin and Uday Ramesh Savagaankar from Meta.
Meta operates a large-scale data warehouse. In the era of AI agents, how do we evolve its data access? My name is Ken, software engineer at Meta. Today, with my colleague Uday, we'll talk about how Meta builds agentic system for its warehouse data access and how such an approach helps us to scale out and streamline the process. So Meta's offline data system spans across data warehousing, stream data processing, and service monitoring and observability. Collectively, they support use cases across analytics, stream data processing, AI, and machine learning. And it's also important upstream and of systems like Gen AI. And with the rise of AI and AI agents, we see the potential to use that to help us improve the data warehouse access. So security remains paramount in our data infrastructure.
Yeah, that's a really excellent point, Ken. At Meta scale, we have billions of users. Some of this data is their private data. And at the same time, we have hundreds of teams that are owning this data, managing access to this data. And we have tens of thousands of engineers that are accessing this data to build the products and services that our users like to use. Ensuring security of data in such a dynamic environment is not only important, but it is also very challenging. And in the rest of this talk, we are going to talk about how we are using agents to address this access management challenge.
So traditionally, we scale out warehouse data access by organizing warehouse into a hierarchical structure. So if we start from the bottom, and those are tables, and the data pipelines producing them, and dashboards consuming them. We organize those assets into projects and managed by uncles. And those projects are rolled up to teams and all the way to the organization hierarchy. And then we overlay roles, as in role-based access control, and over this hierarchy, and together with other dimensions, such as data semantics. However, with AI, the efficient access becomes more important, and the scale of the warehouse continues to grow, and the complexity of the access pattern keeps increasing.
So to understand the complexity, it helps to view our data warehouse as a graph. Each node in this graph is an asset, like a table or a column. And each edge in this graph is a data processing activity, like interactively accessing the data using interactive tools or running a data processing pipeline and things like that. In the past, when most of the analytics was rule-driven, this graph was heavily partitioned and accesses were very localized. If you want to know where the data that you need is, go and ask your colleagues or go look at their code. Similarly, if someone requested access to the data, should you approve it? Well, look them up in the org chart. Are they working on a team that is related to your team? Approve it. But AI is changing the game. With AI, the trend is more and more to pull cross-domain data to make into unified pipelines. And in this situation, both finding the data, requesting access to that data, and managing access to that data becomes extremely challenging. So to address this challenge that is created by AI, we have decided to lean onto AI itself.
As we can see, the system complexity keeps increasing, both in size and access patterns. And also, humans and agents increasingly work together across domains. And so those pose challenges to the system. But as Uday shared, that we also see the potential of AI and AI agents to be the solution. And while warehouse was originally designed for services and humans, and how do we evolve it to be an agentic solution and to support the data access? And also at Meta, people use data tools to access data and manage access. And we need to take a product-oriented approach and integrate the agentic experience into data tools and people's workflows.
So before we dive deeper into any solution, let us just look at the key, focus on some key concepts. We have two personas. On the left-hand side, we have the data user, and on the right-hand side, we have the data owner. The job of the data user is to access the data and build the products, pipelines, and whatever is needed. Job of the data owner is to manage access to the data and safeguard the data. Now, to mimic this interaction, our agentic solution also uses two agents. On the left-hand side, we have a data user agent, and on the right-hand side, we have the data owner agent. The data user agent is responsible for discovering the data, putting together context, and making access request. And data owner agent is responsible for evaluating that request based on context about the data itself, and either approving or denying this request. Essentially, these agents are acting as negotiators for these two, their respective personas.
So in today's talk, and we'll share how we model the problem as a multi-agent problem, and how we build a user and owner agent. And we also talk about how we evolve warehouse for agents to use. And then we'll do a deep dive of an end-to-end use case. We call that a partial data preview. And then we'll share the takeaways. So as Uday shared, that we built the data user agent to help the data user to get access to data. And we also built a data owner agent to help data owner to manage access. And then the two agents also negotiate together and to streamline the process as needed. And we intentionally separate out the two. And for one reason is to decompose the problem. And the second is that to give each of them their own focus. Let's take a closer look at the data user agent. It's not a monolithic agent. It actually consists of sub-agents. So the first sub-agent suggests alternatives to people. So imagine like a data user comes in and uses a data tool to access data and get blocked by the security controls. And so there are usually like options available that can be an alternative table, which is not restricted or less restricted, right? They can actually update their query to remove the sensitive columns, or they can use some curated data analysis instead of writing their own. However, in the past, those information are either tribal knowledge or like spread across documents and wikis and past tasks. And with large language model and agent, and we're able to synthesize those information and then use the data user agent to use that information and guide the data user along the way. And the second sub-agent enables low-risk data exploration. If we think about data warehouse, and many tables have large volume of data, but in many cases, people only need a tiny fraction of the data, and especially at the early stage of data exploration. And how do we enable such access in a low-risk, in a task-specific, context-aware way? And that's very important. And Uday will do a deep dive later on. And the third sub-agent assists the data user to request permission and negotiate with the data owner agent. We remain human oversight, strong human oversight, and throughout the process. But we do believe that with time and maturing of those agents, they operate increasingly autonomously. Data owner agent also has two sub-agents. The first is supports the security operation. So you can think of it as a junior engineer joining the team, and they are given a SOP, standard operating procedure, and which is synthesized from the team's data practice in wikis, rules, and documentation. And then they use that to do the first triage of the incoming permission requests. And the second is for access management. You can think of as a enhanced version of the role mapping process, allow us to better leverage semantics and content. So as previously mentioned, we organize warehouse into a hierarchical structure to scale out the access management. But at the time of agents, and how do we evolve that? Large language model and agents speak in the language of text. So in order to better utilize that in agents, you can think of the hierarchical structure actually naturally mapped to a folder structure. And the tables are resources in this structure, and also the hierarchical structure naturally mapped to the folders. And then this provides a very nice read-only summarized view of the warehouse. And also, this structure is not just for data assets, right? The SOP, as we mentioned earlier, those are basically synthesis of the documentation and data practice. And they are represented in this structure, and we can use that to both for data user agent to guide users, and also for data owner agent to help manage access. And besides like model the inputs to the agents, we also need to think about what information to fit into the agents. And this is about the context management. So we divide that into 3 scenarios. The first one we call automatic context. So imagine someone come to access data and get blocked. And then the system knows exactly who is accessing what and what blocks them. So the context is known exactly. And the second we call static context. So in this case, that people can basically, data user or user agent can choose what to focus on, and usually a project. And also, it can be like the expansion from the automatic context. So for example, if people are blocked by certain data access, and then we can search the alternatives within the same projects. And the third one, we call that dynamic context. So this allows the agents to basically further filter the resources by dynamic attributes, such as data semantics. And besides context management, and there is an important part of the access management is we call that business needs. This is basically the why or what drives people's data access. And we model that we call that intention. We model that in 2 ways. The first one, we call that explicit intention. So in this case, data user basically tells us what they are working on. So imagine someone comes in to use data tools to access data, and then through their workflow, they assume a role and then perform the data access. And once a role is assumed, and then the context of that role is carried over and is available to the agent. And the second, we call that implicit intention. Not all the intention can be modeled this way, because, and this is implicit intention comes in. So imagine someone was woken up during midnight, and they are like, because of a pipeline failure, right? So there is a high likelihood the subsequent data access is related to that activity or event. So in this case, the intent can be derived from the events and activities in the short time window in the past, short window in the past. So with that, I'll hand over to Uday to do a deep dive.
Thanks, Ken. So now I'll focus on something called partial data preview, or PDP, as we call it. Before going deeper, just to recap, we have data users, and we have data owners, and we have user agent and owner agent that help them negotiate the access. But how does this apply to a real-life scenario? That's the main question. In a real-life scenario, like a data workflow, the data workflow starts with data discovery, where the data is, followed by data exploration, followed by data use. In the data exploration phase, the user is looking at small sample of the data to decide whether the data is any good for their use case, like whether the data has the format that they need, whether the data is actually what the description says it is, and things like that. This phase is where we typically see most friction, because at this phase, the users are forced to apply for data access even before they know whether the data is of any good to them. And from data owners' standpoint, they are forced to field all of these large volume of requests from users that may not even end up using this data. And this is why the PDP solution that we have built focuses on this phase of the data lifecycle. So the PDP solution relies on 4 key capabilities. First of all, the solution is extremely context-driven. There is user context, and then there is owner context. Like the user context is the job role and things like that. The owner context is sensitivity of data and other things. But the context is extremely query sensitive. And because of that, the second key capability that we rely on is a fine-grained access control, query-level access control. Each query is different. Some queries aggregate data, some queries don't. Some queries access sensitive columns, some queries don't. And because of that, the access control decision needs to be made on a query-by-query basis, and that is our second key capability. Third key capability is we implement what is called, what we call data access budget. Remember, we are focusing on the data exploration phase, and in this phase, the user is not looking to get access to hundreds of millions of rows. They just want to look at what is going on. And because of that, we allocate a small data access budget to each user, and that budget gets refreshed on a daily basis. Then the fourth capability is rule-based safeguards. No AI is infallible, and we do not want these AIs to go off the rails. And because of that, there are some final rules-based guardrails that keep the agents on tracks. Now, with that background, let us look at exactly how these solutions, the PDP solution works. On the left-hand side, we have, in the blue box, we have the user data agent. And this agent is responsible for making the data access request and put together the context. To do this, this agent first taps into user activities tool. In the user activities tool, it gets information such as like what kind of code the user is working on. Are there any saves that are going on that the user is responding to? What are the tasks that are assigned to this user, and things like that. The user agent also taps into user's profile to figure out where in the org hierarchy the user sits, what their team is working on, and things like that. It collects all of this information and builds a justification for the access request and presents that request to the data owner agent, which is the blue box on the right-hand side. The data owner agent takes this context and builds its own additional context, like what is the query doing? Is the query doing any aggregation? Is the query accessing any sensitive columns? What are the standard operating procedures on those columns? And things like that. And based on all of this context, the data owner agent makes a recommendation. This is just a recommendation. This is not a final decision. This recommendation is then subjected to rule-based engine to make the final decision, whether to allow the access or not. Now, none of the, or at least majority of these key technologies are not new. Like user activity tools have existed forever. Query analysis engines have been used for query planning, query optimization, and things like that. What is novel in our solution is we are using the knowledge distillation capabilities of LLM to distill out structured insights from unstructured data. And then we are using those insights to make a recommendation and finally the ultimate decision. OK, so you might say, this all makes sense, but is it any good? Does it actually work? That's the key question. Of course, we also asked that question. To answer this question, we built a historical data set. Essentially, the data set was based on the data access requests that various users made, the justifications they provided, and the decisions that the data owners made on those access requests, and the reasons the data owners gave for either accepting or rejecting the access. And then we simulated our PDP system on this historical data set. What we found out was our system's rejection recall is 100%. That means if a human user rejected the data access request, our system definitely rejected that access request. But our acceptance recall was lower. And this is by design, because we want our system to be better safe than sorry. Because if our system rejects the data access, the user can always go back and manually apply for data access, and then some human being can review that access and grant that. But by approving a significant majority of the access requests automatically, our system is lowering the load, reducing the friction for the user and lowering the load on the data owner. No AI is complete without a feedback loop, and we are also taking the feedback loop very seriously. And to this end, every single query that is subjected to PDP, we log it. We log all of the context around it. We log the decisions and things like that. And we use all of this in both online and offline analysis to keep monitoring the performance of our system and detect any drift in its performance and things like that. We are also looking into taking this data and feeding that back into fine-tuning the model that we are using so that the model can keep making better and better decisions over time. And over time, we could reduce the amount of oversight we have to provide to this model. With that, we will leave you with some closing remarks.
Yeah. Just a recap what we just talked. And we talk about how we model the warehouse access management problem as a multi-agent problem and build the data user and owner agent. And we talk about how we evolve the warehouse infrastructure and to support such agents and how we model context and intention. And we also do a deep dive and about the end-to-end use case of partial data preview. So what's next?
Well, the journey is just begun. We are not at all done. First and foremost, we have to work on agentic collaboration. So right now, we are only looking at the agents that are essentially making data access requests or data approvals on behalf of the users. But we have to start looking at agents that are accessing data on behalf of users or in an autonomous fashion. And that is going to explode the volume of requests, performance requirements, and everything. And to do this, we also have to evolve our infrastructure and use more standardized ways for managing the interactions. And finally, we have to keep working on evaluation, feedback loop, and continuous improvement to the system. With that, that's the end of our talk, and we have time for a couple of questions.
Excellent job, Cam and Uday. Thank you so much. So we only have time for a couple of questions that you all submitted via the QR code. So Cam and Uday, people want to know, what are the primary benefits of using a multi-agent system for data access? And in general, how does this new system improve efficiency?
Yeah, maybe I can take first look at it. So as we shared, right, we build it as a multi-agent system and instead of monolithic agent for multiple reasons. So the first is that it helps us decompose the problem, because with the engineering process, that each agent can become quite complex. The prompt crafted by encoding the subject matter expertise into the prompt, and the tools we curated and fed into that. So by decomposing them into multiple agents, we can decompose the problem and into smaller parts. And so this allows us to build a more modular system. And also from the engineering team perspective, that we have not a large, but a sizable team and working on this. And this allows basically different engineering groups and to work independently with clear interface. And the third reason is, as we shared earlier, that the user agent and owner agent, they actually serve different personas, right? So from product perspective, that each of them actually interface with user and owner. So yeah, and then on the efficiency side, maybe I can talk about this basically suggesting alternatives, right? So for example, in the past, it's actually very hard for people to find the relevant information, like about, hey, what they can redirect their access to. And but with the synthesizer optimization and use agent to guide people, and that help us for our A/B testing that have a very sizable job of people actually not to request permission, then which means that their access needs is actually supported by the alternatives, and which is much more efficient.
Yeah, just to add to what Can said, another reason for decomposing the problem into multiple agents is to enforce principle of least privilege, because these agents are accessing sensitive information. They are looking into users' activities. They are looking into the user's profile. They have the ability to grant access and things like that. And because of that, we do not want we want to manage the blast radius if one of these agents goes rogue because of prompt injection or something like that. And just as a good security practice, we have decided to partition the agents and give them only the access that they need.
Awesome. Thank you very much. I think we're done for now. Appreciate it.
Okay. Thank you.
Thanks.
chemistry is fire. Conversation is right. If you say tonight, baby, I might let you say all of me. Want you here, need your mind in these sheets. Completely intertwined in our minds, yeah. Tell your future like a psychic. Baby, you gon' end up right in my bed. Chemistry is science. I could play it cool, but I'd be lying. Read you like a psychic. I'ma tell you something, you gon' like it. Chemistry is science. Better than what you was fantasizing. Different kind of blue.
Please welcome to the stage Krishna Gada from Fiddler.
Hello, everyone. How many of you are building AI agents today? A show of hands. OK, many of you. How many of you can say that you actually trust your AI agents when they're deployed to production 100%? Maybe some. So I'm Krishna Gade. I'm the founder CEO of Fiddler AI. We are a leading AI observability startup in the Bay Area. I'm here to talk to you about agentic observability, why it's really important to build reliable, safe, and trustworthy LLM applications. Let's dive in. So the nature of software application, as we know, is changing today, right? For the past many decades, we're used to building deterministic software applications, largely rule-based, logic-based, more static in their behavior. But now, with the advent of AI and agents, you're entering into this world of non-deterministic applications that are dynamic, highly data-dependent, and basically directed by models. And the topic of this conversation today is that you need to think about observability from a first principles perspective to ensure these applications are running properly in production. Before we dive in, I know you've heard a lot of talks today about agents and workflows, but a brief overview, right? What is an agent? Agent is an autonomous system that is solving a complex task, basically with the help of a large language model, calling different tools. And you can construct workflows of agents, in many different ways. Our friends at Anthropic have written a great blog about how the many types of agentic workflows teams are building. A few of them many are in production today. For example, we see a lot of prompt chaining workflows where people are trying to build natural language experiences for business intelligence, for example, where you can take a human readable text, convert into a SQL query, federate like a database request, retrieve the structured data, and summarize for a human readable response. Or you may have like a routing workflow where there's a supervisor agent that's calling many other sub-agents in distilling the task that it is trying to solve. So the reality is that we are moving from a single LLM, like a prompt-in, response-out model, to like a multi-step, goal-oriented, workflow model, where these agents can plan actually what to work on, and reflect upon the outcomes that they're producing, right? And so what happens here is when you're building these complex agent workflows, there is an inherent black box nature to it. You want to know why something is working, why maybe like an outcome that you have seen is not the right outcome. Was it like a tool call issue? Was it a model hallucination that's happening behind the scenes? And this is where we need to think about monitoring. Today, when you think about monitoring, a lot of traditional monitoring systems do not work for these. Most of the agents today are single agent workflows, that take a prompt and get a response out, your RAG applications, right? But the future is going to be these multitasking, multi-step agentic workflows where there's a supervisor that is taking a prompt and context and essentially coming up with a plan and delegating to multiple workers downstream. So you can see a situation like what happened in the traditional software of microservices kind of replicate here with many, many agents coming together and collaborating and sort of solving a business problem. And if you kind of think about what are the observability challenges here, right? So you see that if you have a multitasking or multi-agent workflow, you have a problem of understanding how a given application is working end-to-end, what is a given session doing, what is the user journey like, and how are the different agents working. Were there any tool call failures, model hallucinations that are happening? What is actually, can you trace through a user session and know what happened? Can you replay it back? These are all the challenges that traditional monitoring systems don't sort of solve. And this is where I'd like to argue that we are entering into this world of APM 2.0. For those of you, APM stood for Application Performance Management. Many of us use these APM tools today in production for monitoring our traditional software. But with the advent of agents and models, you have to rethink this. I'd like to call APM 2.0 as this agentic performance management. So what exactly is APM 2.0? So you have this new new kind of application that we talked about that we are all building. It basically constitutes of agents, models, and data all coming together. And you're building these compound AI workflows. I was listening to a talk by an earlier speaker, Tower, where you're extracting data from third-party databases. You're building these conversational assistants or agentic workflows that simplify these tasks. So you're standing up these new kind of applications, and now you need to think about monitoring them properly. So in order to think about APM 2.0, I'd like to consider two worlds that can be married together to solve this problem. One is the traditional APM world, which is a well-studied problem that we know that can help us measure response times, availability, throughput. And then there is the model performance management world that helps us understand models, model drift, hallucinations. And so I'd like to argue that agentic performance management fuses these two worlds. It brings the principles of APM and MPM into this new world of agentic performance management. So what does it look like? So you'll have the APM metrics. For example, was the database that you called from an agentic workflow available? What was the latency of the response? What is the throughput? How much traffic is going through the systems? All of those things. And then how is the model performing? Because agents are largely backed by models. Are models hallucinating? Is there a drift happening in intent or prompts? And then measuring all of those things and bringing them so that you can do a hierarchical visibility. Because agents are these multi-step workflows, so you can actually see what happened through different stages of the workflow, how the task was executed, and create a system of intelligence. And this is the world that we are entering. So what this agentic performance management will give you is not just eyeballing the outcomes of agents, but gives you the visibility into why, right? What happened. And we'll briefly dive into how to build a system like this and learnings from our journey of building an agentic performance management system. So the new way of agentic observability starts with some fundamentally new principles. So there's an interesting concept called reflection, that agents are backed by these large language models. So they can inherently reason about a given task, right? You can actually rely upon these foundation models as judges to figure out, self-reflect and self-critique whether the action that was taken was actually correct action or not. This is a new thing that traditional monitoring tools or traditional applications do not do. The other thing is agents, unlike single-shot LLMs, call tools. So being able to monitor tool usage is going to be important. Being able to know if you're calling the right tools in the first place, are you parsing the tool outputs correctly is important. Agents come up with plans of actions. So being able to know if there are redundant steps that agentic workflows are coming up with is going to be important. And how they're collaborating is going to be important. So if you think about the anatomy of an observed agent, from a philosophy perspective, right? So what goes into an agentic workflow? It starts with the context, the prompt. In a multi-turn system, you have to preserve memory and state. If you forget state and provide a different answer, then it's not going to be good. So you need to be able to track that. And then how a plan gets generated, how is it actually executing, what tool calls are happening behind the scenes, and then you take advantage of reflection. Reflection could also be human escalated reflection. It could be the LLM as a judge, or essentially evaluations that are coming up with how good the response is. And then you can do live intervention, where with the help of guardrails and fallback, can you actually course correct the agentic workflow to do the right thing and maintain the policy? A simple example here is, think about, let's say I'm trying to build a LangGraph application, that queries Zendesk tickets and provides, answers for a human that's asking some sort of customer service, right? Now, anything can go wrong here. You can actually call the wrong API. You can actually get an incorrect response. Maybe the response that you are actually sending violates the company policy. So all of this needs to be monitored from the prompt to the execution to the API calls to the response that was extracted, and then eventually whether the policy of the company is being maintained or not. And that's basically what I think is essentially constitutes observability. So then what are the metrics that we need to track here? If you think about, there are new kinds of metrics. These metrics are not what you get from a traditional APM or an MLOps observability tool. Here is an opportunity for you to think about how many times reflection was invoked in this agentic workflow. That gives you an insight whether there is any misaligned prompts or prompts that are difficult for this agentic workflow to process, or how many times tool execution mistakes happen. Were the APIs called correctly? Were there any misparsed outputs? Were there any issues with the planning of the workflow? Did you see any redundant steps in the workflow? And then basically, what was the handoff between different sub-agents? Was the data integrity being maintained? And then finally, are the guardrails invoked properly? Are there any rule violations happening? So many of these things we do not monitor today for traditional software. And that's what you need to sort of do. So our approach at Fiddler is to instrument this, right? So what we have built is a system that can actually wrap around your favorite application framework of choice. It could be LangGraph, Crew AI, whatever. And you can basically instrument all of this. Instrument every decision, all the inputs and outputs at every stage of the workflow, and then log all of these to a centralized system with all the trace IDs, so you can then do better root cause analysis, where you can actually detect hallucinations in responses, you can detect drift issues, you can detect tool call failures, and be able to know what happened, and you can replay the entire session if you need to be able to support an auditing aspect of it. And so in reality, the system looks like this, right? Once you instrument the application, you then send all of the logs to an observability system that runs all of this data against these type of trust models, language models that are used as a judge that create metrics like faithfulness of response, safety issues, is there a PII exposure here, is there a policy violation happening, and then provide these metrics for a guardrails invocation or a real-time monitoring that you can then leverage to monitor the full agentic app. So going back to that previous example, in the case of this travel application, you would see a sort of a hierarchical visibility view, where that travel application that is making calls to essentially an airline agent or a hotel booking agent, how is it working? What was actually the information passed through that workflow? Where are the failure points? And you can then monitor each of these sessions, aggregate at each of these node level to see at an aggregate level which tasks are failing, and then also pinpoint from a granular level, what is failing and why that has failed. So what I'd like to argue is, when you think about production readiness, you need to think about an observable agent. Right? You need to think about, are you able to explain the chain? Are you able to explain what happened with your agentic workflow? Are you able to go beyond metrics, just beyond simple evals of your LLM models to being able to know if the policy that you've implemented is being compliant? Are you able to track audit trails? Are you able to replay back your sort of what happened with the system? And then the insights that you're generating, are they consumable by not just the AI engineers that are developing the agentic workflows, but also sort of the compliance teams or the security teams? So with that, I would like to sort of share a few hot takes, right? So number one is logs and metrics. The way that we thought about in the traditional APM world, I don't think apply to this new agentic performance management. There is this new world that we are entering where you need runtime semantic tracing, where you need to be able to know what's happening through the agentic workflow, how the data is flowing, what is happening to the various external calls, and being able to know that. And so there is this concept, what I call reflection, that you can take advantage of. So in many ways, agentic observability is not an externalized watchdog that is watching an agentic workflow happen, but it is a co-observer. So you can take advantage of these reasoning models that have the cognitive process, right, that can tell you, whether the outcome was correctly done or not, and essentially use those insights to build this observability, build all these metrics. And finally, agentic failures are not necessarily bugs, right? You essentially, and many times these are misalignment issues. It's almost like, as AI becomes more and more intelligent, it's almost like how you control and sort of supervise humans in many ways. How do you enforce alignment? And so with the advent of guardrails, and what you can do is you can do live intervention. You can have an agentic workflow like I showed in that feedback loop, you can have guardrails and fallback triggers that get invoked whenever there is a policy violation happening. And so you can actually intervene with an observability system, which more or less in the traditional APM world has been a passive system monitoring servers and applications. In this case, it can be much more of an active system that can take part in the application workflow and do live intervention. So with that, I'd like to sort of give a call to action. If you're thinking about deploying AI agentic applications, think about observability from a first principles. Think about that life cycle where you're able to ingest the prompts, instrument the tool calls, look at the model hallucinations, invoke guardrails, so that you actually are able to build these almost self-healing agentic workflows for your customers. If you have any questions on this, I'd like to answer. But thank you so much for the talk. I'm Krishna at fiddler.ai. If you need to reach out, I'm happy to take any questions. Yeah.
Hey there, Krishna. Once again, thank you very much. Really good stuff here. The best way to give questions, by the way, is through the QR code that you all have access to. And there's a few that some of the audience members here would love to ask. The first one is, how does Fiddler handle trace propagation across nested agent calls?
Yeah, so the way it works is, so there are basically 4 primitives today, right? You have the application framework. So you could use your favorite application framework, LangGraph, Crew AI, Google has an agent development kit, whatever that is. And you have tools that you call. Tools could be, maybe you're creating an agent for customer support, so you're calling Zendesk or ServiceNow, Salesforce. And then you have models. You could be using GPT or Claude or other sort of models. And then you have observability. So what Fiddler what will do is it'll instrument this workflow. In this case, it's a lang chain, let's say it's a LangGraph workflow. We can basically instrument each of these steps and then log at each of these steps, log all the inputs and outputs and the decisions, and then provide a trace view. Right? Provide a trace view of the individual session, an individual session that happened, but also do custom aggregations. So you can then aggregate which tasks are succeeding, which tasks are failing, whether you're seeing more system call failures happening, whether you're seeing more model issues like hallucinations or PII exposure happening. You can sort of do that. And so this is basically a workflow around that, where a view of a trace view happening, where you can see individual parts of the tree, which nodes are working well, which nodes are not working well.
And because of time constraints, we only have time for one more question here. What does co-observing with agents really mean?
Yeah. So this is a very interesting concept, right? So if you think about traditional software applications, what has been monitoring so far? You essentially take logs from a server and you ship it over to an external system. It will then analyze things for you. Are there stack traces happening? Is there latency spikes happening? Are you seeing more throughput than you're expecting? Is there a hot shard in a database? These are well-studied problems over the years, right? Now, in many ways, this observability, you can call it a passive observability. With agentic performance management, because it's relying on these reasoning models and foundation models, you have an opportunity to be a co-observer. So where you can actually do an intervention, if you need to, with the help of guardrails. You can actually know if the response that you got out of a model, it's actually, let's say it's a hallucination. You can actually course correct it. You can reflect upon it. You can essentially try this once again with a different prompt adjustment so that you can get a better response. So this is actually a very, very new concept. So the whole sort of co-observing aspect of it is basically where an observable system works in conjunction with the application, where you have instrumented the application and you have essentially inserted your guardrails and fallback triggers into the application, so that you're not only monitoring the application, but you're also course correcting the applications to the right thing. So that is what I mean by co-observing. And it's a very, very interesting area to invest in.
Krishna, thank you very much. Great stuff here. Thank you.
Thank you so much. So if you're curious, look us up at fiddler.ai or reach out to me. Thank you so much for the opportunity.
Please welcome to the stage Alex Petrescu from Meta.
Thank you. Hello, everyone. My name is Alexandru Petrescu. I'm a software engineer. I work on the wearables platform team and Meta Reality Labs. I'm going to talk today about a different kind of scale, scaling AI into the real world. So we're going to talk about some of the challenges to building wearables and the Ray-Ban Meta architecture that we use to solve some of these challenges. We set off with a hypothesis at the beginning of this journey that for AI to be useful, it needs to be where you were. It needed to see what you see. It needed to hear what you hear. We're not alone on this journey. The industry has also been on a similar journey. We now have assistants on our computers. We have assistants in our home via smart home devices that you can talk to across the room. We have them in our pocket, built into our mobile phone operating systems. And now we're building wearables that are the closest to our perceptions. So we think that once you give these kind of capabilities, AI will start to be able to interact and help us out in the real world. For example, with tasks such as remembering things that are important, but you don't do very often, like parking in a new specific scenario. I hope this works for me when I get back home. It can also interact with more complex objects that are actually not meant for humans, right? Like QR codes that are starting to pop up everywhere. We can have our AIs be able to interact with this type of content in a way that is more difficult for us. Right now we have to pull out our phones, take photos, do a whole bunch of stuff. But also it can interact with content meant for humans, right? Like, for example, information on signs, whether it be this sign, or information from while you're walking around to be like, how close is the nearest school? What is its rating? How far is it to work? But also more lighthearted and little quick actions, such as taking a photo of your video of pushing your kid on the swing without having to stop, take out your phone, frame it, do all of that stuff. So assistants can help us in lots of real world scenarios and lots of real world everyday tasks. So we're going to talk about some challenges in building wearables, things that are kind of unique or interesting. We're talking about the Ray-Ban Meta architecture. We're talking about optimization specifically for AI on wearables. And then we're going to talk a little bit about what's coming soon. So the challenges first. I'm going to talk about 4 different challenges of building wearables. The first one's going to be design. Then we're going to talk a little bit about the hardware challenges. Then we're going to talk about physics, aka the real world, and then we're talking about some unique challenges when it comes to features of wearables. So the first, and I think probably one of the most important, is that for AI to be everywhere you are, and for it to be accessible, you need to be wearing it. And now it's on your body. It's now part of your style. It's part of your how you present yourself to the outside world. So these devices can't only be functional. They need to fit your everyday style and your everyday requirements. Whether you're going to work, whether you're at home, you're going out with friends, you're on the beach or in a ski lift, wherever you are, in order for AI to be useful in those scenarios, it needs to be accessible. So design is very important. For example, my wife has multiple pair of both prescription and sunglasses that she switches out to wherever isn't relevant that day. So we're lucky enough, for example, to partner with X or Luxottica to be able to provide lots of different styles and shapes and sizes and low bridge and different options. This is actually very important in order to making sure that these devices are usable in the most scenarios and the AI is accessible for the people when they want it to be. So the next step is once you have the shape that you want, you have to miniaturize all your hardware. So this is something that is quite tricky. It's, you have to figure out how to fit all of these little components in different parts, right? You've miniaturized everything, but it's really like a 4D Tetris puzzle. Certain things have to be in a certain position, like your mics have to be able to be in a certain place, your camera has to be, your battery has to be in a certain place to make sure you have correct weight balance. So you have all sorts of challenges of miniaturizing and trying to fit. And then each device that you fit in, each shape of style and things will have a slightly different design. So this miniaturization is actually quite difficult and takes a considerable amount of time. I should stop touching that. Next, is the real world kind of physics challenges that all wearables and all devices kind of face. There's power, there's thermals, and there's connectivity. I'll talk a little bit about each one. The first one is power. For these devices to be useful, they need to be accessible, right? They need to be powered on. So you have issues of both battery size and chemistry. So the battery size will, has lots of great benefits. So, bigger battery, longer battery life, you can use them longer. However, then they're heavier and different, for different applications, that doesn't work. You also have different battery chemistries and different type of batteries that you can use for these devices, but that will give you different peak power and total power. So I'm going to talk a little bit about both. Total power is, how many photos you can take, how long you can listen to music, things like that. That's pretty straightforward. That's, how big your battery is. That's great. But peak power is something that's interesting and unique to wearables, is because these batteries are so small, they actually can't produce a lot of power at the same time. And so certain components you can't use at the same time. You might not be able to use your Wi-Fi chip and do video camera, like video recording at the same time, for example. They might pull too much power in order for you to be able to do both those things. So you have to be very careful to orchestrate your different types of workloads. And this is the real world. These devices are with you in all sorts of scenarios. Your smart home device gets to stay in your nice air-conditioned house. Your wearable needs to be everywhere you are. Sometimes it's cold outside, sometimes it's hot. As any EV car owner knows, when it's cold outside, you get a few less miles from your charge. It is even more extreme for wearables because the batteries are even smaller and they're exposed to this weather even more. So if you're on a ski lift or it's the middle of winter, or you might get different capabilities of power from your batteries. Next, it's kind of related, but thermals. We've now miniaturized all these little things. You're like, great, we can make them really, really, really small. However, they still consume power. Any type of work that you do with these chips, with these things, will consume power. If you consume power, you generate heat, and now you're generating heat right next to someone's face, which is quite challenging and creating many different challenges for our designers of our hardware. So we have to be very careful with the types of materials we use and the way we dissipate heat from all of these components. We might not be able to, for example, use a particular component for too long because we can't dissipate its heat fast enough. So you might be able to use a chip for 5 seconds or 10 seconds or 30 seconds, but maybe not 5 minutes, because at that point, the amount of heat that it's generating is you're not able to dissipate with a little tiny form factor that we have available. And lastly, the outside world bites us again. If it's hot outside, it's really hard to dissipate heat. The hotter it is, so if you're building sunglasses like we are, and you're in Arizona and it's 120 degrees, that's much harder to dissipate that heat than if you're at home. So all of these challenges means we have to be very careful about the types of functionality that we provide and carefully orchestrate all of our components, our software, even in our initial design. So the last bit in physics is connectivity. We have These devices need to be connected to the internet to access our AI models and the world's information, right? You need to be able to access sports and search and do all these things. But we have, again, challenges of power. So we have things like 4G, that's super fast, but uses a lot of power. So it's just not practical for most wearable devices. We have Wi-Fi that is good because you can tune and you can make it lower powered if necessary. But generally, it takes a lot of power, especially if you're communicating with something across the room. But also, Wi-Fi is not accessible everywhere. It's accessible maybe here, but it's not accessible when you go walk around and go do something. And AI needs to be accessible. Lastly, we have BLE, which is great. It's in the name, Bluetooth Low Energy. It's low energy, but that low energy also comes really low bandwidth, which is the challenges for devices like AI that require sending and receiving significant amount of data. Images, video, audio. We have to send and receive that kind of information. That makes it a real challenge for all this. And lastly, offline, you have to think about these as well. It's very rare for our home devices, our laptops to be offline, things like that. But our devices, you're going to be in all sorts of situations. You're going to be traveling to different parts of the world. You're going to be in a subway. You're going to be in a basement apartment somewhere. Like you're going to be in a crowded stadium. So sometimes you have to make sure that your device still works, even though you don't even have connectivity. That's a challenge for AI-powered devices where AI needs to be accessible, and oftentimes that means talking to a server somewhere. All right. The last part is these challenges are product requirements. So AI, we've been talking a lot about agents and big models and all sorts of stuff. All of that is on, that makes sense, that exists somewhere on the server. So we definitely have to support, sending information to servers. We have to do multimodal requests, so that means we have to send images or video. So those are definitely requirements. But we also have to support really short commands, things like take a photo or take a video, call my mom. All of these need to be included as well, and they have different requirements. We'll talk a little bit about each one. Then we're dealing with sensitive information. We're dealing with things you're saying. We're dealing with things you're seeing. We're dealing with your contacts. We're dealing with messages that you were sending or receiving. So we have to be very careful about preserving user privacy and figuring out how we build and architect these systems in order to do that. Again, I talked about building these large models on our server, and everything's great. If you have to send everyone's messages and everything they see and everything they hear and all their contacts to the servers, that's not going to be a great story. So we have to think about these things while we're architecting AI for wearables. And lastly, speed and reliability. When you depend on these devices, speed and reliability become features. If I say, hey, take a photo, it needs to happen right then, that second. It can't happen 3 seconds from now because I need to establish a connection to the server. I need to send that. The server needs to process that. It needs to send the request back. Then I need to actually take the photo. It needs to happen now, because if it doesn't happen now, I'm going to lose whatever I was taking photo of, and I'm never going to do it again, right? So there's some commands that have to be instant and have to be super reliable, because again, let's say our reliability is 75% or something like that. If 1 out of 4 times it fails to take a photo of something that's important, you're never going to use it again. We need to build the types of reliability like a light switch. You need to be able to, you never question whether or not your light's going to turn on when you walk into the room. You just walk in and you turn it on. That has to be how wearables, the type of reliability wearables needs to have. Okay, enough challenges. Let's talk about how we solved some of these for Ray-Ban Meta. We have 4 main components. We have our glasses, of course, and we have our case, which I will talk about in a bit. We have a companion app on the user's phone. That's the Meta AI app. We can communicate with it over Bluetooth or over Wi-Fi. And then, of course, we have our Meta servers, which provide our large language models. So we'll talk a little bit about the hardware first. On the hardware, it's on the frames itself, we not have both input and output, such as like cameras and microphones and speakers and buttons and a touchpad. But we also have onboard compute in both a microcontroller and a system on a chip. We'll talk a little bit about both of those. And then for battery life, we have a 4-hour day of use battery on our frames. And then we also have another 36 hours of charge in our case. This means that as you're out and about, you don't have to go find a wall plug to charge up your glasses or something. You can just put them in the case, they'll recharge quickly. Actually, with our new Oakley glasses, which is just released, this is out now 8 hours of battery on our frames and 48 hours in the case. So we're making advancements even today in this. The glasses themselves, I talked a little bit about the components. The microcontroller is used for a power-efficient wake word. You know, this is something that needs to be accessible all the time. So as long as you're wearing your glasses, Meta AI has to be accessible. So our wake word has to be powered on and listening all the time. That's obviously very challenging with the amount of compute and power that we have. So we have to use a microcontroller and super efficient algorithms to be able to do this. However, then once we've detected wake words, we can use our compute, our system on a chip, for product logic. We can actually start to run models. We can actually do product logic, figure out what the user wants, and even perform certain actions for them. So for example, our take a photo request is completely processed on the phone. It's on the frames without needing any extra processing anywhere else. And then we have accelerators for on-device models like DSPs that allow us to run certain models and certain workloads in even a more efficient way. And lastly, of course, we have Bluetooth and Wi-Fi connectivity. Our phone provides connectivity for Meta AI. It provides communications, logic, and processing. It can talk to the phone app, it can talk to your contacts, it can send messages, receive messages, it can talk to WhatsApp, and send and receive messages from all of those apps. We can talk to our partner apps, such as Spotify or Audible or Be My Eyes, and be able to control those apps on behalf of the user. And we can also do advanced media processing. This is one of those optimizations where we can do a lot of media processing. We have a full system on a chip on our glasses, but it makes more sense to be more power efficient in these cases and offload some of this compute to the user's phone for advanced media processing. Our servers are pretty typical. That's where we have our big LLMs, advanced multimodal AI. That's where we have our plugin system, so we can do search. We can search for information and retrieve information from other places around the web. We have agents now to be able to do certain tasks, things that take a little bit longer. And then we have personalized user memory to remember user preferences and also remember things that the user asked us to remember. So with this architecture, we have on-device compute that is fast, is reliable, and is privacy conscious. We have our Meta AI app, which allows us integrations into all these different phones, apps. Right? It provides privacy because your messages stay on your device. And then it provides connectivity. And then our meta servers, that's where we have our real advanced AI capabilities. That's where our extensibility is. But making it work is not enough, right? We have a solution, it works. But like I said, speed is a feature here. So we're going to talk a little bit about some optimizations for AI that we found are most interesting and most useful. So let's talk real quick about, let's look at an example utterance and how we would normally process it. If the user says something like, what does the sign say in English? We would transcribe the user's text. We would perform some sort of understanding on it. We would get some sort of final decision on what actions we need to take. Then we'd perform those actions. So we know we need to take a photo because the user is asking about something they're seeing. We need to do some OCR on that photo because we need to understand the text that's in the image. We need to resize it because we need to send it to our servers, and that, over BLE. So that takes a little while. And then we need to send it to our servers. And then our servers respond, and we're done. What we're trying to optimize in most of these scenarios, and what's most important that we think, is user perceived latency. That's basically the time after the user finished speaking to when the system actually responded or did the action. So that's what we are trying to optimize in most of our scenarios, most of our things. So let's talk about some ways to do this. There are predictive processing is probably our top choice for this. This is basically starting to predict what the user is going to want to do, maybe certain parts or certain actions, before the user is done speaking. This is actually a very powerful technique because, even when I say, what does this sign say in English, by the time I say a few of those words, we might be able to predict that we need to take a photo, for example. Then we can once we predict, we can start doing multiple things at the same time. I said we have to be careful about orchestrating all of the different types of workloads, but we can actually do multiple things at the same time. We can maybe load the next model while the speech model is going. We might be able to take a photo or resize something. And then we can use accelerators judiciously, right? And figure out which accelerators make sense for which workloads. So we'll go through the same example with optimizations. So while we're transcribing the user speech of what does this sign say, we can start performing understanding. We can start to predict some speculative operations, such as, we need to take a photo now. The user's still in the middle of their sentence. We can start taking a photo. We can start saving it to disk. We can start processing it. And then we can, for example, decide to run our OCR model on an accelerator because our main model is running on the CPU. So we can choose to figure out which models run in which places. And then we have to wait for the for the user to finish speaking, right? People say all sorts of things, and they could change their mind at the very end, or they could say something that we didn't expect. So you still have to wait till the very end. You can't just send and you're done. So there is some time still at the end. We have to send all of this to the server, and we have to respond. However, as you can tell here, we've reduced the user perceived latency quite a bit, even though we probably haven't made any of the individual operations any faster. If anything, if I'm going to be honest, since we're using and we're competing for resources on the device, some of these are actually slower, which is counterintuitive that you made each individual thing maybe a little bit slower, but the whole operation significantly faster. So with this, we've been able to perform commands such as take a photo, call my mom, all sorts of things, in a snap of your finger within less than a second with very high reliability. We can also do advanced AI requests, such as something that requires an image to be sent to a server within a few seconds. But this journey is never finished. We're constantly looking for optimizations of even tens of milliseconds throughout our stack. Let's talk a little bit about what's coming soon. Agents are coming soon. That's everyone's. But I said that reliability is very important. With agents come much more complexity that we have to deal with, not only in terms of how long they take, because they can be a little bit unpredictable because they have reasoning, but also reliability, right? Because they can take multiple steps and they can fail at any step. We're expanding to more markets. We just expanded to India and Mexico. So we'll have more different types of users talking and doing requests on our servers. And we're adding more features, such as we just launched live translation, which can do speech translation in real time with another person on the glasses, even offline. I've talked about a few of these. We're not done. We have all these optimizations. We have all these new workloads. We have power utilization is going to continue to be a problem for all of us. We have more competing workloads with all of this predictive work. But with I-18N and we're moving into different markets, we're probably going to have more model misses, right? We're going to have people are going to say things in different ways. So this is a continuous process in order for us to make sure that we continuously stay fast. So before I let you go, I just want to say building devices that bring AI into the real world takes a village. There's a lot of different types of partners that need to work on these devices in order for this to come to life. And thank you for them, and thank you for everyone coming to the talk.
Alex.
Sure.
Alex, some very good stuff there. Thank you so much. Due to time constraints, we only have time for one quick question. So it came from the crowd. Once again, thank you all for submitting your questions on the QR code. And the question is, how do you approach user testing and feedback integration during the development cycle, especially considering the diverse real-world scenarios and user behaviors for a device like Ray-Ban Meta?
It's real tough. Dog fooding is very, very, very important for everybody. So we have to make sure that we use these devices as real users. You can't just use them in your office as developers, put them on your head, try them a couple of times, take them off and be done, right? You really have to take these devices home, live with them, put them in the rain when we're on a jog and you're sweaty, and file those bugs and complaints, right? We have to collect data. So our analytics is very, very important, collecting analytics from production. And like I said, because different people can say different things, and it's very important. We always have to measure what's happening actually in production and constantly take that feedback back to our training and improve our models, especially the ones that do predictive processing. So it's definitely challenging. It's probably one of the hardest parts.
Alex, once again, thanks again for your time. Appreciate it.
Thank you, everyone.
Please welcome to the stage Kartik Lakshminarayan from Meta.
You made it this far, thank you. So before we dive into the panel, can I just make a request? Can all of you just stand up? 10 seconds, just stretch. No break. Last session after lunch. You can do yoga if that's what drives you. Just need some energy flowing while we get the panelists out. Thank you so much. All right, let's get our panelists out. Thank you.
Please welcome to the stage Delia David, Anna Berenberg, Bar Moses, and Chi Kay.
Thank you, thank you. All right, I was thinking about how to make the intro here, and after listening to the talks all day, I don't want to repeat the same thing, right? By now, you already know AI agents are just different. They're not just responding to your commands. They have a mind of their own. They work autonomously. But all of that creates a massive shift in even the concept of what we think is infrastructure. And that's what we are here to talk about today, right? This is changing how we think about infrastructure. How do we build? How do we scale? How do we secure? It opens up lots of questions. But fortunately for us, we have 4 brilliant minds that are going to help unpack this, maybe give us a lot of food for thought of how you think about this. So let's dive right in with some introductions. Delia, if you could go first, tell us a little bit about yourself and one thing that's super exciting for you in this agentic future.
Hi, everyone. I'm Delia. I'm an engineer at Meta. I've been at Meta for 14 years. For the last years, I've been working on data infrastructure for recommendation systems and generative AI. And most recently, I've been working on data execution environments and tools for web navigation agents and code agents. What I'm excited the most, I think personalized education. because everyone should enjoy physics and math, and any other topics you're interested in.
Everyone should enjoy physics and math. Love that. Anna, if you could go next.
My name is Anna Berenberg, and I've been at Google for 19 years, and I'm engineering fellow there. I work at Google Cloud, and I'm responsible for platform. Not like we have 300 products, but you need one platform, so it's a solution, not a product. What I'm most excited about that in the last 30 years, we built web serving stack, and we optimized it, and we did everything. And now AI came about, and it's just upended the whole stack, and you have to build from the ground up. And so it's an exciting time to be an infrastructure engineer.
Always an exciting time. Bar.
Infrastructure was always cool. I don't know what you're talking about. My name is Barb Moses. I'm the CEO and co-founder of a company called Monte Carlo. Monte Carlo is creating and leading a category called Data and AI Observability. And our mission is to help accelerate the adoption of data and AI by increasing its trust and reliability. So we work with over 500 enterprise with companies like Roche, Fox, Cisco, Intuit, and many others, helping those building data and AI products, making sure that they're reliable. I'm personally excited, definitely about infrastructure for sure. Also about personalized biomedicine. Really excited about sort of better outcomes that we can drive through better healthcare.
Personalization seems to be like a key theme here. Chi.
Hey, my name is Chi. I'm the corporate vice president in Azure, mainly in charge of Kubernetes and other cloud-native services. I have been bouncing between Google and Microsoft a few times. One of the most exciting thing to me as an engineer, so coding agent is the most exciting to me. And with a quick involvement in this space, I just feel in the future the V2 is not so daunting anymore. Because anyone did services, you know that when you design a system, you always face choices, like is that the A or B, and we don't know, there's trade-offs, pros and cons, but until you have A and B, you never know which one is absolutely gonna be better. You have back of the envelope calculations, but now I hope with so many AI coding agents, we could implement both and test both out. That's what makes me feel very happy.
Amazing. It just great to hear, even in the intros, all these perspectives. But I'm going to dive right in, set some context for the audience, please, if you will, Delia. Can you just tell us why is this change in infrastructure even happening? Maybe set some context of what to expect. What is driving all this change?
Yeah. So first of all, agentic workloads are unlike most of the workloads we deal with in infrastructure on a day-to-day basis. If you have worked on reinforcement learning for games, robotics in the past, then maybe you're familiar, but most of us in infra are not. One thing, agents are exploring massive search spaces in order to find solutions, as opposed to doing a well-engineered single solution in traditional software. These solutions take tens, hundreds, or even thousands of steps, extremely long. They are requiring us to really redefine reliability, latency, and security of our systems. And to leave you with one example, one thing we are working on is web navigation, and part of that is shopping. So let's say I'm organizing a summer camp, and I want to buy T-shirts. I want to buy tens of T-shirts of different sizes, different colors, same theme, but like different design. And of course, I was late, and I need to overnight all of them. Now imagine how many actions on the web, on multiple websites, these agents will have to do. So that's the challenge we are working towards.
That's great. I think that's a lot of context. I'm worried about what that credit card bill is going to look like with these agentic shopping experiences. But that's great context. Maybe we can dive into what are some specific changes that you're starting to see with this context that Delia just shared in our systems. Maybe start with you, Bar, and what you're seeing in your work, how is this evolving? What are some of the key needs?
Yeah, and I love what Delia said around the importance of the security, latency, and reliability of systems. And I think with sort of the rise in AI and agentic systems, we have to think about that differently than how we have thought about it today. But maybe just starting with, like, why does that even matter? Like, why do we need these systems to be reliable? I'll just share a real-world example that happened a couple of months ago. I think this was a Chevy Tahoe, basically a website, a car website, and a user was sort of interfacing with a chatbot, and the user convinced the chatbot to sell them a Chevy Tahoe car for $1. Now, I commend the user for being able to convince the chatbot to do that, but think about not only the revenue implications of that, also the brand and trust implications that happen in these instances, right? That's just one example. Another example that went viral a couple of months ago was, I think there was a chatbot for Cursor's customer support that they built, and the chatbot was hallucinating a policy that didn't even exist, and that sort of went viral. And so, these are instances where the reliability of these systems matters for us, not just as a society, but also has real implications here and now. Now the question is, how do we build reliable systems with undeterministic models with this whole world? And I think one of the common failures or sort of common mistakes that we see is thinking that you can think about AI systems separately from data systems. And really, I think thinking about them as sort of divorced systems is wrong. Oftentimes, AI systems can be wrong because of a problem in the data. It could be a problem in the AI itself. And so actually, I think thinking holistically about the data and AI estate, what does that even mean? And if you think about the last 10 years or so, infrastructure teams are building with databases, data warehouses. We've seen the rise of the lakehouse, ETL, BI, ML. That whole sort of estate, if you will, is expanding massively. And now you add to it, different orchestrations, agents, prompts, RAG pipeline. I'm throwing a lot of words, but this is basically a pool of sort of, architecture that the platform team now owns, and that entire thing needs to be reliable. And one of the sort of early thoughts that we're starting to develop is that a system can be unreliable for 4 core reasons. The first is the data ingested can be wrong. So literally it can be data that's inaccurate. The second is you could have a problem with the code. So there might be a code change that has downstream implications. The third thing that can happen is you can have a system failure. This could be some orchestration that's not completed. And the fourth thing is that you can have all of that run perfectly, but the model output will still be inaccurate or just not fit for purpose or just not what you expected. And so, what we're starting to develop is think about your data and AI estate holistically and think about these 4 core pillars for what can go wrong and starting to develop an observability around that framework.
Awesome, thank you. Anna, if I can have you add on, I'm sure you have your own perspective of how you see things.
Nobody talks about networking. It seemed to work. But if you just look inside of it, it actually doesn't. It barely works. You're just holding it with Band-Aid. What happened, right? HTTP usually expecting to have this millisecond request response latency. Here you have seconds sessions, so you need streaming. Do you need streaming on a protocol? You need the streaming on an application. Let's look at the load balancing. What load balancing? You can only serve one RPS. I mean, not one request. And with one request, you can do 100% of CPU utilization. So you no longer can load balance based on a request on a weighted round robin or any of that. None of that works. Now you need to know the queue depth size. Now you need to know number of tokens. Right? Then you talk about routing. Routing doesn't work because, hey, who can route based on the natural language? So everybody is building routing in their own AI application, and networking is like, oops, don't know what to do with it. So will it push down into the networking itself? Then caches, think about caches. Cache is no longer a thing, right? Because it's every time you get different answer, so you need a semantic caches. Then you start thinking about policies. Hey, policies, how do you even do policies if you don't understand the protocols? So now you have to suddenly, HTTP is not enough. Now you have to understand OpenAI or Gemini APIs even to talk to models. You need to understand MCP to talk to tools. You need to understand A2A to talk to agent, right? So because you actually need to understand where's the prompt, for example? How do I understand which prompt is being injected, and how do I do content checking and stuff like that? And then all this thing is actually located all over the countryside. Some of it could be on your VPC. Somebody could be on somebody else's VPC. Tools can be on internet. Some agents could be provided by the cloud provider and your own. And you have this mix of different paths for which you need to orchestrate. Everything needs to be orchestrated because it's actually a bit on the insane side, right? Because the outcome is non-deterministic, could hallucinate, could buy a car for $1, right? So how do you protect against buying a car for $1? And all of that requires policy, and all of that requires new networking. So it's exciting, very exciting.
I think buying a car is a good thing if you're a consumer for $1. So we got to figure that out. But maybe bringing you in, Chi, like I know safety and security is really important. Is this conversation so far like really terrifying for you?
Yeah.
How are you thinking about security?
Absolutely, absolutely. Resonates so well with me. $1 for the car, and these are benign cases. Like people are not even intentionally trying to attack or trying to breach the system. And there are cases where attackers are there. If you think about the LLM or AI help developers to be more productive in security space, hackers too, they can leverage LLM too. Recently, there are several cases like recent GitHub had a 0-day CVE that some carefully orchestrated attack, they use the GitHub issue. They have some malicious prompt, they embed into a GitHub issue. You would never think, okay, that's GitHub issue, it's a data. How can it be malicious? But people utilize that. And then they create the MCP server, and everybody think, oh, it's from GitHub, so I'm going to install this MCP server, I'm going to use it. And turned out it exposed people's private repositories in public repos README file. So this is data filtration. But these are carefully orchestrated attacks that in the past might not be so easy, might be harder with LLM. We power these attackers more. So so in this world, these context pollution, context poisoning, not pollution, poisoning become something that is really threatening this world. Of course, that just like I think Hassan in the morning said, these attacks should not prevent us to continue to develop agents. We should still do it. But we do have to keep this in mind when we start to develop these agentic AI workloads.
Yeah, very insightful. I think all progress happens when there are challenges, but you move forward. It's part of them. But let's push on that. I think failure modes is a key point. Maybe bring you in, Delia, like share a little bit about how you think about failure modes and the impact on like reliability and what thoughts you have for that.
So maybe I can start with the simple things, unknown unknowns. Typically in a project you have 5–10% unknown unknowns. I think here it's completely flipped, like 95% is unknown. And maybe we can take an example. Let's take coding agents, or even more generally, software engineering agents. So now imagine in your company, you have your services, but like everyone else has 10 agents, 10 AIs doing work for them 24/7. These agents are extremely prolific, like way more productive than you. They can do in few minutes what you can do in hours in terms of, let's say, coding. So now, what could go wrong? I think it's safe to assume that if you haven't tested something, it will go wrong. So everything will go wrong. So what do you do in this case? I think everyone needs to develop more fluency in AI, starting with evals. Like we really need to ramp up on how to build a good, diverse, comprehensive eval across pretty much all levels of difficulty. And how do we evaluate individual systems and then connect the dots into workflows across multiple systems? And of course, how we do this in secure sandboxed environments, because you don't want to risk production. But yeah, pretty much everything could go wrong. This could be bad API calls. This could be overload, like systems getting 1,000 times more the load because you have all these AIs working nonstop for everyone in the company. This could be CLI comments corrupting data, and of course, security problems. So another thing that I would mention, we need to be very diligent in instrumenting everything about agents, like all the calls that happen across the systems. Like, is this call issued by some code that a human has written? Is it from an AI? Whose AI is it? What prompt generated it? What's the step-by-step rollout or trajectory? Because one, you want to keep some of these trajectories, convert them into training data to train the next generation of your agent. And then two, you want to debug issues, so you want to replay these trajectories.
Sounds messy. But
yeah, I think the more tools, the more agents you have, the messier it gets. Definitely beyond my imagination.
maybe some job security out of that. I don't know.
I'd like to add here.
Please go ahead, yeah.
So we talk a lot about observability. There was a talk about agent observability. Now we talk about data observability and reliability. And all that comes to the question, how do we build commercial systems, right? So if everything can go wrong, how do you build commercial AI application? To build a commercial AI application, observability is required but not sufficient. You need to have a health checking. So what does it mean for agent to be healthy? If LLM behind agent hallucinate, is agent healthy? How do you detect if with a bad prompt something got hijacked and now is actually agent is being instructed, essentially being hijacked because something instructed LLM to generate code that does something not expected, right? Is this agent healthy? What does it mean healthy with regards to, are we going to fail over from this agent? Or are we going to take it out of service? Is this agent, is it good enough or not? And so everything is changing so much that basic concept like health checking have to change from the ground up, and it's fascinating.
Yeah, I think I want to shift to left a little bit, because we're talking about after the binary is launched. What about before or while, right? I think earlier this morning we talked about eval. This eval function. I think in the future we just need to make sure we write sufficient tests and the code can be ephemeral. The code can be thrown away and let AI rewrite it. But what's important is the behavior need to be preserved. I understand it's easier to say than do. If you have 10 parameters, and each parameter, if you have just 2 values, you get 2 to the power of 10 combinations if you want to enumerate all of them. And if the value goes up, and if your number of parameters goes up, your system can be very complex, very hard to guarantee. But with the API kind of system, it's doable. And with AI, maybe it's easier. So I have always been, that's why earlier I brought up this V2, is code become ephemeral. We can always rewrite in different languages.
Fascinating, thank you. We've been talking about agents and infrastructure, so I want to pivot this to humans. Just saying the quiet part out loud, how did the role of humans in this new world evolve? Like, what advice would we have, maybe looking to you, Bar, to help share that perspective?
Yeah, I mean, I think, I was saying this earlier, like I'm ready to go to the beach and have agents do all of my job. If that can happen, sign me up. But I think if you look at history, software engineering as an example has come a really long way, like from the days of COBOL and whatnot. And if anything, we've needed more engineers However, the job has changed dramatically from what we've been doing. And so I think this technological change is different than any other that we've seen. However, I do think that humans, more than any time in the past, are needed, whether it's human in the loop or in any other version. And so I think, I think the jobs will be different and how we work will be dramatically different, but I think the need for different types of work will be required. And I'll just share an anecdote. I was talking to sort of a CTO of Fortune 500 company a couple weeks ago, and he basically shared, maybe some of the sentiment among this panel. He was basically telling me, I'm gonna have 5,000 agents in production by the end of the year, and I have no idea what the hell is gonna happen. I just don't know what's gonna happen there. And I think the notion of, can we instrument everything? Can we do evals? Can we do all of the above is I think very appealing. And the question becomes what do we automate? Where do we have AI? One of the things that we've in our experience, we build various agents. Like we've built something called a troubleshooting agent that basically helps teams automate the work of, once there's an incident, identifying what's the root cause of it. So if you take the work of an analyst or an engineer, when there's an incident, they basically, if it's a Sev0, they start coming up with different hypotheses. What we've done is we've taken an agent that spawns sub-agents, and basically each agent recursively looked into a hypothesis, and then there's basically this orchestrator agent that sums it all up. Now, the interesting thing is that people love that, and they love the ability to have to automate all of that work. But guess what? People really don't want this agent to actually fix it for themselves. They want to be able to say yes or no before you take any corrective action. So there's a very, very strong need still for a human in the loop, especially when it comes to taking actions and making decisions. But all the research, the summarization, the sort of recursive, more manual toil, definitely, I think there's a lot of appetite to that. And maybe in the future, this sort of notion of multi-agent and sub-agents become even more popular and more sophisticated.
Cool. We're almost out of time. We're going to leave with one last question for all of you, starting with you, Chi, which is, what is one bold prediction that you're willing to make of something that's going to happen in the next 12 months?
I think right now, agent is still more in the software side. I'm hoping tomorrow, in a year, it get to hardware. I can make my own robots. I don't have robots. I don't have to wait for some company, maybe in China, to make those robots for me. It's like a Lego. I can have them connect to LLM to help plan and maybe help me do the house cleaning, but to my own taste, not somebody pre-made. Like MCP for robots.
All right.
Awesome.
Thank you. Bar.
I was reflecting on, a couple of decades, there was this mobile revolution, and then there was a slew of startups that were like mobile, and everyone was mobile first, and there was a lot of talk about that. And now, we're kind of all mobile, and we don't have to use the word mobile anymore because it's obvious. I think in 12 months, the same thing is going to happen with the word agentic and with the word AI and the word generative AI. We don't need to spell out that everything is agentic and generative AI. It's just going to be that way.
Nice. Anna?
There was promise of intent-based configuration forever and ever, right? And it never materialized. And people tried and tried and tried. And I believe that we are going there. I don't know, 12 months, but I'm hoping within a year there's going to be a change, because natural language processing, by definition, will drive products, and they will drive configuration, and basically it's going to transition itself from the knob-based stuff to the intent-based, because it's easier that way to translate.
Delia.
I hope in 12 months, one of these models solves an open math problem. Maybe not quite the Riemann's hypothesis that everyone is talking about, but one open math problem.
I'm a simple guy. I like more beach time. I thought that's what you would say. But anyway, thank you all. This has been, thank you to the panelists. Thanks for all of you. Put our hands together.
Please welcome to the stage, Yelena Pieszewicz-Grobowicz from Meta.
what a day. Oh, this is. Hi, everyone, and what a day, right? Like, I hope everyone enjoyed the program that we created for you. For our virtual audience, this will be kind of closing. And for everyone in person, we still have a poster session, a raffle, and a few other things. All of the talks that you've seen will be posted online on our YouTube channel, Facebook video, and a few other places. And we hope you'll engage with them, share them with your friends. We also hope you'll consider applying, registering for our next events, like networking and a product at scale. Networking is in August in this location, and product at scale will be in, I believe, in Menlo Park in September. With that, again, like for me, this day was quite interesting and inspiring. Like, I can't wait to see like the predictions we heard here and like throughout the day about what will happen over a year or on a longer time horizon. There is no way denying this is an interesting time to be in this industry. Probably all of our jobs will evolve as well. And I think it's a very meaningful thing to connect on and build a community around. So please stick around for the poster sessions and happy hours. And we still have a raffle for Meta Ray-Ban glasses. So I'm going to read them. And this time, we'll have Nick help actually share, take the glasses to the people who get them. So we'll start with the first number that I have is 363-9651. So again, number is 363-9651. Do we have? OK, going once, going twice. The next number. OK, so this one is 310-968-2. 310-968-2. These are really bright. OK. OK, the next one is 410. Oh, you got it? OK, sorry. 36. Nope. Sorry. That was close, but like a few digits off. OK. 410-9712. 410-9712. OK, we'll have to come up with a methodology to get the numbers in the room. OK, another 410 number. Is there any excited about 410 numbers? OK. OK, 410-9686. 9686? Oh, OK, one off. OK. I guess we'll, like, if we don't find anyone in the next 10 minutes, like, we'll go with, like, plus minus 10. Is there? We have a winner, yay! 410-9686. That's a winner. Woo! OK, we have one more. We're within a time slot allotted for the raffle. So let's go back to 363. Any 363s in the room? OK. 363-9684. 363-9684. OK. How about another 363-9618? 363-9618. OK. Do we have it? Woo! OK. Well, I guess with that, thank you, everyone, for coming. I hope you enjoyed the day. And please stay for happy hour and the networking and spend some more time with posters. Thank you, everyone, for coming.